Preface of Organic Evolution. This is the LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Preface. The addition of another to the long list of books which have been written on evolutionary subjects would hardly be justified in the present instance, were it not for the fact that the writer is a paleontologist, whose viewpoint and the evidence at his disposal are therefore materially different from those of the great majority of authors who have enriched the literature of evolutionary biology. The discussion is not based solely upon existing evidences, but also upon the geologic life record, which, although very imperfect compared with that formerly present, is nevertheless wonderfully rich in precept and example, such as do not come within the scope of the usual methods of instruction. The work aims to be comprehensive in its scope, but should make a special appeal to students of the past life of our globe. It is hoped, however, that a wider public will learn thereby that the science of paleontology has a unique social or human value. The work is the outcome of 23 years of college teaching, during the last 11 of which, courses more or less closely paralleling the substance of the present volume have been offered to Yale University students. While the course at Yale has been presented in the form of lectures, a textbook, Jordan and Kellogg's Evolution and Animal Life, has been used for reference, especially in the earlier lectures. The use of that excellent work has necessarily influenced the author's teaching, and as a consequence, the writing of the present book, certain chapters of which will be seen to parallel somewhat those of Jordan and Kellogg. The writer wishes thus to acknowledge his indebtedness to this source. For the larger part of the work, the sources vary, the principal references being given at the close of each chapter. These collectively form a representative bibliography of the subject from the present writer's point of view. Each chapter, as it has been written, has been referred to one or more of the author's colleagues for criticism, and, so far as possible, such criticisms have been met and suggested additions inserted. It is hoped that by so doing, errors of fact have been in a measure eliminated. The final responsibility, however, lies with the author. I am deeply indebted to my colleagues, Professors Schuchert, Barrell, and Woodruff of Yale University, and to Professor W. K. Gregory of Columbia University and the American Museum of Natural History for painstaking criticism, as they have collectively read and commented upon the entire work. Dr. W. D. Matthew of the American Museum and Professor H. H. Wilder of Smith College have also aided me in the text, while I am able, through the courtesy of President Osborne of the American Museum, the New York Zoological Society, through Mr. C. W. Beebe, the United States National Museum, that of the Academy of Natural Sciences of Philadelphia, and the Peabody Museum at Yale, to present the series of photographs which form the plates. The text figures, which have been taken from many sources, have, with very few exceptions, been especially drawn for the book, and are very largely the work of Mr. William Bakke, which was rendered possible through the generosity of the publishers. A very great portion of the labor of preparing the manuscript and of seeing it through the press has fallen to Miss Clara M. Levine of the Yale Museum, to whom I am especially grateful. Richard Swann LULL, Yale University, June 1917. End of Preface. Recording by Lucretia B. Chapter 1 of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Chapter 1. History of Evolution. Part 1. The problem of the creation resolves itself into two aspects: the origin of the forms of life and the origin of life itself. It is not surprising, therefore, that these great questions should be among the earliest recorded speculations of humanity, for life in its varied forms comes so close to personal experience. Theories of origin. 4 theories have been advanced to account for the existence of the varied kinds of animals and plants on Earth today. Theories in some respects diametrically opposed to one another, in other respects somewhat in accord. They are: 1. Eternity of present conditions. 2. Special creation. 3. Catastrophism with a. Repopulation by immigration, b. Repopulation by successive creations. 4. Organic evolution. Theory of eternity of present conditions. The first theory argues for the unchangeableness of the universe, holding not only that organisms have been unalterable throughout their existence, but that they have always existed and will continue to exist in the same unchanging state throughout eternity. This was apparently the belief of very few authorities, for one finds almost no allusion to it in the literature of science, although Hutton wrote, quote, "The result of this physical inquiry is that we find no vestige of a beginning, no prospect of an end." End quote. Whether this should be interpreted as a statement that the world has neither beginning nor end is, however, open to question. Theory of special creation. The second theory, that of special creation, is the literal interpretation of the Mosaic account of creation set forth in the first chapter of Genesis. A simple story, beautifully told, derived from the Hebrew tradition and well suited to the state of knowledge of the times and of the people for whom it was written. This account, strictly interpreted, has been the teaching not alone of the Hebrew, but of the Christian church authorities for many centuries, although the increase of zoological knowledge made it harder and harder to reconcile with observed facts, until, strained almost to breaking, it had to give way to the doctrine of evolution. Suarez. One of the greatest advocates of the special creation doctrine during Christian times was Father Suarez, born 1548, died 1617, a Spanish Jesuit priest who taught emphatically that the world was made in 6 natural days. On the first of these days, the materia prima was made out of nothing, to receive afterwards those substantial forms which molded it into the universe of things. On the third day, the ancestors of all living plants suddenly came into being, full grown, perfect, and possessed of all the properties which now distinguish them, while on the 5th and 6th days, the ancestors of all existing animals were similarly caused to exist in their complete and perfect state, by the infusion of their appropriate material substantial forms into the matter which had already been created. Finally, on the 6th day, the anima rationalis, that rational and immortal substantial form which is peculiar to man, was created out of nothing, and breathed into a mass of matter which, till then, was mere dust of the earth, and so man arose. But the species man was represented by a solitary male individual, until the Creator took out one of his ribs and fashioned it into a female. Huxley. So profound was Suarez's influence upon European Catholic thought that his teaching continued to be the only orthodox belief in Europe until the middle of the 19th century. In a similar manner, John Milton, born 1608, died 1674, influenced Protestant thought in England by the wondrously written story of the creation in Paradise Lost. Some advocates of the theory claimed that none of the forms had changed in the several thousand years which had elapsed since the beginning, but that the latter-day descendants were in every way precisely similar to the original pair when they issued from the hands of their Creator. Other keen observers, like Linnaeus, thought that all the species of one genus constituted at the creation but one form, ab initio unum constituerant speciem, their number being subsequently increased through intercrossing with other species, and the hybrids thus produced forming additional species to those originally created. Linnaeus also held that certain forms had lost their pristine character through degeneracy, the result of climate and environment. Theory of catastrophism. Cuvier. A new complication arose through the discovery of older faunas, the remains of which were preserved in the form of fossils, and which seemed to represent creatures whose existence antedated that of the living types. Cuvier, born 1769, died 1832, one of the founders of the science of paleontology, became interested in the bones which lay buried in the gypsum quarries in the hill of Montmartre within the present limits of the city of Paris. His studies of these forms, and especially his reconstructions of their skeletons, showed the great anatomist that he was dealing with extinct animals which had no existing representatives. Cuvier also had, because of his official position in the Jardin des Plantes, the opportunity to study hosts of specimens from all parts of the earth, and as a result of his research gave to the world a new theory, that of catastrophism or cataclysm, to account for the extinction of these forms. He is generally accredited with the belief that the cataclysms were worldwide and that the slaughter of the older fauna necessitated the creation of a new one to take its place. That belief, however, was held by later scholars of the same school, but apparently not by Cuvier. What Cuvier believed was that the catastrophes were local. Quote, "Sudden revolutions, such as subsidences of the earth's crust, followed by invasions by the sea of continents once dry, while other revolutions resulting in the upheaval of mountain chains have again cast back the waters and allowed, on the foundation of the dried bottom of the sea, the constitution of continental soils favorable to the expansion of new terrestrial faunas. These new faunas are not created on the spot, but come from distant regions, their migration from which has become possible owing to temporary bridges between continents." De Pere. Cuvier's belief has a great deal of truth in it, except that the revolutions with resulting climatic change and consequent extinctions and immigrations have been rapid only in proportion to the length of geologic time, but very, very slow, as mortals note the flight of years. D'Orbigny. Further knowledge of historical geology led to an expansion of the catastrophic belief far beyond the teaching of Cuvier, and postulated a recreation following each cataclysm and corresponding to the principal geologic periods. Alcide d'Orbigny, born 1802, died 1857, writing in the year 1848, expounded this theory as follows. Quote, "The first creation shows itself in the Silurian stage. After its annihilation through some geological cause or other, A second creation took place a considerable time after, in the Devonian stage, and 27 times in succession, distinct creations have come to repeople the whole earth with its plants and animals after each of the geological disturbances which destroyed everything in living nature. Such is the fact, certain but incomprehensible, which we confine ourselves to stating, without endeavoring to solve the superhuman mystery which envelops it." De Perret. Theory of Organic Evolution. Evolution is the gradual development from the simple, unorganized condition of primal matter to the complex structure of the physical universe, and in like manner, from the beginning of organic life on the habitable planet, a gradual unfolding and branching out into all the varied forms of beings which constitute the animal and plant kingdoms. The first is called inorganic, the last organic evolution. Early Greek theories. Organic evolution is often imagined to be a 19th century contribution to biologic science, whereas the idea is itself the product of an evolution of thought and is the fruition of no fewer than 24 centuries of speculation and research. The germ of the evolutionary idea had its inception with the Greeks, whose wonderful fertility of mind has so enriched the world. The first writer to deal with the problem, Anaximander, living 5½ centuries before the Christian era. Empedocles, born 495 BC, died 435 BC, may be called the father of evolution, though the evolution that he taught implied no succession of related animals, gradually improving in successive generations, but a series of attempts on the part of nature to produce more perfect forms, the unfit being eliminated. He is the first to show the possibility of the origin of the fittest forms through chance rather than through design. Another Greek, Democritus, born 460 BC, died 357 BC, went further than Empedocles in that he taught the adaptations of single structures and organs, whereas the latter applied the idea to entire organisms. But by far the most notable figure in Greek philosophy was Aristotle, born 384 BC, died 322 BC, whose versatility as a writer upon all aspects of human knowledge was remarkable. In view of the limited opportunities for observation possible in those days, when the teeming host of microscopic forms as well as the extinct creatures were utterly unknown, the deductions of Aristotle, even where he appears to retrogress from the truth, are highly logical. He did not believe in special creation. Nevertheless, he postulates an intelligent design as the primary cause of the changes which have been wrought in nature, and the central thought in his evolutionary theory, if such it was, is an internal perfecting tendency, impelling organisms to greater and greater perfection. As a result of this, he saw a complete gradation in nature from the mineral to the plant-like animal, the animal with senses, and hence locomotor powers, and finally man. Aristotle considered life a function of the organism, not a separate principle, and had an understanding of adaptations and of heredity, even of the atavistic heredity wherein an ancestral trait reappears in a later descendant after having lain dormant for several generations. Osborne says of him, quote, "Aristotle's argument for operation of natural law rather than of chance, in the lifeless and in the living world, is a perfectly logical one, and his consequent rejection of the hypothesis of the survival of the fittest, a sound induction from his own limited knowledge of nature. If he had accepted Empedocles' hypothesis, of the origin of the fittest through chance rather than through design, he would have been the literal prophet of Darwinism." End quote. To summarize, then, the Greeks offered as causes of evolutionary change 3 explanations: 1. Intelligent design; 2. The operation of natural laws implanted by intelligent design; 3. The operation of natural causes due to laws of chance. No evidence of design, even in origin. Middle Ages. And now, for hundreds of years, owing largely to the repressive measures of the Church authorities, though some, like St. Augustine, would have taught otherwise, the progress of the evolutionary idea virtually ceased until the coming of the philosophers Bacon, Descartes, Leibniz, and Kant, and the naturalists Linnaeus, Buffon, Erasmus, and Charles Darwin, E. Geoffroy Saint-Hilaire, and Lamarck. The philosophers contributed very materially to the problems of causation, but the real proof of evolution lay in the facts concerning animate nature which the naturalists gathered and explained. Linnaeus. Among the great naturalists, Linnaeus, born 1707, died 1778, was a contributor of facts rather than of theory, for his faith in the origin of species through special creation never wavered, except that he believed in the production of post-creation forms by hybridizing or by degeneracy due to climatic change. He was one of the first to put systematic zoology on a firm basis and advocated the scheme of double Latin names for each clearly defined species of animal and plant. Linnaeus' work, however, proved a great stimulus to the research along evolutionary lines which was carried out by his contemporaries and successors. Buffon. First among these was Buffon, born 1707, died 1788, a French savant who, Osborn says, was the naturalist founder of the modern applied forms of the evolutionary theory. Buffon lived in a time when to express one's views along lines not deemed orthodox by ecclesiastical authority might invite serious annoyance or even persecution, and he was not of the stuff of which martyrs are made. To this may have been due his apparent wavering between special creation and evolution. Buffon's teaching may be briefly summarized thus. The chief factor in the mutation of species, quote, was the direct influence of environment in the modification of the structure of animals and plants, and the conservation of these modifications through heredity. End quote. The transmission of these acquired characters, however, is nowhere expressly stated by Buffon, but is certainly implied. Packard tells us that Buffon was not an original investigator, leaving no technical papers nor memoirs, but was a brilliant writer and a popularizer of science. His voluminous works express not only the evolutionary factor which he advanced, but ideas on the influence of climate on various races of men, the formation of new varieties of animals through human intervention, artificial selection, and the same results produced by nature through geographical migrations. Thus he understood the significance of isolation, although he did not expressly state it. Buffon did, however, record his views on the struggle for existence to prevent overcrowding, and thus to maintain the balance of nature. Herein he anticipates Malthus, whose work on human population later proved to be so great a stimulus to Darwin and Wallace. Buffon also speaks of the elimination of the least perfected species, and the contest between the fecundity of certain species and their constant destruction. Erasmus Darwin, born 1731, died 1802, was a country physician, a naturalist, and a poet of some distinction. He was the grandfather of Charles Darwin, to whom he seems to have transmitted the love of science and desire to know what could be learned concerning the deeper problems of life. Erasmus' direct influence upon his grandson, however, through the medium of his writings, seems to have been slight. The elder Darwin's theory as to the cause of evolution differed from that of Buffon in that he did not emphasize the influence of the directly acting environment, but believed that modifications spring from within by reactions of the organism, an idea more nearly comparable to that of Lamarck, but going even further than the latter's in being applied to plants as well as to animals. Thus he says, quote, "All animals undergo transformations which are in part produced by their own exertions, in response to pleasures and pains, and many of these acquired forms or propensities are transmitted to their posterity." End quote. This is the first time that the factor of the inheritance of acquired characters is clearly stated. Erasmus Darwin emphasizes the fierce struggle for existence which, he says, checks the rapid increase of life and thus is beneficial in the end. Hence he just misses the idea of survival of the fittest in connection with the struggle for existence. Dr. Darwin believed that powers of development were implanted within the original organism by the Creator, and that these in turn gave rise to the various adaptations without further divine intervention. He does not, however, believe in the inherent perfecting principle of Aristotle, but holds that the power of improvement rests with the animal's own efforts, and that the result of these efforts upon the creature's body can be transmitted to its offspring. Two distinctly modern conceptions are attributed to Erasmus Darwin: the statement of the evolution of all forms of life from a single protoplasmic mass, or, as he himself expresses it, from a single filament, capable of being excited into action by various kinds of stimuli, and the idea of the immensity of time, millions of years, required for the evolution of the organic world. End of Chapter 1, History of Evolution, Part 1. Recording by Lucretia B. Chapter 1 of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Chapter 1, History of Evolution, Part 2. Lamarck, born 1744, died 1829, was one of the most remarkable as well as one of the most pathetic figures in evolutionary history. A man of brilliant attainments, yet because of ideas which failed to meet the approval of the influential Cuvier, and because of his own blindness and poverty, he suffered social ostracism for what he thought to be the truth, and only received a tardy appreciation years after his death. The work of Lamarck as a philosophical zoologist parallels that of Erasmus Darwin so closely that it would almost seem as though the latter must have been the inspiration, if not the source, of Lamarck's thought. The possibility of this, however, is stoutly denied by Packard, who states emphatically that Lamarck was in no way indebted to Erasmus Darwin for any hints or ideas. Charles Darwin notes the similarity when he says, "It is curious how largely my grandfather, Dr. Erasmus Darwin, anticipated the views and erroneous grounds of opinion of Lamarck. It is the latter's Philosophie zoologique, published in 1809, which parallels Darwin's Zoonomia most closely, and contains the final statement of the author upon his evolutionary hypothesis, which was never developed beyond this point. Lamarck's theory of the evolution of animals was not that change was the result of the direct action of the environment, but that the latter acted on internal structure through the nervous system. Herein he agrees with Erasmus Darwin. Darwin went still further, however, since he thought that plants could also react to environmental stimulus through their sensibility. Lamarck, on the other hand, thought that plants were directly influenced by their surrounding conditions, so that, while agreeing with the elder Darwin in regard to animal evolution, his views on that of plants were in accord with those of Buffon. Either theory, however, depending as it does upon the changes wrought upon the individual, implies the inheritance of acquired characters, a thing which Lamarck assumed and never tried to prove. And as we shall see, the whole fabric of his theory rests upon the possibility or impossibility of this one point: whether the new characteristics impressed upon the organism during its lifetime can be transmitted to its young. Among the notable contributions of Lamarck to the science which concerns itself with living things were the term biology, a word coined simultaneously by Treviranus, whereby that science is now designated; his conception that species vary under changing conditions; the theory of the fundamental unity in the animal kingdom; and the idea of a progressive and perfecting development of animals and plants. This last, he says, is due to a certain order originally imposed upon nature by its author, which is manifest in the successive development of life. He denied, however, any idea of a perfecting principle in nature. In diametric opposition to Cuvier's teaching, Lamarck denied all catastrophes in geology or sudden changes in organic life, but was an advocate of the uniformitarian school, which believed in gradual change without any sharp breaks either in the continuity of terrestrial history or in the evolution of animals and plants. All that is needed to effect any evolutionary change, he held, is matter, space, and time. Lamarck also gives us the first real conception of the tree of life, or phylogeny. All classifications before his time had been simply a numerical succession of zoological groups, arranged one above another. In Lamarck's earliest attempt, published in 1802, he uses the vertical scale, which Osborn compares to a fir tree with central stem and radiating branches. But in 1809 he had arrived at the true conception of life as a tree branching from the roots into larger and smaller stems. In a later attempt in 1815, his tree is still branching, and he has realized the apparent isolation of the vertebrates, which present-day authorities are at a loss to connect with their invertebrate ancestry. With the development of his tree of life came the conception of extinction of past races of animals and plants. This Lamarck clearly understood as applied to the lower grades of organisms, but he could not imagine how so perfect a being as a mastodon could possibly become extinct except through the interference of mankind. He thought that as the lower forms evolved into higher or became extinct, they were replaced by the increasing creation of new beings. The persistence of certain primitive types was perplexing, but was explained by the apparent fact that in their own peculiar environment there had been but little change, and changing conditions were a sine qua non of evolution. In summing up Lamarck's work, one must account for the smallness of his influence upon evolutionary thought, for he had but a single follower in all France. Locally, Cuvier's prestige and his own blindness, which rendered his retirement necessary, were largely responsible. As Osborne says, quote, Lamarck, as a naturalist, exhibited exceptional powers of definition and description, while in his philosophical writings upon evolution, his speculation far outran his observations, and his theory suffered from the absurd illustrations which he brought forward in support of it. His critics spread the impression that he believed animals acquired new organs simply by wishing for them. His really sound speculation in zoology was also injured by his earlier and thoroughly worthless speculation in chemistry and other branches of science. Another marked defect was that Lamarck was completely carried away with the belief that his theory of the transmission of acquired characters was adequate to explain all the phenomena. He did not, like his contemporaries, Erasmus Darwin and Goethe, perceive and point out that certain problems in the origin of adaptations were still left wholly untouched and unsolved. His arguments are, in most cases, not inductive but deductive, and are frequently found not to support his law but to postulate it. End quote. Lamarck's place among scientists is not yet really established. He was undoubtedly a naturalist of the first rank, but as an evolutionist, although he later gained, especially in America, a large following, he cannot yet be placed, as the crucial point in his whole theory is still sub judice. E. Geoffroy Saint-Hilaire, born 1772, died 1844, another Frenchman and a contemporary of Lamarck, was not, however, his follower, but rather a disciple of Buffon, going back to the old factor of direct environmental influence as the sole cause of evolution. He anticipated a much later writer, De Vries, by teaching that transmutation, or the change from one species to another, might be by sudden leaps or saltations, a theory which was in direct opposition to Lamarck's belief in the slow deliberation of the process. Saint-Hilaire believed, however, that these leaps took place not in the adult but in the embryo. Quote, hence the underlying causes of sudden transformation were profound changes induced in the egg by external influences, accidents, as it were, regulated by law. End quote. As a result of this belief in evolution per saltum, it was not necessary to show the existence of intermediate forms, those perplexing missing links in the phyletic series, and it also removed the objection that interbreeding would speedily swamp new characters according to the law of averages, because physiological isolation, which prevents indiscriminate mating, would thus be secured. While Saint-Hilaire can with justice be called one of the founders of evolution, his influence in its development was not as great as that of his contemporaries. Charles Darwin, born 1809, died 1882, is beyond doubt the foremost figure in evolutionary history, not so much for the originality of his ideas, for they had already been largely anticipated by his predecessors, but because of the abundant proof with which his statements were accompanied, proof based upon thousands of careful observations extending over a long term of years. Darwin's wonderful development and application of the inductive method, making theory everywhere subservient to fact, and the clarity and simplicity of his exposition made his arguments irresistible, and accomplished what none of those who went before him could possibly have done: the wide acceptance of his doctrine, not alone by biologists, but by thinking men in general. While some of the so-called Darwinian factors, notably that known as sexual selection, are to a certain extent discredited in the light of our greater knowledge, the fact that Darwin's work paved the way for the general acceptance of the truth of evolution puts him at the forefront of the masterminds whose contributions to the science made this acceptance possible. The story of Darwin's life is well known. Born on the 12th of February, 1809, this emancipator of human minds from the shackles of slavery to tradition saw the light upon the very day that ushered in the life of Abraham Lincoln, the emancipator of human bodies from a no more real physical bondage. Darwin studied first at Edinburgh, but finding medicine unsuited to his tastes, entered Christ's College, Cambridge, as a candidate for the Church. His love of nature, however, dominated all other interests, and shortly after graduation an opportunity came to join the ship Beagle as naturalist in a voyage of exploration around the world. The 5 years spent upon this memorable journey, the narrative of which is so admirably set forth in the book A Naturalist's Voyage Around the World, resulted in the accumulation of the first of Darwin's great series of observations, the final decision to devote his life to zoological research, and the beginning of that illness which made him a lifelong invalid. This last factor necessitated a retired life, and thus proved of indirect benefit, as it enabled him to accomplish the immense amount of work which he did without being impeded by the distractions of a public career. A brief chronology of Darwin's scientific and literary work, which had for its climax the appearance of the epoch-making Origin of Species, is as follows: 1831 to 1836, Voyage of the Beagle. 1837, beginning of the notebook for the collection of facts bearing upon variation in animals and plants. 1838, read Malthus on population, and conceived the idea of natural selection as the result of the struggle for existence. Footnote: in this essay, Malthus shows that while the normal rate of human increase is according to a geometric ratio, space and the available food supply remain constant. Hence, it follows that some very active agent or agents must be at work to keep down the surplus population. Otherwise, neither terrestrial space nor food would suffice for their support in a relatively brief period of time. End footnote. 1842. Allowed himself briefly to set down his views for the first time. 1844. Wrote a more elaborate statement of his progress, which sets forth the main arguments which were later developed in The Origin of the Species. These embrace the three principal factors of his theory: the struggle for existence, variation, and natural selection of those variations which conform with environmental need. He also developed the idea of sexual selection, and attached more weight to the influence of external conditions and the inheritance of acquired characters than in the edition of the Origin of Species in 1859. This statement, amounting to 230 pages, was set apart, together with the sum of £400 to £500, with which to publish it in case of the author's sudden death. 1856. Sent Sir Joseph Hooker, the botanist, his manuscript. He had now abandoned entirely the factors of Buffon and Lamarck, and placed the utmost reliance upon the efficiency of natural selection as the prime factor in evolution. 1858. Received from a young man, Alfred Russel Wallace, born 1822, died 1913, a brief essay embodying a theory of evolution of which, as in Darwin's case, natural selection was the prime factor. And strangely enough, it was again Malthus' essay, read by Wallace 12 years before, which stimulated the conception. At first, Darwin was inclined, out of chivalrous friendship for the young man, to suppress his own laboriously elaborated work and to publish Wallace's to the world. Fortunately, the good counsels of his friends Hooker and Lyell prevailed, and as a result a joint paper setting forth the views of both authors was read before the Linnean Society of London, July 1st, 1858. Then Darwin set to work to write the Origin of Species, which was prepared in a few months and published in 1859. In the first edition of the book, he takes a somewhat less decided view of the efficacy of natural selection, believing it to have been, however, the principal but not the exclusive agent in evolution. Selection, he says, works upon chance variations, but by this he does not mean fortuitous in the modern sense, but occurring according to laws of which we have no knowledge. As a result of his extensive observations upon domestic animals, Darwin gradually receded from his extreme views concerning the efficacy of natural selection, and began to lean more and more toward Lamarck's teaching. In 1876, in a letter to Moritz Wagner, he says, quote, "When I wrote the Origin, I could find little good evidence of the direct action of the environment. Now there is a large body of evidence, and your case of the Saturnia is one of the most remarkable of which I have heard." End quote. In the sixth edition of The Origin of Species, in 1880, Darwin gave the final expression of his belief in the following illuminating sentence, quote, "This modification of species has been effected chiefly through the natural selection of numerous, successive, slight, favorable variations, aided in an important manner by the inherited effects of the use and disuse of parts, Lamarckian factor, and in an unimportant manner, that is, in relation to adaptive structures, whether past or present, by the direct action of external conditions, Buffonian factor, and by the variations which seem to us in our ignorance to arise spontaneously." End quote. Owing to Darwin's invalidism and the gentleness of his character, he left to others the championing of his cause, his chief exponent being Thomas Henry Huxley, born 1825, died 1895, himself a man of remarkable learning, forcible logic, and one of the great masters of written and spoken English, in every way admirably equipped to fight Darwin's battles for him. Huxley's contribution to biology is, therefore, not alone his many admirable research productions in recent and fossil anatomy, but his service as an educator of the public in commanding the general acceptance of Darwin's teaching. Since Darwin's day, evolution has been more and more generally accepted, until now in the minds of thinking men there is no doubt that it is the only logical way whereby the creation can be interpreted and understood. We are not so sure, however, as to the modus operandi, but we may rest assured that the process has been in accordance with great natural laws, some of which are as yet unknown, perhaps unknowable. Quote, "The world has been evolved, not created. It has arisen little by little from a small beginning, and has increased through the activity of the elemental forces embodied in itself, and so has rather grown than suddenly come into being at an almighty word. What a sublime idea of the infinite might of the great architect, the cause of all causes, the father of all fathers, the ens entium. For if we could compare the infinite, it would surely require a greater infinite to cause the causes of effects than to produce the effects themselves. All that happens in the world depends on the forces that prevail in it, and results according to law. But where these forces and their substratum, matter, come from, we know not. And here we have room for faith." End quote. Erasmus Darwin, as interpreted by Weismann. End of Chapter 1, History of Evolution, Part 2. Recording by Lucretia B.
Chapter 2 of Organic Evolution. This is a LibriVox recording, and all LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Don Evans. Organic Evolution by Richard Swann LULL. Chapter 2. The Organic Kingdom. The physical basis of life. The contrast between living and lifeless matter. The material universe is composed of a number of substances known to the chemists as elements, which rarely exist in a free, uncombined state, but usually in more or less intricate combinations, each element with one or more others. The same elemental substances make up the minerals and rocks, the water and atmosphere, on the one hand, and the bodily substance of all animals and plants on the other. The only difference being in the unique character and peculiar complexity of the chemical compounds we call organic, and not in the primal substances of which they are composed. The contrast between matter and the living and lifeless states is largely due to the presence in the former of a peculiar chemical compound known as a protein or albuminous substance, a highly complex union of many atoms of such common elements as carbon, hydrogen, oxygen, nitrogen, sulfur, and several others. Combined with the proteins are other organic compounds which, together with some water and certain salts, make up the highly organized substance protoplasm, of which all living things are composed. Therefore, in its last analysis, the contrast between the mineral kingdom on the one hand and the organic kingdom on the other depends not upon the power of movement, nor of producing heat or light, nor of growth, nor of containing certain elements to the exclusion of the others, but merely upon the presence of protoplasm with its component protein. Huxley has called this protoplasm, out of which all living beings are made, the "physical basis of life," because it constitutes the tangible substance which forms in itself, or as a result of its activity, the entire structure of any plant or animal. It is therefore the fundamental building material of the organism. Protoplasm may be studied from 3 points of view. its chemical makeup, its physical characteristics, and the peculiar physiological or functional attributes which it possesses, and the sum of which constitutes that phenomenon we call life. All of the qualities manifested by an animal or plant, however high its degree of organization, are only the qualities or their combination exhibited by protoplasm itself. There is no biologic proof of the presence of any vital spark, or other life manifestation in addition to these characteristics of the physical basis of life. Chemical characteristics of protoplasm. Chemists have resolved protoplasm into some 16 different elements. These are carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, chlorine, fluorine, silicon, sodium, potassium, lithium, calcium, magnesium, iron, and manganese. Occasionally, possibly abnormally, copper and lead have been found in protoplasm. The former, however, exists regularly in the blood of certain lower animals. Of these elements, only the first 4 are in relatively large quantities. The others, while apparently vitally important, are proportionally very minute in amount. Protoplasm has been subjected to repeated chemical analysis, but the question arises whether anyone has succeeded even in approximating the actual combination of the elements in the living material. For the most refined methods break down the high complexity of the protoplasm itself, leaving us simply the debris for actual examination. A very fair estimate of the amount and proportions of the elements may be learned by studying that which enters into the organism in the form of food and the waste resulting from its vital activities. The chemical compounds which compose protoplasm are conveniently grouped as organic and inorganic. The organic ones are, first, the albuminous substances or proteins already referred to, containing carbon, hydrogen, oxygen, nitrogen, and sulfur, united into molecules of high complexity, the number of individual atoms being numbered by the hundreds. Protein has various forms, such as albumin, globulin, fibrin, plastine, and nuclein. Some of these, however, may be secondary products not resident as such in the actual living protoplasm. Briefly, the proteins are the nitrogen-containing compounds. An organism also contains 2 other groups of non-nitrogenous organic compounds known respectively as the carbohydrates or starches and sugars, and the hydrocarbons or fats and oils. The former are composed of carbon, hydrogen, and oxygen, the ratio of 2 atoms of hydrogen to 1 of oxygen, as in a molecule of water, being always maintained. The carbon atoms are always either 6 or some multiple of 6 in number. The hydrocarbons, as the name implies, contain mainly hydrogen and carbon, and if oxygen be present, it is in relatively small proportion. These non-nitrogenous organic compounds have for their chief function the liberation of energy, whereas the proteins are the chief building material of the body, but may under certain circumstances be energy liberating also. Associated with the proteins in the protoplasm are various salts, such as potassium, sodium, and calcium phosphate, potassium and sodium chloride, magnesium sulfate, and certain other similar substances of doubtful significance. In addition to these, protoplasm contains a varying proportion of water, known as the water of organization, which aids its fluidity. Physical properties of protoplasm. No matter what its source may be, whether plant or animal, protoplasm is a singularly uniform substance in general appearance. It may be described as grayish, viscid, semi-transparent, and semi-fluid. The grayish color is due to the presence of numerous granules in its substance. Where these are lacking, it is hyaline or colorless and transparent. The granules may be in part secondary products in the protoplasm derived from the constant chemical changes which it is undergoing and which will shortly be described. In addition to the granules, the protoplasm may contain vacuoles, or spaces filled with a fluid, possibly containing food in process of digestion, possibly waste matters about to be discharged. Among the protoplasmic granules is a group differing from the first. These, when the protoplasm has been subject to a certain staining process, absorb the stain to a greater degree than the surrounding protoplasm. On account of their greater affinity for coloring matters, the substance of these granules has been called chromatin, and this, when concentrated into one or more bodies, forms the nucleus of the mass. The remaining protoplasm, when organized into the anatomical unit of structure known as a cell, is called the cytoplasm. Of these two protoplasmic substances, the nucleus and cytoplasm, the former seems to be of more vital moment to the cell, for the cytoplasm alone, separated from the nucleus, is unable to continue its existence. The nucleus regulates the vital processes of the cell, has impressed upon it the specific characters of the organism, and thus serves as the vehicle of inheritance. Hence, in the present state of our knowledge, the peculiar chromatin granules must be regarded as an integral part, perhaps even the most essentially and primarily important portion of the living substance. The most powerful microscope fails to resolve protoplasm into its ultimate parts. Biologists, therefore, do not agree when the minute structure is discussed, some supposing it to consist of tiny granules embedded in a common matrix, that's the granular theory, others regarding it as consisting of a tangle of delicate threads known as fibrillae, that's the filar theory, and containing the more fluid portions much as a sponge does water. Such a conception as the latter, however, is at variance with the known fluidity of the protoplasm as a whole, for while a sponge may contract and change its shape, it can not flow. On the other hand, to suppose the fibers to be fluid is also open to objection, since one fluid can not form a network supporting another. All of this simply emphasizes the subtle character of this wonderful life substance, so complex chemically that it is apparently unanalyzable, and of so minute a structure as to be ultramicroscopic. And with special lighting devices, microscopes have been made to resolve entities as small as 1/1,000,000th of an inch. Physiological properties of protoplasm. The physiological or functional properties of protoplasm are several, most of which are peculiar to it alone. These properties are best understood when one realizes that protoplasm is always, in both animals and plants, in the form of a cell, a single one of which may constitute the entire organism, protozoa, protophyta, or the latter may be composed of many cells varying in form and function. The physiological properties of protoplasm are, therefore, with some exceptions, those of the entire cell. Of these, the most conspicuous, perhaps, is the power of movement. In the plant cell, which generally has a rigid limiting wall, this is usually merely a streaming of the contained protoplasm. The animal cell, on the contrary, is rarely thus limited, so that the cell as a whole may change its shape indefinitely, as in the amoeboid movements manifested by certain of the lowest forms or by the white blood corpuscles in a man, or it may merely shorten in one dimension, as in one of the component cells of a human muscle. Another property is that of sensation or sensitivity, the power to feel, which is manifested by movement, proving that the cell possesses irritability. While the resultant movement may be disproportionate to the stimulus, they generally bear a certain ratio to each other, and up to a given point, an increased stimulus will cause a correspondingly greater movement. Two other closely correlated characteristics are, first, conductivity, by which stimuli are transmitted throughout the mass of the protoplasm. Touching one part of the cell may give rise to movement in a remote area. This conductivity is thus the means of communication between one portion and another. The second of these characteristics is coordination, which gives rise to purposeful movements such as the harmonious motion of the cilia or locomotor organs of a protozoan. Coordination would be impossible without conductivity, and these two, together with irritability, constitute the animal functions in contrast to the vegetal ones which will be next described. Vegetal functions of protoplasm. Of the vegetal functions, the first vital phenomenon is metabolism, divided into two aspects, of which one is constructive metabolism or anabolism. That's Greek to throw up, the power on the part of the cell to utilize or assimilate food, briefly, to make it over into protoplasm similar to its own. The other is destructive metabolism or catabolism, Greek there to throw down, the disassimilation or breaking down of protoplasm into simpler compounds. This is always accompanied by the liberation of energy, which may take the form of the mechanical motion already referred to, or of heat, light, or electricity. If the anabolism, which represents the cell's income, exceeds the catabolism or expenditure, the result is growth. If the reverse be true, diminution of size follows. Growth is accomplished not as a mineral crystal grows by the addition of material to its outer surface or apposition, but by a much more intimate process known as intussusception, that is Latin to take up within, whereby the nutrient material is disseminated all through the substance of the cell. With a small cell, growth occurs up to an optimum of size for the organism, when, under ordinary conditions, it ceases to increase in size, but may increase in numbers, usually by the simple process of dividing into two. A partial explanation of this is that the organism's ability to get food depends upon its superficial area, which increases with the square of its diameter, whereas its need of food depends upon its bulk, which increases with the cube. Hence, while in the minute cell the surface will suffice for its needs, as the cell grows it wants outrun its absorptive ability until an equilibrium is reached, beyond which increase in bulk can only be gained by a large increase in surface, which is most readily accomplished in a simple geometrical form by dividing it into two. This division constitutes, therefore, a sort of discontinuous growth, and forms one of the most essential of all protoplasmic attributes, the power of reproduction. While the entity of the parent cell is thus lost, its life and its substance still exist in its offspring. Hence it cannot be said to have died, and the offspring will in turn pass on their life and substance to their offspring, and so on as long as the line endures. In many lower forms of life, this potential immortality, which is a further characteristic of protoplasm, is true of the entire organism. In higher forms, where a certain group of cells only is set apart for reproduction, they alone possess this attribute, the remaining tissues of the body dying when the individual span of life is complete. This protoplasm, unanalyzable, ultramicroscopic, endowed with all of the qualities of the highest animal or plant, metabolism, movement, irritability, adaptability, growth, reproduction, and such immortality as has sufficed to continue unbroken the slender chain of existence from the beginning of life on earth, and will, so long as life endures, is one of the greatest wonders of the world. Simple life processes as illustrated by Paramecium. Many of the life processes of protoplasm have been summarized in the foregoing sentence, but a clearer conception of them may be gained by a concrete example, such for instance as the protozoan Paramecium, the so-called slipper animalcule. This organism is chosen as it is relatively large and easily procured from stagnant pond water and like places. Professor Woodruff, through having bred more than 5,000 generations in the Yale laboratory, has made it virtually a domestic animal. Structure. Paramecia are minute unicellular forms just on the verge of invisibility, for when a drop of water containing them is held up to the light, they can be seen with the naked eye as tiny white motes moving in every direction. Under a microscope, Paramecium is seen to be an elongated body tapering toward either end, with the forward extremity somewhat rounded. On one side there is a pronounced depression, the oral groove, at the depth of which is a short tubular gullet leading into the substance of the cell. Externally, the animal is uniformly clothed with hair-like structures known as cilia, which, by bending swiftly in one direction, followed by a slow recovery, cause it to progress. Cilia also line the mouth depression and the gullet. Here their function is not locomotor, but prehensile, that is, to aid in securing food. Within, Paramecium shows several important structures embedded in the granular protoplasmic mass. Of these, the most conspicuous are the food vacuoles, spherical spaces containing water, food particles, and certain digestive ferments. These food vacuoles are temporary stomachs, having their origin at the end of the gullet, where they are formed merely by forcing a drop of water with its contained food particles into the protoplasm. Other structures are the contractile or pulsating vacuoles, one at either end of the body, with a central cavity and radiating spaces extending into the surrounding protoplasm. The radial canals absorb moisture and waste products from the cell until they are distended, and then discharge them into the central vacuole, the latter dilating as the radial spaces diminish. When the central cavity is full, it forcibly contracts, voiding its contents through the ruptured cell surface into the surrounding medium. The two pulsating vacuoles contract rhythmically and alternately. Within the mass of the cell, at about its center, lies the essential nucleus, a compound structure composed of chromatin and consisting of a greater meganucleus and a lesser micronucleus. The latter is, however, the more important in reproduction, while the former has to do with metabolism. Locomotion. The physiological processes seen in Paramecium are essentially like those of the highest forms, and may be conveniently grouped under two headings: the animal functions of locomotion and response to stimuli, and the vegetal functions of nutrition, growth, and reproduction. Locomotion is effected by movements of the cilia, which bend sharply toward the rear of the animal and thus sweep the creature forward. Then they relax, and the relative slowness of this movement offers comparatively little resistance to the water and hence does not appreciably check the creature's way. Paramecium swims rapidly forward, rotating slightly on its long axis as it goes, and seems to make purposeful movements. A careful study of its behavior, however, makes it evident that its movements are governed by certain fixed rules, so that they may be predicted in advance with more or less certainty. If, in its onward course, Paramecium strikes any obstacle, the cilia reverse their action, and the animal moves backward a certain distance. It then reverses once more, changes its direction somewhat toward the ventral side or that which bears the mouth, goes ahead again, and may clear or once more strike the obstacle according to chance. But its movements are not all in one plane of space because of the rotation upon its axis, which causes the ventral side to face in any direction at the beginning of its forward motion, to the right or left or up or down, as the case may be, and thus increases severalfold the chances of avoiding the object. Nutrition has for its objects the increase of bodily substance or growth, and the replacement of that which is consumed in the production of energy. It is not a simple process even in Paramecium, for it consists of a number of distinct steps, of which the first is ingestion, the securing of food. This is accomplished by means of the cilia lining the mouth depression and gullet, which sweep in any nutrient materials such as the bacteria or other organic particles in the surrounding water. These are forced into the protoplasm at the bottom of the gullet, which, giving way before their entrance, forms a food vacuole. Into this there comes the digestive fluid, whereby the nutrient material is extracted from the food, constituting the step known as digestion. The nutrient material is then absorbed from the vacuole into the adjacent protoplasm and is assimilated, anabolism, in the manner above described. During the process of digestion and absorption, the food vacuole has been carried in the streaming protoplasm first toward the posterior end of the body, then forward along the dorsal side to the anterior end, then backward past the mouth until it reaches an egestive area, not an actual aperture, but a region where the integument is easily ruptured, and here the food vacuole breaks forth into the surrounding medium, carrying the residue of contained water and the indigestible food refuse. This process is known as egestion, and the movement of the vacuole throughout the body for the distribution of the food corresponds to circulation in a higher form. Catabolism, or disassimilation, is continually in operation to produce all of the mechanical changes or movements which the organism undergoes. This energy is produced through an oxidizing or physiological burning of the protoplasm, the oxygen being derived from that dissolved in the surrounding water by the process of respiration. No special respiratory organ is present. The whole surface of the animal serves instead. This oxidizing of the protoplasm breaks it down into a number of simpler compounds, the reduction being accompanied by the liberation of energy. But there remains the effete material to be eliminated, and this is done by the process of excretion. The excretory products constitute the bodily waste in contradistinction to the food refuse which has never been properly a part of the animal's substance. They usually take three forms: carbonic acid gas, that is, CO2 or carbon dioxide, which is eliminated through the surface of the body and by contractile vacuoles; water excreted by the contractile vacuoles; and nitrogenous wastes, which are eliminated by the same mechanism in solution in the water. Reproduction in Paramecium is effected in the simplest possible manner by the transverse division of the cell, each half developing the parts which are lacking and reorganizing into a perfect animal. Previous to the division of the cell, however, the micronucleus has divided by a very complex process known as mitosis, that's Greek for thread, whereby the halving of the chromatin is done with the utmost nicety, so that not only does each daughter cell get its full quota of nuclein, but each tiny portion is equally divided between them. Thus generation after generation of Paramecium is produced, each undergoing its life cycle of youth, maturity, and reproduction. Conjugation. Occasionally, however, reproduction is preceded by a process known as conjugation. This is effected by the coming together of two individuals which form a temporary union by their ventral sides, but without actual fusion of substance. In Paramecium caudatum, the meganucleus then breaks up into small bodies and disappears. The micronucleus, on the other hand, divides into two daughter micronuclei, each of which divides again. Two of these disappear, and the remaining ones are known respectively as the stationary and active pronuclei. Each active pronucleus then migrates over into the other Paramecium, where it unites with the latter's stationary pronucleus to form a new nuclear body, which consists of equal portions of nuclein from each conjugating cell. The animals then separate and each nucleus divides and forms new micro and meganuclei. The chief purpose of this conjugation would seem to be biparental inheritance, to increase the range of variation and hence adaptability by combining in the offspring the characteristics and experiences of two more or less remote ancestral lines. Other explanations have been offered which may or may not be true, but the almost universal occurrence of conjugation points at any rate to the fact that it fulfills some very vital function in organic economy. Food supply of organisms. The question naturally arises as to the source of the highly complex compounds which form the bulk of protoplasm, for clearly they do not exist as such in the mineral kingdom, nor can an animal manufacture them. Plants, therefore, must be the constructive chemists of nature, although they can not utilize inorganic matter in its elemental condition. Having given, however, water, carbonic acid gas, and certain nitrogenous compounds comparable to ammonia, the green or chlorophyll-bearing plant, in the presence of sunlight, the ultimate source of all organic energy, can construct the proteins, sugars, fats, in fact all the complex food materials necessary for the sustenance of the animal. The animal itself, on the other hand, is limited in its constructive power, and is mainly destructive. Its only source for the highly necessary nitrogen is the proteins, which it must have ready-made, or starve. All it can do is to modify the form of the material somewhat and transmute plant protoplasm into animal. Huxley, in his address on the physical basis of life, delivered in 1868, summarizes the interrelation of animal and plant protoplasm, emphasizing first of all the oneness of the physical basis of life. Think, he says, of the microscopic fungus, a mere infinitesimal ovoid particle which finds space and duration enough to multiply into countless millions in the body of a living fly, and then of the wealth of foliage, the luxuriance of flower and fruit which lies between this bald sketch of a plant and the giant pine of California, towering to the dimensions of a cathedral spire, or the Indian fig which covers acres with its profound shadow, and endures while nations and empires come and go around its vast circumference. Or, turning to the other half of the world of life, picture to yourselves the great finner whale, hugest of beasts that live, or have lived, disporting his 80 or 90 feet of bone, muscle, and blubber, with easy roll among waves in which the stoutest ship that ever left dockyard would flounder hopelessly (hardly true in these days of giant liners), and contrast him with the invisible animalcules, mere gelatinous specks, multitudes of which could in fact dance upon the point of a needle with the same ease as the angels of the schoolmen could, in imagination. With these images before your minds, you may well ask, what community of form or structure is there between the animalcule and the whale, or between the fungus and the fig tree, and a fortiori between all four?" Unquote. Huxley speaks further of man's power of assimilating the dead protoplasm of any animal or plant, and thus transforming it into his own living substance. He says, "Hence it appears to be a matter of no great moment what animal or what plant I lay under contribution for protoplasm, and the fact speaks volumes for the general identity of that substance in all living beings. I share this catholicity of assimilation with other animals, all of which, so far as we know, could thrive equally well on the protoplasm of any of their fellows, or of any plant. But here the assimilative powers of the animal would cease. A solution of smelling salts in water, with an infinitesimal proportion of some other saline matters, contains all the elementary bodies which enter into the composition of protoplasm. But, as I need hardly say, a hogshead of that fluid would not keep a hungry man from starving, nor would it save any animal from a like fate. An animal cannot make protoplasm, but must take it ready-made from some other animal or some plant, the animal's highest feat of constructive chemistry being to convert dead protoplasm into that living matter of life which is appropriate to itself. Therefore, in seeking for the origin of protoplasm, we must eventually turn to the vegetable world. A fluid containing carbonic acid, water, and nitrogenous salts, which offers such a Barmecide feast to the animal, is a table richly spread to multitudes of plants, and with a due supply of only such materials, many a plant will not only maintain itself in vigor, but grow and multiply until it has increased a millionfold, or a millionfold, the quantity of protoplasm which it originally possessed, in this way building up the matter of life to an indefinite extent from the common matter of the universe. Thus the animal can only raise the complex substance of dead protoplasm to the higher power, as one may say of living protoplasm, while the plant can raise the less complex substances, carbonic acid, water, and nitrogenous salts, to the same stage of living protoplasm, if not to the same level. But the plant also has its limitations. A plant supplied with pure carbon, hydrogen, oxygen, and nitrogen, phosphorus, sulfur, and the like, would as infallibly die as the animal in his bath of smelling salts, though it would be surrounded by all the constituents of protoplasm." Unquote. End of chapter 2. Recording by Don Evans. www.lazuli.com.
Chapter 3 of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Chapter 3. Chapter 3. Classification of Organisms. Kinds of classification. Animals, or plants, may be grouped together for convenience of study in one of two ways. They may be classified taxonomically, zoologically or botanically, according to actual blood relationships, or from the standpoint of their life conditions. The latter classification may be called binomic, i.e., in accordance with the laws of life. The adaptive response on the part of two unrelated organisms to similar environmental conditions may give rise to convergences, wherein organisms come to resemble each other so closely that they have sometimes been actually classed together. The distinction between convergent and homogeneous, i.e., of the same race, organisms, is often a matter of extreme difficulty. When the classification is based upon living organisms only, errors are apt to occur, for groups of animals which today stand entirely isolated are shown to be related when their fossil ancestry is known. Zoological classification depends, therefore, in a measure upon paleontology or the study of ancient life, while binomic classification is largely a recent science. Zoological classification. As in a military organization, armies are divided into smaller and smaller subdivisions, brigades, regiments, battalions, and companies. So the organic world is divided into corresponding groups which, while increasing in number, lessen in importance as one descends the scale. An understanding of these divisions is necessary to our work. Kingdoms and subkingdoms. The organic world is made up of two types of organisms, animals and plants. The first characterized in general by a more active sentient life, the others passive, lacking in muscular and nervous systems, almost inert. These two groups of organisms are known as kingdoms, and constitute the first subdivision of the world of life. The kingdoms are in turn divided into subkingdoms, though here there is some difference of usage. These subkingdoms are comparable in that each is made up of unicellular organisms on the one hand, protozoa or protophyta, as the case may be, and multicellular organisms on the other. To the latter, the zoologists have given the name metazoa, but there is no equivalent term in general usage applied to the plants. Phyla. Subkingdoms, in turn, are divided into phyla, or types. Both terms are objectionable, as each has more than one meaning, but the term phylum is the one in general use in this sense. The protozoa constitute but one phylum, while of the metazoa there are at least 11 such groups of forms, as for instance the mollusks, arthropods, and vertebrates, each separated from the others by very distinctive characteristics, in that their ground plan of structure differs widely in each case. Thus, the mollusks have a soft, unsegmented body with no trace of locomotor skeleton, while the arthropods and vertebrates are both segmented and possess locomotive hard parts, but with the distinction that in the arthropods the skeleton is external, while in the vertebrates it is principally internal, the body being stiffened longitudinally by an axis known as the vertebral column. Classes and families. Phyla are divided into classes, such as the fishes, reptiles, birds, and mammals among vertebrates, and those in turn into families, genera, species, and varieties. Extremists in classification use the prefixes sub or super to signify groups somewhat more or less restricted than the unqualified name would imply. Thus a class may include subclasses, and these in turn superfamilies, families, and subfamilies before the genera are reached. Genera, species, and varieties. The chief object of our study being the origin of species, an adequate conception of a species is necessary. While biologists have not yet succeeded in arriving at a unanimity of opinion as to just what constitutes a species, the general conception of a kind of animal or plant to which a definite name has been given, such as a red fox, timber wolf, coyote, or jackal, just about expresses the idea. A species, therefore, is a group of individual animals or plants resembling each other very closely, not only in broad features, but in minute detail as well. In general, they are such as can breed together and produce fertile offspring, which in turn may reproduce. This was Huxley's great test of a species, but does not always hold true. The two species of camel, Camelus dromedarius and Camelus bactrianus, will breed together, and the llama, Auchenia glama, will breed with the alpaca, Auchenia pacos, and the offspring are fertile. This is also true of several species of deer and of certain of the bovidae, such as the zebu, Bos indicus, and the gayal, Bibos frontalis. Furthermore, the result of such a cross was bred to an American buffalo, Bison americanus, and produced a calf, the result of a triple alliance, not only of distinct species, but according to our present definition, of 3 distinct genera. Bartlett. Sometimes forms which are quite different, as certain snails, and which might well be considered different species, nevertheless grade into each other, if a sufficient series be found and placed in orderly sequence. The extremes would be species if the means of the series did not exist. As it is, they are varieties. Varieties may be arranged in gradational series, each differing from the next in very minute detail. Species do not so intergrade into each other. Were the annectant varieties blotted out by extinction, so that only the extremes of the series survived, the latter would then become separate species. Hence one rather poetic definition of species likens them to islands in a sea of death. All of the dog-like forms which were mentioned by way of illustration, with the exception of the fox, show specific differences, but anyone would at once see a great many important resemblances, which seem to imply a very close degree of relationship among them all. If they were bred together, however, the offspring would probably prove infertile, as in the case of the domestic mule, whose parents are the horse and ass. The various wolves and the jackal on the one hand, and the horse and ass on the other, belong in each case to the same genus, but to different species. This conception of genera and species was first clearly stated by Linnaeus, who gave to each animal and plant with which he was familiar a double name in Latin form, although often derived from the Greek or other languages. These names imply relationship, for the first is that of the genus to which the form belongs, while the second indicates its species. Thus the scientific name of the timber wolf is Canis lupus, of the coyote Canis latrans, of the jackal Canis aureus, but the red fox bears the name Vulpes vulgaris, showing it to be not only a separate species, but a different genus as well. All of these, however, are dog-like forms, and hence belong to the widespread family Canidae. This family, together with the cats, bears, weasels, and various other animals, is carnivorous, with teeth of a peculiar sort, and to all such forms Linnaeus gave the class name Ferae, of which the modern equivalent is Carnivora. To revert to the definition of species once more, Webster thus defines it: a more or less permanent group of existing things or beings, associated according to attributes or properties determined by scientific observation. In general, the idea of permanence is implied, but only while conditions remain the same. Changing conditions, either through the migration of the animal to a new home, or an actual change, climatic or otherwise, in the old one, will react upon the species and thus alter its characteristics. There may also be a gradual change in the organisms, in non-essential things in the course of time, even with practically unchanging conditions, especially where isolation of lines is established, as in the case of the various varieties and species of land snails in the radiating valleys in the islands of Tahiti, Crampton. A species has also been defined as a stage in the evolution of a race. The species has already been spoken of as an island, and the genus may be called an archipelago in a sea of death. Jordan and Kellogg. End of Chapter 3. Recording by Joy S. Grape. www.coffeewithleonardcohen.com.
Chapter 3, Part B, of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Chapter 3, Part B. Classification of Animals. Modified from Parker and Haswell. Animal Kingdom. Subkingdom Protozoa. Unicellular, solitary, or colonial organisms of minute size, without separate tissues, composed of cells. Phylum 1. Protozoa, with the characteristics of the subkingdom. Class 1. Sarcodina, without external cell wall, locomotor organs pseudopodia, frequently with a calcareous shell or a siliceous skeleton. Lobosa, with blunt or lobe-like pseudopodia, naked amoeba, or shelled arcella, etc. Marine and freshwater, sometimes parasitic. Foraminifera, calcareous shell, generally with numerous fine apertures. Pseudopodia fine, branching or anastomosing. Marine and freshwater. Radiolaria, siliceous shell, delicate, lace-like. Fine, ray-like pseudopodia with central axis. Marine. Class 2. Mastigophora. Body with limiting membrane. Locomotion by means of one or more whip-like flagella. Solitary or colonial. Some flagellate forms show certain plant-like characteristics, notably in the presence of chlorophyll, or leaf green. Thus they are variously claimed by both zoologists and botanists. Certain members of this group lie upon the frontier between the plant and animal kingdoms. Class 3. Infusoria. With limiting membrane. Locomotor organs, when present, numerous hair-like cilia, ciliata, as in Paramecium. Non-locomotor Suctoria possess tentacles terminating in adhesive knobs, etc., for securing food. Class 4. Sporozoa. Parasitic protozoa with complicated life histories. The young are generally reproduced in the form of spores. Locomotor organs are usually absent. Many human scourges, such as malaria, are caused by sporozoa. Subkingdom Metazoa. Multicellular animals with definite tissues composed of cells, along which there is division of labor. Reproduction by means of ova and spermatozoa, sexual, the rule, although asexual reproduction does occur. Phylum 1. Porifera. Sponges. Plant-like organisms, motionless, without tentacles, with a more or less complicated internal canal system and with inhalant and exhalant pores. simple or colonial. In the more complicated sponge stocks, the individuals can no longer be distinguished. Skeleton, when present, consisting of calcareous or siliceous spicules or of chitinous, horny, fibers, spongin, sometimes reinforced by siliceous spicules. Commercial sponges possess a chitinous skeleton without the supporting spicules. Phylum 2. Coelenterata. Hydroids, jellyfishes, coral polyps, etc. Radially symmetrical animals, generally with tentacles and stinging cells, with one internal cavity functioning both for circulation and the digestion of food. Class 1. Hydrozoa. Polyps with a simple internal cavity, either simple, hydra, or forming more or less complex colonies, hydroids, in which there is division of labor among the various individuals, zooids. The reproductive zooids take the form of medusoid buds, which may become detached from the colony as free-swimming medusae, jellyfish. Class 2. Scyphozoa. Coelenterids in which the medusae are large and dominant. There is no hydroid colony, but the medusae are generally derived from minute polyps known as scyphulae. Class 3. Actinozoa. Corals. Polyps with complicated internal cavities and with no free-swimming medusae. They may be either fleshy, sea anemones, or secrete a horny or calcareous skeleton, corals. Solitary or colonial, the latter sometimes becoming massive coral stocks, aggregates of which form extensive reefs or islands. Class 4. Ctenophora. Comb jellies. Pelagic coelenterids which progress by means of rows of comb-like swimming plates formed of fused cilia, more or less ovoid to band-like in shape, and generally provided with two tentacles which bear adhesive, instead of stinging, cells, never colonial and exclusively marine. Phylum 3. Platyhelminths. Flatworms. Bilaterally symmetrical animals, flattened dorsoventrally, the body cavity filled with a tissue called parenchyma. Digestive and other systems generally much branched. The free-swimming turbellaria have ciliated contractile bodies, while the parasitic forms are not ciliated as adults. Those of the latter which are of simple form are known as trematodes, while the elongated segmented tapeworms, without digestive system, are called cestoda. Phylum 4. Nemathelminths. Threadworms. Cylindrical, worm-shaped animals with a body cavity. Many are parasitic and may lose the intestinal canal. Phylum 5. Trochelminths. Wheel animalcules. Variously shaped organisms of minute size, sometimes sedentary, again swimming by means of ciliated bands which may resemble revolving wheels, hence rotifers. Phylum 6. Molluscoidea. Lamp shells and sea mosses. Attached, bilaterally symmetrical, unsegmented animals, with a crown of ciliated tentacles or spirally rolled arms. Class 1. Bryozoa. Sea mosses. Minute animals usually encased in chitinous tubes or cells, generally colonial and often resembling superficially a hydroid or an alga. Class 2. Brachiopoda. Lamp shells. Marine forms with a bivalve shell, thus resembling the true mollusks, clams and mussels. In the brachiopods, however, the shell valves are dorsal and ventral, whereas in the mollusks they are lateral. The mouth lies between two ciliated spiral arms which rest closely coiled within the shell. Numerous in geologic time, comparatively few living. Phylum 7. Ectenodermata. Spiny-skinned animals. Marine, radially symmetrical forms whose parts are in multiples of 5, with a calcareous skeleton varying in its development from minute scattered plates to a complete shell. Locomotion by means of a water vascular or ambulacral system which is peculiar to the group. Never parasitic nor colonial. Class 1. Asteroidea. Starfishes. With a pentagonal or star-like body formed of a central disc and 5 or more radiating arms. Class 2. Echinoidea. Sea urchins and sand dollars. Spheroidal, oval, or disc-shaped forms with a solid test or corona beset with numerous spines. Class 3. Holothuroidea. Sea cucumbers. Oval or worm-like, with leathery body wall containing minute plates or spicules. A crown of retractile tentacles around the mouth. Class 4. Crinoidea. Sea lilies or feather stars. Stalked echinoderms with many branched arms. Some, comatula, become secondarily free. Formerly numerous, now relatively rare. There are two wholly extinct classes, the Cystoidea and Blastoidea, somewhat similar to crinoids. Phylum 8. Annulata, Annelida. Segmented worms. Primitive, worm-like forms, with ring-like or somewhat flattened segments, and without jointed limbs. Marine worms, earthworms, and leeches. Phylum 9. Arthropoda, arthropods. Bilaterally symmetrical, segmented animals with jointed appendages. Body encased in an exoskeleton of chitin, often more or less hardened by calcareous salts. Class 1. Crustacea. Crabs, lobsters, and barnacles. Aquatic arthropods with 2 pairs of antennae and numerous appendages. Breathing generally by means of gills. A few secondarily adapted to terrestrial life. The majority free-living, some fixed or even parasitic. Class 2. Arachnida. Spiders and scorpions. Exoskeleton chitinous, 4 pairs of legs. Air breathers except the horseshoe crab, Limulus, often with silk spinning and poison glands. Free-living or rarely parasitic, never sedentary. Class 3. Myriapoda. Centipedes and millipedes. Numerous similar body segments, each bearing 1 or 2 pairs of legs. Air breathers, some armed with poison fangs. Class 4. Hexapoda. Insects. Body divided into 3 distinct regions, head, thorax, and abdomen, of which the second bears 3 pairs of legs and usually 2 pairs of wings. The higher insects undergo a complex metamorphosis. This class includes the most highly diversified and by far the most numerous of all animals, living under almost every conceivable condition of life. Phylum 10. Mollusca. Mollusks. Bilaterally symmetrical, unsegmented animals without locomotor skeleton, but with a more or less developed fold of the body wall known as the mantle, and a variously formed shell composed chiefly of calcium carbonate. Class 1. Pelecypoda. Bivalves. Clams, oysters, mussels, etc. Shell consisting of 2 lateral valves connected by an elastic hinge ligament. Fixed or free, freshwater or marine. Class 2. Gastropoda. Univalves, snails, etc. With a variously developed and ornamented, generally spirally twisted shell and an expanded creeping foot. Free-living, salt, and freshwater, some terrestrial. Class 3. Cephalopoda. Squid, octopus, nautilus, etc. With distinct head which has a circle of arm-like processes, sometimes bearing tentacles, sometimes hooks or suckers, and the equivalent of the foot of other mollusks. Shell variable, may be absent, octopus, or may be a large, spirally coiled, chambered structure, nautilus, which in some extinct forms was highly complex. Marine, some of immense size. Phylum 11. Chordata. Chordate animals. Bilaterally symmetrical, generally segmented animals with a perforated pharynx, gill slits, a hollow, dorsally situated nerve cord, and an axial, stiffening notochord which is generally replaced by the vertebral column. Subphylum and Class 1. Hemichorda. Belanoglossus, etc. Small worm-like animals with rudimentary notochord. Marine, semi-sedentary. Subphylum and Class 2. Urochorda. Tunicates or sea squirts. Generally sedentary marine animals which are free-swimming at least during larval life, when they possess a notochord in the tail. The adult is enclosed in a mantle or tunic, which may contain cellulose, a substance rarely found in the animal kingdom, generally with retrogressive metamorphosis. Subphylum 3. Vertebrata. Backboned animals. Section A. Acrania. Cephalochorda. Skull-less, notochord running to end of snout. Blood colorless, including only the little lancets, Amphioxus, etc., found burrowing in sand near the shore, nearest the ancestral vertebrate of any living form. Section B. Craniata. Skull-bearing vertebrates, with red blood. Class 1. Cyclostomata. Lampreys and hagfishes, with suctorial mouth armed with chitinous teeth, and no jaws. Elongate, eel-shaped forms, without paired fins. Class 2. Pisces. Fishes. Aquatic, generally scaly or armored, with paired and unpaired fins. Breathing by means of gills, sometimes with accessory lung-like organs. Cold-blooded, usually oviparous, egg-laying forms. Elasmobranchi. Sharks and rays. Dipnoi. Lungfishes. Ganoidae. Ganoid or armored fishes. Teleostae. Modern bony fishes. Class 3. Amphibia. Frogs and salamanders, cold-blooded, naked, and slimy or armored, with paired fins transformed into terrestrial hand-like limbs. Unpaired fins, when present, never supported by fin rays. Oviparous, breathing generally by means of gills during larval life, and by lungs as adults, with metamorphosis. Urodela, salamanders. Anura, frogs and toads. Gymnophiona, caecilians, legless, burrowing forms. Stegocephalia, extinct armored amphibia. Class 4, Reptilia, reptiles. Cold-blooded, scaly or armored, terrestrial or aquatic animals, breathing exclusively by means of lungs. Oviparous, though some snakes and the extinct ichthyosaurs brought forth the young alive. Viviparous. The living orders are few. Squamata, lizards and snakes. Chelonia, turtles and tortoises. Crocodilia, crocodiles and alligators. Rhynchocephalia, an ancient order of which the solitary lizard-like sphenodon of New Zealand is the sole survivor. Of many extinct orders there are Theromorpha, mammal-like reptiles, Ichthyosauria and Plesiosauria, marine reptiles. Dinosauria includes small to gigantic terrestrial forms related to the birds. Pterosauria, aerial reptiles with membrane extensions by which they could fly. Class 5, Aves, birds. Warm-blooded, feathered animals, with the forelimbs transformed into wings. Oviparous, a numerous but very uniform class. Class 6, Mammalia, mammals. Warm-blooded, hairy forms, generally quadrupedal and terrestrial, some aquatic, whales, seals, other aerial, bats. The young are with few exceptions viviparously born, alive, and are nourished after birth by the secretions of modified skin, mammary, glands. Chest and abdominal cavities separated by a muscular diaphragm. Subclass Prototheria. Order Monotremata, egg-laying oviparous mammals. Ornithorhynchus and Echidna. Subclass Eutheria, viviparous mammals. Some of the orders are Marsupialia, pouch-bearing mammals, opossum, kangaroo. Edentata, anteaters, sloths, and armadillos. Insectivora, shrews, moles, hedgehogs. Chiroptera, bats. Rodentia, rats, hares. Carnivora, dogs, cats, bears, seals. Cetacea, whales and dolphins. Ungulata, hoofed animals with several suborders. Elephants, horses, rhinoceroses, cattle, deer. Sirenia, sea cows. Primates, monkeys, apes, man. End of Chapter 3, Part B. Recording by Jesse Noar. Chapter 3, Part C of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Swann LULL. Chapter 3, Part C. Bionomic Classification. This classification of organisms is based upon the mode of life and the consequent adaptive modification of structure, form, and color, which in some cases so obscure the fundamental characteristics of the group to which the animal belongs as to make its true classification in the zoological scale a matter of great difficulty. For in extreme cases, true relationships are betrayed only by studying the life history of the organism, and cannot be learned from its adult condition, as in the parasitic barnacle Sacculina. A bionomic classification, therefore, does not necessarily agree with one based on such revealed relationships, but is, historically, a more primitive classification. Animals and plants may be considered first in their interrelationship with other organisms, and secondly in their relations to the physical environment. Interrelationships with other organisms. Free-living forms are such as are not sedentary nor in permanent association with other organisms in any of the several ways to be described below. They do, of course, depend upon other animals or upon plants for their sustenance. In the former case they are called carnivorous or predatory, in the latter herbivorous. The predatory animal, unless it be simply blood-sucking or one which, like certain insects, bird lice, feeds upon portions of the skin, usually destroys the prey, while the herbivore does not necessarily injure the food plant disastrously. Free-living forms of the same species may band together for mutual aid or defense, when they are called gregarious or communal. See Chapter 16. Parasitic. Parasitism will be discussed more at length in a later chapter, chapter 17, especially with regard to its degenerating influence upon the parasite. It is an ignoble association between one animal or plant and another, and while the parasite is benefited in that it obtains food and protection with the least possible effort, the effect upon the host is generally a detrimental one, and sometimes disastrous. But the parasite usually instinctively avoids fatal injury to its host, as that would be decidedly to its own disadvantage unless its days of parasitism be fulfilled. Herein it differs from the predaceous animal, whose association with the prey is transitory, but almost invariably destructive of its life. Commensal association, in contrast with parasitic, is mutually beneficial. It does not, however, imply an organic union such as prevails among symbiotic forms, but merely a more or less permanent association for mutual good. The word commensal means one who eats at the same table, but in ordinary usage has become obsolete. Nevertheless, that is what the word implies biologically, i.e., an animal which lives with or on another species, partaking of the same food. A familiar example is the association of a hermit crab and a hydroid which forms a dense furry growth over the crab's shell. The crab is a wasteful feeder, and the hydroid gathers in the tiny particles of rejected food. It also gets transportation without effort, and in return offers the crab a certain immunity from attack, as it is armed with stinging cells, and the general appearance of the furry growth renders the crab less conspicuous. Another example is the rhinoceros bird, which picks ticks from the rhino's back and gives warning of approaching danger to its dull-witted friend. The pilotfish which accompanies the shark is still another, and the peculiar association of gnus, ostriches, and zebras in Africa is a further instance. In the last example, it is merely the extension of the mutual aid afforded to the other members of a herd by the sentinels, so as to embrace more than one species. The ostrich is so capital a watchtower that the others have taken advantage of it. Symbiotic. This is the most intimate association of all, again for mutual benefit, and by some writers it seems to be considered as merely a more intimate form of commensalism. Symbiosis means living together, and in its restricted sense implies an organic union or internal partnership between organisms, so intimate that it can only be severed by death. It cannot exist between two animals, but only between an animal and a green, chlorophyll-bearing plant, or between a green and a colorless plant. Instances of the first sort are found among the lower animals, such as the green hydra, Hydra viridis, of which the color is not due to animal pigment, but to the presence of numerous minute green plants embedded in its cells. Another instance is that of the flagellate protozoan Euglena viridis, in which precisely the same conditions exist, and many radiolaria contain symbiotic algae known as yellow cells or zooxanthellae. This last relationship is thus described by Thomson. They, the yellow cells, are unicellular plants embedded in the transparent living matter of the radiolarians, and a very profitable partnership has been established. Being possessed of chlorophyll, the algae can utilize the carbonic acid formed by the radiolarian, and are able to build up carbon compounds such as starch. They give off oxygen, which is of course profitable for the animal, and they doubtless utilize nitrogenous waste products made by the animal. If things are not going well, it is always open to the radiolarian to digest its partners. The huge numbers of radiolarians, alike of individuals and of species, seem to indicate that the symbiosis is very profitable. Symbiotic association of green and colorless plants is found in the lichens, which have been proved to be compound plants, each consisting of the branching and interlacing threads of a colorless fungus enclosing partner green alga cells. The fungus fixes the plant, absorbs air, water, and salts, protects the alga from drought and injury, and forms spores which are wafted away by wind and water, and may start new lichens if they find their proper partners. The alga uses the sunlight to build up carbon compounds, and it joins with the fungus in forming sexual reproductive bodies. By taking proper precautions, the alga can be got to live in water without the fungus, and the latter can live on sugary media or the like without the alga. Thomson. Another remarkable instance of symbiotic association of somewhat different sort is that of the various beneficial bacteria that live within the bodies of higher animals, especially in the alimentary canal, and which seem to serve a very important function in aiding in the digestion and absorption of food. There is some question whether the animal could live its normal life without the aid of these internal organisms. Should their effect be deleterious instead of beneficial, they would be classed as parasites instead of symbiotic partners. Interrelationships with the physical environment. In discussion of the physical environment, the first consideration is the medium in which the organism lives, whether air or water, for this determines its method of breathing. The other features are its relation to the bottom or substratum, and whether or not the creature is a locomotor type, for as we shall see, both of these considerations influence very profoundly the fundamental form and often the color of the organism. The forms which do not depend upon the substratum, but are suspended in the medium wherein they live, may be either planktonic or nekton, according to their locomotor ability. Those which rest or move upon the bottom are called benthos. Plankton are the animals or plants which float in the water largely at the mercy of wave or current, as they possess little or no locomotive powers other than the ability to rise or sink. They range in size from microscopic dimensions to medusae half a yard in diameter, and have in general the following characteristics. Body more or less transparent, usually hyaline or pale violet or rose-tinted, though some jellyfish are rather gaudily colored. The hue is as a rule, however, one which harmonizes well with the water. There is an almost total absence of opaque skeletal structures, only a few retaining delicate calcareous shells inherited from their benthonic ancestors, Grape. In general form, planktonic organisms are as a rule radially symmetrical, for locomotion in one direction is what usually determines bilateral symmetry. The horizontal distribution of the marine plankton is largely caused by ocean currents which tend to keep the swarms of individuals together and move them en masse. Such powers of locomotion as they possess enable these organisms to sink to greater depths for darkness or tranquility during stress of weather, coming to the surface at night or in time of calm. During the day many of them sink to a depth of from 50 to 150 fathoms, rising to the surface only on quiet nights. While marine or haloplankton is the most abundant and varied, freshwater or limnoplankton also exists in nearly all lakes and rivers. Permanent aerial or geoplankton probably does not exist, though microorganisms such as bacteria or germs seem to float about in the air almost indefinitely. Examples of planktonic organisms are the innumerable foraminiferal and radiolarian protozoa, diatoms among plants, and the swarms of medusae or jellyfish seen in summer seas. Many mollusks, pteropods, heteropods, are included, some of which form the staple of diet of the great whalebone whales, and because of their small size are devoured in countless numbers, while the minute shells of foraminifera, radiolaria, pteropoda, and diatoms form the bulk of the oozes which cover thousands of square miles of the ocean floor. Nekton consists of animals with sufficient locomotive powers to stem the aquatic and aerial currents and go whithersoever they will. Their chief characteristics are well-developed motive organs, spindle form to reduce resistance, bilateral symmetry, body non-transparent but with distinct coloration which may follow fixed laws. The skeleton is opaque and the muscles and generally the organs of special sense are highly developed. Of marine invertebrates, certain of the cephalopods, notably the squid, are good examples, while among vertebrates the great majority of fishes, sea turtles, whales, and seals among the living types, and the great marine reptiles, the ichthyosaurs, plesiosaurs, and mosasaurs, among extinct animals, represent the aquatic nekton. Aerial nekton is abundant in the flying forms, such as insects, birds, pterosaurs, and bats, some of which, notably certain insects and birds, have wonderful powers of sustained flight. Aerial nekton, however, differs from the aquatic in that sooner or later it must come to rest upon the bottom and become benthonic. Benthos. Benthonic forms are the bottom dwellers, whether fixed to the substratum or with powers of locomotion over it. The former are called sedentary, the latter vagrant benthos. Sedentary benthonic forms, as a rule, exhibit radial symmetry, well shown in corals and crinoids on the part of animals and in the great majority of higher plants. Marked exception, as in the brachiopods and barnacles, do occur. Of course, this radial symmetry is only attained in its perfection where the environmental conditions are alike on all sides. Among sedentary animals, so great a dependence is placed upon food swept within reach by means of stream, tidal, or wave action, that the food-getting organs are apt to degenerate or never develop, and often a special ciliary device takes their place, as in the brachiopods, crinoids, pelecypod mollusks, tunicates, and even in the lancet, Amphioxus, and larval lamprey, cyclostome, among vertebrates. Loss or non-development of musculature, locomotor organs, bilateral symmetry, and organs of special sense are characteristic of sedentary benthos, and with rare exceptions colonial organisms are restricted to this group. Examples of sedentary benthos would be the sponges, hydroids with the exception of the remarkable Siphonophora, a free-swimming planktonic colony wherein division of labor among the various zooids has been carried to an extreme, actinozoa, sea anemones, and corals, molluscoidea as a whole, barnacles among the crustacea, certain bivalve mollusks such as the oysters, and the tunicates. With plants, almost all belong to this category, the only exceptions being the motile bacteria and other protophyta which have been included under plankton. Nectonic plants are unknown. While aerial sedentary benthos includes the great bulk of the higher plants, air-breathing sedentary animals are rare. A number, which like the barnacles may be left bare by the retreating tide, thus become temporarily aerial but do not respire air, although provision has to be made by nature to withstand the exposure. The only true aerial sedentary benthos seem to be the scale insects, Coccidae, which attach themselves permanently to some plant, twig, leaf, or fruit, and remain constantly in one place thereafter as long as the plant juices yield sufficient nourishment. Drying up of the leaf upon which they live has been known to cause a very short migration, and while extremely degenerate and scale-like, as the name implies, they never wholly lose their organs of locomotion. The group known as vagrant benthos is an extremely extensive one, including a large number of marine but fewer freshwater types, but almost all air-breathing animals. Bilateral symmetry is the rule, though some, notably the echinoderms, are radially symmetrical. This radial symmetry of the echinoderms masks a more primitive bilateral symmetry, whereas in such forms as the irregular sea urchins, a secondary bilateral symmetry is very marked. Coupled with bilateral symmetry goes the development of locomotor and the higher sense organs, and because of the intensity of the struggle for existence, the various adaptations of form, color, and food-getting devices are extremely varied. True colonies, such as the bryozoan Cristatella, occur but are very rare, though other animal associations, gregarious or communal, are much more frequent. The transition from the vagrant benthos to nekton is easy, and the instances numerous, and in some cases it is difficult to know under which category the animal should be placed, as in the case of certain marine worms and the sea otter. The term meroplankton was introduced by the German naturalist Haeckel to introduce the free-swimming young of benthonic organisms which lead, during their larval state, a planktonic existence. These forms are as a rule extremely small and have feeble powers of locomotion, generally by means of cilia. Nevertheless, they are so numerous that the upper strata of the oceans are literally crowded with them, and they form a great source of food supply for the more aggressive forms of life. Grabow says of them, "Floating about in the sea, in perfect clouds or swarms, these meroplanktonic organisms pass their short existence, a sport of the waves and currents. Sooner or later, however, they will sink to the bottom, a veritable rain of seedling organisms, and if they fall upon a fertile soil, in other words, if they reach the proper facies of the substratum, they will develop into the benthonic adult, but if they fall upon an unfavorable bottom, or if food supply is scarce, they will perish." The necessity of some means of dispersal or for the repopulation of an area wherein accident has destroyed the original inhabitants is imperative, and in the case of sedentary adults can only be attained by this means. Meroplanktonic larvae are found in every group of aquatic sedentary benthonic animals. The young of the sedentary scale insects, on the other hand, which are active for a brief time, are vagrant benthos. Spores and many seeds like those of the maple and dandelion constitute about all that can possibly be included in aerial meroplankton. Pseudoplankton is a term proposed for organisms such as the sargassum or gulf seaweed, which is normally or in early life an attached benthonic organism, but which becomes planktonic. The meaning of the term has been extended to include plants or animals living as sedentary or vagrant benthos upon floating objects such as the algae, hydroids, or bryozoans, which may be attached to the floating sargassum, and the crustacea, mollusks, or other animals which dwell among them. In many instances the pseudoplanktonic existence of these forms is due to accident, but on the other hand it seems to be habitual with certain forms, which, like the goose barnacle, lepus, rarely occur except attached to floating objects such as the timber or the bottom of ships, especially when the latter are derelict. Many of the animals found on floating sargassum seem to be characteristic of it in this condition, as they do not occur when it is attached. End of Chapter 3. Recording by Jesse Noar.
Chapter 4, Part A of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Don Evans. Organic Evolution by Richard Swann LULL. Chapter 4, Part A. Geographic Distribution. Kinds of distribution. The distribution of life on Earth has three aspects, two of which are distributions in space and one in time. Of course, every organism can be considered from all 3 points of view, but a clear comprehension of each can only be obtained by treating them separately and in order. These three distributions are known as follows. In space: geographic, horizontal or surficial distribution; bathymetric, vertical or altitudinal distribution; in time, geologic, durational distribution. Geographic distribution. The distribution of life over the Earth's surface is worldwide, as no place is so forbidding as to be entirely without its flora or fauna. The dense tropical forest, the bleakest mountain, the scorching heat and drought of the desert, the devastating cold of the polar regions, each has its quota of inhabitants, living out their lives as best they may. Closer study, however, reveals the fact that the distribution of life is by no means a uniform one, and aside from differences in fauna, due to climatic or other causes, there are peculiar instances of isolated distribution. Thus, for example, Africa has elephants, antelopes, and great apes, such as the gorilla and chimpanzee in its fauna, while Brazil, with very similar environmental conditions, has none of these, but instead possesses the tapir, sloths, and prehensile-tailed monkeys. The tapirs themselves are found in Central and South America, and again in the Malay Peninsula and Sumatra, a curious instance of discontinuous distribution, explicable only by assuming that the American and Malay tapirs are the last survivors of a widespread race, whose intervening representatives have been blotted out. Again, it is seen that the fauna of Great Britain and Japan, which are separated by thousands of miles, are very similar, whereas in Bali and Lombok, two small islands in the Malay archipelago, separated by a strait only 15 miles wide, the animals are much more unlike. Thus it is evident that the dispersal and distribution of animals is governed by laws which are far from simple. To understand them thoroughly, "The zoologist must trace out in detail the exact area or areas inhabited by the several species, genera, and larger groups of animals, and this process, to be reliable, must be based upon a true and natural classification of the animals themselves. The latter can only be attained by a due consideration of the theory of evolution, or descent with modification, as generally understood at the present day. With this must be intimately associated a knowledge of extinct forms and their distribution in time and space, and this again depends upon an acquaintance with the extent and relative position of the various fossil-bearing strata which build up the huge series of sedimentary rocks. Dispersal of animals. Necessity. The struggle for existence brought about by the rapid rate of multiplication of all animals and the consequent scarcity of food within a given area renders the dispersal of animals imperative. Not only is this struggle between members of the same species, but between allied species or any sorts of animals whose needs are sufficiently similar to induce competition. Again, gradually changing climatic conditions, which render the old home no longer suitable, impel migration where migratory roads exist. Otherwise, gradual extinction is often the result. A study of the distribution of fossil animals, such as the elephants or horses, gives evidence of repeated and worldwide migrations which probably occurred as often as opportunity arose. The extension of geographical range seems, therefore, to be a prime necessity in the case of the great majority of organisms. Barriers. Topographic barriers. Such barriers as high and extensive mountain ranges limit the distribution of many terrestrial forms, and in general are more effective if the mountains are more or less parallel with the equator, as in Europe and Asia. Here we find a marked difference between the species occupying the northern and those occupying the southern slopes. This is notably true of the great Himalaya range in northern India, which rears its mighty summits far beyond the limits of perpetual snow. On the south we have hot, moist places of India, with a very distinct tropical fauna which in many respects resembles that of Africa. North of the barrier, conditions of climate, both in temperature and degree of moisture, are entirely changed, and with them appear animals, with some notable exceptions, of a totally different sort, more nearly comparable to those of Europe. In the New World, where the mountain chains in general run north and south, their influence upon animal distribution is vastly less, and in no case do they form the striking boundaries between zoogeographical realms as in the case of the Himalayas. In many cases, says Gadow, the fauna is the same on either slope of a mountain range, and they act rather as equalizing or dispersing factors, especially when they extend from north to south. Witness the Andes, owing to which Ecuador and Peru bear a great resemblance to the Central American fauna and differ from the tropical parts of South America." The mountain ranges in the western United States do exert a certain influence, however, principally through their control of humidity. The winds blowing in from the Pacific are laden with moisture, but as they reach the mountain uplift they are deflected higher and become cooler, which causes the precipitation of the moisture in the form of rain. On crossing the barrier, the winds are practically moistureless, and, as a consequence, aridity of climate prevails east of the mountains, producing conditions ranging all the way from dry plains to actual desert. This, of course, has its profound influence upon the character of the vegetation and consequently upon plant-feeding animals, and indirectly, though to a less extent, upon carnivores. In North and South America the animals are only influenced in their range directly by conditions of temperature and rainfall. One important topographic barrier in North America is that which limits the Mexican plateau and again forms a line of demarcation between faunal realms. The plateau itself, though extending well into the tropics, has a temperature climate, and the fauna is similar to that of the region to the north and northwest. From the edge of the plateau the land drops away abruptly, and conditions rapidly change to those of a hot, moist tropic region, with a corresponding change in the plant and animal life, which is now that of tropical Central and South America. Climatic barriers. While degree of heat is of prime importance in limiting animal dispersal, Heilprin thinks that its influence has been largely overestimated. Notable instances in proof of his contention are the tiger and elephants. The former, while its normal home is in the hot districts of India and the Indian archipelago, is not restricted to those regions nor to such as have similar climates, for it is found in the elevated regions of the Caucasus and the Altai chain, and in the Himalaya range its footprints are not infrequently found impressed in the fields of snow. It is a permanent inhabitant of the cold plains of Manchuria and the Amur region, prowling about even in winter along the icy margins of the Aral Sea. The northern range of the tiger extends to about 53 degrees north latitude, as far north as Lake Baikal in Siberia or Lake Winnipeg in Canada. Elephants also do not seem to suffer from cold, provided a sufficient amount of water be obtainable. Hannibal, who invaded Italy in 218 B.C., took a herd of war elephants of the African species over the Little St. Bernard Pass, which has an altitude of 7,176 feet. Elephants also range in altitude in the Kilimanjaro region of eastern Africa from sea level up to 13,000 feet, which must give a marked temperature range. The Indian elephant also appears to be equally at home among the cool mountain heights and amidst the hot and jungly lowlands. The influence of temperature is much more marked in limiting the distribution of cold-blooded animals, or those which depend upon external temperatures for the maintenance of their bodily heat, than in the case of the warm-blooded forms. Thus the amphibians and reptiles are tropical and temperate in their distribution, rapidly diminishing in numbers toward either pole. Salamanders are limited to about the 63rd parallel in Europe, while frogs and toads are absent only from the higher latitudes north and south. The absolute northern limit of amphibian life coincides rather closely with the somewhat erratic line of 0 degrees centigrade, that is 32 degrees Fahrenheit, of annual mean temperature, a little to the north of which line the ground remains permanently frozen below the surface. The surface crust, which thaws during the summer, engenders an abundance of insects as food supply, but its freezing down to the icy bottom makes hibernation impossible. Reptiles, on the other hand, are more restricted. The crocodiles are tropical or subtropical in their distribution. The northern limit of the turtles is 50 degrees, while of the lizards there are few beyond 40 degrees, and at 60 degrees the order entirely disappears. Snakes have the widest range, but only 3 species in Europe are found beyond 55 degrees, and but one, the common viper, extends to the Arctic Circle. The terrestrial vertebrates of the frigid zones are therefore entirely birds and mammals, whose constant temperature and efficient bodily clothing enable them to maintain an active existence where the reptiles and amphibians would be reduced to a condition of torpor. This torpor can be endured for a while, and the period of hibernation or winter sleep on part of temperate cold-blooded animals is a normal manifestation, but it has its limits and cannot extend over too great a sum total of the animal's life. The presence of fossil reptiles or amphibia in the rocks of a given geologic period is, therefore, highly indicative of past climatic conditions. Lack of moisture controls the distribution of animals and plants principally where it is of a sufficient extent to produce desert conditions, for while many forms are marvelously adapted to withstand the harshest drought, for others it forms an insuperable barrier. The most notable desert barrier is that of the Sahara, which forms the area of demarcation between the Ethiopian or African zoogeographic realm and the Eurasian. So efficient is it that such mobile forms as the deer, which are found in the Americas from the Straits of Magellan to the Arctic and over the entire Eurasian continent except the Arabian Peninsula and the adjacent area to the east, are totally absent from Africa except in its extreme northern part, from the Straits of Gibraltar to Tripoli. Of course, they are absent from the long isolated Australian region, except where they have been introduced by human agency. The Sahara in Africa and the Arabian Desert are impassable to such forms. Animals like the amphibia, which require moisture for their larval life and have no great migratory powers, find even a small arid area an insuperable obstacle. The increase of moisture renders a region unsuitable for certain forms of life, in part due to possible swampy conditions which may make the area impassable to creatures not adapted to them. Swamp dwelling generally places its mark upon the animal, as in the splay feet of certain Permian reptiles. It is doubtful, however, whether even extended morasses act as a very great barrier to dispersal. Increased humidity does have a marked effect, secondarily, in affecting the vegetation, the spread of insect life, and the like, to be described later. Vegetation barriers. The profusion of vegetation depends very largely upon the climatic conditions mentioned before, temperature and degree of moisture, and its prevalence is favorable to the dissemination of certain types and unfavorable to others. The influence of vegetation is both direct and indirect. Direct, in the impossibility of forest living, especially arboreal animals, crossing regions where forestation does not occur, and in forming, especially in the tropics, so dense a growth of jungle that larger terrestrial animals are incapable of penetrating it. Thus during Pliocene times mastodons of the genus Tibolodon migrated from North into South America over the newly established Isthmus land bridge. But during the Pleistocene, while there were several species of magnificent elephants, euphas and mastodon, in North America, none of them apparently succeeded in penetrating south of the southern limits of the Mexican plateau. The one possible recorded exception is that of an imperial mammoth, Elepkas imperator, the tooth of which has been reported from the lower Pleistocene of Cayenne, French Guiana. What the conditions were which prohibited the passage of the later elephants into South America, while the earlier ones effected a crossing, we do not surely know, but the presence of a tropical jungle too dense to be penetrated by such huge beasts as these is highly suggestive. For Baumann says that at the present day the vegetation is impenetrable to an animal as large as a man, without mechanical aid. The lack of vegetation very effectively limits the distribution of certain forms, notably the primates, which with few exceptions are dwellers in tropical forests. Not only do they need trees for their safety and usual mode of progression, but also as a source of food. For the primates as an order live upon fruit, nuts, and blossoms, as well as upon insects and small birds, all of which are products of these forests. Primates were very prevalent during the Eocene in western North America. At the close of the Eocene period, however, they became utterly extinct in North America, nor is there the slightest evidence of their reappearance until the coming of man. The Eocene, especially during the middle part, when the primates were most abundant, was a time of subtropical or warm temperature conditions, as the rocks contained palms and bananas mingled with many similar mild temperature trees. With the ushering in of the next period, however, that of the Oligocene, and more especially in the Miocene, the tropical forests gave way to those consisting largely of deciduous trees which could not support a primate population all the year, hence their local extinction. This serves to illustrate not only the means whereby the absence of vegetation may limit dispersal, but also the way in which food supply limits distribution. Other illustrations would be the necessity for trees and shrubbery for animals with short-crowned browsing teeth, on the one hand, and of extensive pasturage of harsh grasses for those with long-crowned grazing teeth, on the other, each type of vegetation being unadapted to the other type of animal. Vegetation is important also in the case of many insects. Caterpillars, for instance, may be addicted to a certain species of food plant and be coextensive with it in distribution and unable to exist where the plant does not occur. Conversely, some plants are absolutely dependent upon certain species of insects for pollination, without which they can not propagate their seeds. Parasitic insects, which depend in turn upon the plant feeders, cannot, of course, exist where the latter do not occur, for many parasites are limited exclusively to a certain genus and species of host, and this again may be restricted to a very small group of plants. Insectivorous birds are also in a measure dependent on certain specific insects, the limits of whose distribution determine theirs, while frugivorous birds, or those which, like the hummingbirds, sip nectar from the flowers, are directly limited by the existence of certain types of vegetation. Thus the whole fauna and flora of a district is bound together by a complicated network of particular conditions, and the slightest alteration in any detail may upset the balance of the whole and lead to far-reaching and unforeseen results." By Bartholomew. Large bodies of water. Extensive bodies of water, when not frozen, form perhaps the most insuperable barriers of all, especially to terrestrial vertebrates like the amphibians and reptiles and mammals, but not to those which have powers of sustained flight, such as birds and bats. Freshwater fishes are also prevented from migration by large bodies of salt water, although certain fishes, such as the shad, salmon, sturgeon, and smelt, the andromedous fishes, pass from salt to fresh water annually, while in the catadromous eels the reverse migration occurs. The barrier is effective, therefore, only in the case of exclusively freshwater types, such as the carps and garpikes, catfishes, bowfin, and brook trout, some of which are quite locally restricted. To the modern amphibian, salt water constitutes a most effective barrier, as common salt is poisonous to the amphibia. Even a solution of 1% prevents the development of their larvae. Consequently, seas, salt lakes, and plains encrusted with saline deposits act as a most efficient boundary to normal spreading. But undoubtedly many individuals have made long and successful voyages across the seas on floating trees. Solutions of lime are likewise detrimental to many species, and it is a general fact that limestone terrain is poor in amphibian life, unless, of course, sufficient accumulation of humus counteracts or prevents the calcareous impregnation of the springs and pools in meadows. Salamandra maculosa is, for instance, absent in central Germany on the Muschelkalk, but it occurs in abundance in neighboring districts of red sandstone or granite. Nor can the larvae be reared successfully in very hard water. Amphibians are, as one would infer, almost completely absent from oceanic islands, the Seychelles, New Caledonia, and the Fiji and Solomon Islands forming island groups exceptional to a general rule. Another remarkable fact is the very nearly universal limitation of the tailed forms, sirens, newts, and salamanders, and so forth, to the northern hemisphere. Here the great land masses, Australia, Africa, and South America, are almost, if not entirely, isolated by the oceans, and the small migratory roads left open, which have proved sufficient for such creatures as the mammals, are inadequate for those inactive amphibians. The burrowing caecilians, on the other hand, are confined to South America and Africa, with the exception of the Seychelles, southern India, and the East Indian islands of Sumatra, Java, and Borneo, all of which are supposed to be relics of an ancient southern continent, for whose existence prior to the Tertiary period there is much evidence. The Anura, frogs and toads, enjoy a much broader distribution than the tailed forms, being barred to their overseas migration only from the most remote of oceanic islands. Their methods of dispersal will be discussed later. For some reptiles, notably the crocodilia and marine turtles, the seas, of course, afford no obstacle, the only practical limit to their distribution being that imposed by temperature. Among the most interesting of living reptiles are the giant tortoises, some of which have been in captivity for upwards of 150 years. They are confined today entirely to certain oceanic islands, the Galapagos Islands off the coast of Ecuador, Galapago being one of the Spanish terms for tortoise, and the islands of the western Indian Ocean, namely the Mascarenes, the Reunion, Mauritius, Rodriguez, the Comoros, the Aldabras, the Amirantes, and the Seychelles. On the other hand, these tortoises are totally extinct on the mainland of South America, Africa, and Eurasia. Their shells are common as fossils, however, in India, Europe, and North America, in rocks of Miocene to Pleistocene age. As land tortoises are drowned within a few hours if they attempt to swim, their distribution could not have been accomplished by any overseas journey, but must indicate again former land connections over which they could travel. Their present distribution is also within the limits of the ancient Gondwana land mentioned earlier. The serpents, many of which are fairly good swimmers, are incapable of passing large bodies of salt water of their own volition, with the exception of the specially adapted sea snakes, which are found in the tropical seas, sometimes several hundreds of miles from land. Lizards, in their adult condition, are as incapable of passing an oceanic barrier as are the snakes, but, as Heilprin remarks, "It would appear that in some special way, whether as affected by the oceanic currents themselves or through the agency of birds, their eggs may be transported to very considerable distances out to sea, since this order of animals is sufficiently represented in remote islands where neither snakes nor amphibians have as yet been encountered." With the birds, as we shall see, it is only the flightless forms, such as the ostrich, rhea, and cassowary, or the apteryx of New Zealand, which are debarred from transoceanic migrations, for even small birds are carried far on favoring gales. With mammals, except those which, like the whales and seals, are especially adapted to marine life, bodies of water of a greater expanse than 20 to 50 miles are impassable when not frozen. Many mammals are, however, excellent swimmers, the jaguar being known to cross the broadest of the South American rivers, while the tiger and elephant, as well as the deer, will all take to the water freely. But it is doubtful whether any of them will venture out of sight of land. Heilprin summarizes as follows: although "it may safely be conceded from our present knowledge on the subject that while many of the land mammalia can effect with safety and even readiness such water passages are most generally to be met with on continental areas, none probably would be prompted to undertake a journey across an arm of the sea whose width measured 50 or more miles, or even one much exceeding half that extent. To these difficulties or impossibilities on the way of dispersion must be attributed the circumstance that the vast number of oceanic islands are deficient, except where man has effected an introduction, in representatives of this particular class of animals." The finding of allied or nearly identical forms of mammals upon land masses now isolated generally points to former land connections where now none exist. Just as bodies of water prevent the passage of land animals, so land masses form barriers to the spread of sea life. Such, for instance, is Cape Cod, which separates the relatively cold waters of Massachusetts Bay from the ocean to the south, with a very marked distinction in the contained faunas. The Isthmus of Panama is another case in point. While certain relic seas like the Caspian contain seals, porpoises, and other marine vertebrates whose forefathers entered it when it was an arm of the sea, their descendants being in turn cut off from the ocean with the severance of communication. A species of shark in Lake Nicaragua is another such zoological exile. Impurity and lack of salinity of seawater. These afford an effective barrier to the dispersal of certain kinds of marine animals, such as the brachiopods, echinoids, crinoids, starfishes, squids, and foraminifera, but notably the corals and sponges. While there are freshwater sponges, they form a very small proportion of the entire number which are extant, and none have skeletal structures. On the other hand, the corals are exclusively marine, although "a few are known in brackish and even in tolerably fresh water." Cilicia rubeola is reported by the Challenger in the river Thames in New Zealand, and Dana states that "upon the reefs enclosing the harbor of Rewa in the Fiji Islands, where a large river 300 yards wide empties, which during freshets enables vessels at anchor 2.5 miles off its mouth to dip up fresh water alongside. There is a single species of madrepora growing here and there in patches over a surface of dead coral rock or sand. In similar places about other regions, species of pontes are most common." Several species of corals grow at the mouth of the Rio de la Plata. Nevertheless, no stony coral has ever habituated itself to a freshwater habitat. Quote by Grabe: "Poritis lernosa flourishes in muddy water, and Astrea bowerbanki does not seem to mind mud or sediment, or even muddy brackish water, growing on and encrusting the stones at the mouth of the Mangrove Creek, Australia, these stones being covered with mud and slime and washed over twice in the 24 hours by muddy brackish water." End quote by Grabe. These exceptions, however, are notable, for as a rule all such forms require a water of maximum purity and salinity. Hence it is that extensive coral reefs or sponge-growing areas are never found near the mouths of large rivers such as the Amazon, Orinoco, or Mississippi, each of which bears a great load of sediment seaward. The Great Barrier Reef of Australia extends along the eastern shore of that continent for a distance of 1,500 miles, and along the entire adjacent coast the map fails to reveal a single river of importance, although there are a few relatively small streams. End of Chapter 4, Part A. Recording by Don Evans. www.lazuli.com. Chapter 4, Part B of Organic Evolution. This is a LibriVox recording, and all LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Don Evans. Organic Evolution by Richard Swann LULL. Chapter 4, Part B. Means of dispersal. Animals and plants are so widespread over the surface of the globe that migratory routes must be many, despite the effective barriers which have been mentioned. The means of dispersal are land bridges such as those at Suez and Panama, both of which are of recent origin, geologically speaking, have nevertheless afforded the means whereby continents receive their fauna. The Panamanian Bridge is of particular interest because we know the history of its existence so well. There was evidently land connection between North and South America up to at least Middle Eocene times, although it may not always have been where the Isthmus of Panama now lies. While that connection existed, there was free intermigration between the continents, but during a long period of severance, until late Miocene or early Pliocene time, no interchange of species was possible, and each fauna underwent a remarkable evolution, without the admixture of forms from the other. The reformation of the land bridge, however, opened up the avenue of migration, and we find recorded the immediate incursion of the more virile North American types into South America, such as the mastodons and horses, deer, wolves, and cats, and the immigration of South American forms, the ground sloths, armadillos, and other species in exchange. The Bering Strait, although now impassable except over the ice in winter, has been at various times in the geological past a migratory route of the utmost significance, so important, in fact, that the land animals of North America and those of the Eurasian continent show the closest blood relationship, and this was especially true during Tertiary times. In fact, as Matthews says, quote, "The Alaskan Bridge is in existence today, only a few yards of its planking removed, if one may so speak, the substructure intact and the marks of the missing planks still showing on the undamaged portion." Unquote. Actually, the intervening water between America and Asia has a width of only 36 miles and a depth of from 23 to 30 fathoms, so that the comparatively slight elevation of 200 feet would afford dry and safe transit for the passing and repassing hosts. Natural rafts and driftwood. Terrestrial animals, either accidentally or with intent, occasionally take passage upon drifting material which enables them to accomplish over water journeys which are sometimes of considerable extent. Many Arctic animals, such as the reindeer, will go out upon the ice to effect a crossing like that over Bering Strait. The Nova Zembla reindeer, occasionally going to Spitzbergen, a distance of 240 miles, or such forms as the polar bear may venture out upon the shore ice for the seals or fish which constitute their prey. The bears are splendid swimmers, for one was observed by Captain Parry in Barrows Strait 20 miles from shore, with no ice in sight. Even such natatorial powers would not, however, take them to Iceland, and yet living bears are stranded on the Icelandic shores every year, no fewer than 12 having arrived in one season. In such instances the journey was probably very largely accomplished by means of floating ice floes which had broken away from their moorings. Natural rafts of vegetation are a very potent factor in dispersal. There are masses of driftwood and leaves held together by a tangle of vines, creepers, and other vegetation, and sometimes having a covering of soil sufficient to maintain living plants or even trees. Such rafts are formed by the natural accumulation of timber along the rivers, caused by the caving of the banks on the outside of the river bends, and as larger masses are formed they are swept out to sea by the action of the stream. Such natural rafts have been reported several times more than 100 miles beyond the mouths of some of the world's great rivers, and in one recorded instance the distance traveled was over 1,000 miles. Heilprin tells us that floating masses of wood, with upright trees growing over them, were mistaken by Admiral Smythe in the Philippine seas for true islands until their motion made their real nature apparent. Such rafts often have quite an assemblage of animal life, such as monkeys, tiger cats, squirrels, and arboreal mammals in general, together with reptiles and molluscs. Of the geckos, a group of climbing lizards, Gadow says, I quote, "Although not at all aquatic, they are particularly fit to be transported accidentally on or in the trunks of floating trees, to which they cling firmly, and they can exist without food for months." Unquote. In one instance a boa, a huge species of snake, was transported 200 miles on a cedar tree to St. Vincent. Heilprin records the landing of 4 pumas in a single night in the town of Montevideo. He goes on to say, "To what distance such a floating raft with its living cargo may ultimately be carried, in safety, and without detriment to its inhabitants, over the oceanic surface there are as yet no data for determining. But there would appear to be no reason for assuming that they could not be transported to a distance of several hundreds of miles, seeing that the upright vegetation found on many of them would serve with powerful effect in the face of a wind. And while the majority of the animal inhabitants might be exterminated before the end of the voyage, the safe arrival on an island or distant shore of a very limited number of individuals, embracing both males and females, would serve in a short period, under favorable conditions, to stock the new land with the species. That an absolute limit is set, however, to migration as effected in this manner is proved conclusively by the utter absence in most of the oceanic islands of indigenous mammals, excepting bats." Unquote. Favoring gales. The forms aided by this means are the aerial nekton, insects, birds, and bats, and while all three can progress without the aid of favoring winds, their flight is very largely increased thereby. This aid is perhaps largely accidental; nevertheless migratory birds are known to take deliberate advantage of it. Insects present numerous instances of great powers of sustained flight when aided by air currents, of which the most conclusive are naturally those recorded at sea. One given by Bartholomew is that of the ship Pleione, which, I quote, "returning home some years ago from New Zealand, upon reaching a point some 960 miles southwest of the Cape Verde Islands, encountered some hundreds of moths belonging to a species which is common in the eastern tropics, but not found in South America, which was the nearest land. From the direction of the wind during the 4 days previous to the occurrence, it appeared to be beyond doubt that the insects had come from the islands named, and therefore must have crossed nearly 1,000 miles of ocean." Unquote. The nuptial flights of many insects often aid, either incidentally or purposefully, in their dispersal when taken upon windy days. Bird flight is marvelous, and some recorded instances are credible only in these days of the perfection of the aeroplane. Many birds are known to pass several hundreds of miles on the wing without rest, and it is highly probable that their unaided flight may extend over 1 or more thousand. The wild goose is supposed to fly at 60 to 75 miles an hour, and the swallow at 90 miles per hour or more, and many other birds may be nearly if not quite as speedy. A sustained flight of 10 to 12 hours is not beyond belief. Otherwise, the enormous distances which certain migratory birds cover would not be possible. Land birds have been met with at all points in the transatlantic passage, but it is quite probable that passing craft afford temporary refuge to the weary ones. The prevailing westerly winds between 30 and 58 degrees north latitude carry many birds all the way across, for the landing of American birds during or after heavy storms upon the coast of England and the island of Heligoland is no unusual thing. North of 58 degrees, the prevailing winds are easterly, so that the European birds are transported to America by way of Iceland and Greenland. Bats are found the world over, even on the most remote sea isles, where they may be the only indigenous mammals. This is sufficient evidence for their migratory power. Migrations. Migrations are of two sorts: permanent or racial movements, where there is some such impelling cause as the changing of climatic conditions or the unendurable increase of competitions for food, shelter, or safety at home. Many such are recorded and will be recorded in human history, like the coming of the white men to America, while prehistory has innumerable instances of the same thing. A few such were the intermigrations between North and South America, already referred to. The worldwide dispersal of the elephants from their primal African home, and of the American camels into Asia, and their relatives, the llamas, into South America. For several such migrations of horse-like forms between North America and the Old World there is also much evidence. Seasonal migrations also occur for food and for reproduction. Those for food occur in the temperate and frigid zones, where the inclement weather of winter brings such scarcity of sustenance that animals must migrate or starve. The caribou of North America make such seasonal migrations, and the American bison or buffalo were also known to do so. The migrations of many insects, such as the Rocky Mountain locust, are well known. The most remarkable migrations are those for reproduction, for many animals have within them a wonderful homing instinct which impels them to seek out their own birthplace for the purpose of bringing forth their young. Under this head come the movements of certain fishes, such as the herring and alewife into shoal waters along the coasts, and the shad, sturgeon, and salmon to the rivers. The last mentioned ascend the Columbia and Yukon for thousands of miles, passing all but impassable obstructions in their journey and wearing themselves out in its accomplishment. Some bird migrants also cover thousands of miles, as, for example, a cuckoo which makes the annual journey from Fiji to New Zealand and return, an overseas voyage of 1,500 miles in either direction. The curlew sandpiper breeds on the Siberian tundras, but goes in the northern winter to the Cape of Good Hope, Tasmania, and Patagonia, down the three main continents. Others, like the penguin, make their long migration by swimming. Of the mammals, the sea lions, or fur seals of Alaska, excite our admiration, not so much from the length of their journey of 1,500 miles, but because of the accuracy and precision of their navigation, always arriving at the beach in the Pribilof Islands, for instance, at approximately the same time and place as the year before. But their actual passage is as mysterious as that of a raiding submarine. Zoogeographical realms. Students of animal distribution have divided the world's surface into a number of distinct areas according to the likeness or unlikeness of their fauna. These divisions are based very largely upon the distribution of mammals, but they serve nearly as well to show the dissemination of other terrestrial groups, though manifestly not at all for the birds or for marine types. Several plans have been proposed having many points of resemblance, but differing in certain minor details. The boundaries and nomenclature given on the present map are largely those of W. L. and P. L. Sclater, proposed in 1899. The realms are plotted upon a polar projection map instead of the usual Mercator's projection, as the former renders the migratory routes much more intelligible. Most naturalists agree in dividing the land surface of the globe into 6 primary areas, to which the term realm has been applied. These have been more or less divided into sub-realms, some of which are in the nature of transition areas between the larger realms. The 6 realms are: 1. The Nearctic, embracing all of North America to the edge of the Mexican plateau and including all of the islands to the north together with Greenland. 2. The Neotropical, consisting of Central America south of the Mexican plateau, all of South America, and the Antilles or West Indian islands. 3. The Palearctic, embracing the whole Eurasian continent except that portion lying south of the northern line of Persia and Afghanistan, the Himalaya Mountains, and the Nanling Range in China, all of which are barriers of a physical nature which most animals cannot surmount. Africa north of the Sahara, Iceland, Spitzbergen, and the Arctic islands north of Siberia are included in this realm. 4. The Ethiopian, including all of Africa and Arabia south of the Tropic of Cancer, although some authorities extend it north to the Atlas Mountains, making it thus include the entire Sahara. Madagascar and other small adjacent islands also come within this realm. It is almost exclusively tropical, more so than any other region. 5. The Oriental, consisting of the southern coast of Asia east of the Persian Gulf, the entire peninsula of India south of the Himalayas, India east, and the portion of China south of the Nanling Range. The islands of Sumatra, Borneo, Java, Celebes, and the Philippines are also included. 6. The Australian, embracing Australia, New Guinea, Tasmania, New Zealand, and the oceanic islands of the Pacific. Owing to the great similarity of their respective fauna, the Nearctic and Palearctic are sometimes grouped together as the whole Arctic realm. Lydekker has proposed 3 major terms to include the whole terrestrial surface, which make a strong appeal to the student of extinct as well as of living mammals, as they represent the 3 great areas of independent mammalian evolution. Lydekker would include Nearctic, Palearctic, Ethiopian, and Oriental regions, among which there has generally been more or less freedom of intermigration, in one great arctogaeic realm. South America, or the Neotropical region, was for a long time during the Tertiary isolated from the rest of the world, and to it he has given the name Neogaea, or the Neogenic realm. The third great realm, the Australian, which has been isolated since the beginning of the Tertiary, he calls Notogaea, and this is today the home of those living Mesozoic mammals, the marsupials, which competition has practically eliminated from the rest of the globe. End of Chapter 4, Part B. Recording by Don Evans, www.lazuli.com.
Chapter 5A of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Chapter 5A. Bathymetric Distribution. Definition. Bathymetric distribution concerns itself with the vertical range of organisms in space, and means much more than mere altitude, in that in passing from the highest alpine peak to the profoundest depths of the sea, one would find a series of contrasting conditions which of necessity profoundly affect the organism. Of these, the primary conditions are three. 1. The air or water medium, which determines the method of breathing, is, with few exceptions, in each case prohibitive to the inhabitants of the others. 2. The presence or absence of light not only modifies the animal directly, but indirectly through its effect upon the food supply. For assimilative plants, which form the ultimate nourishment of all animate nature, cannot exist where light is wholly absent. 3. The third primary condition is the presence or absence of a substratum, without which the organisms must be self-supporting, either buoyant or able to swim. This condition therefore determines the bionomic group to which the animal belongs, whether plankton or nekton on the one hand, or benthos on the other. See Chapter 3. The secondary conditions limiting bathymetric distribution are whether the water be fresh or salt, and the increase of pressure with depth, very slight for air-dwelling forms, but relatively enormous for those dwelling in the sea. 3 organic realms. Hence, from the bathymetric as well as from the geographic standpoint, 3 organic realms may be recognized. The bathymetric divisions are geobiotic or terrestrial, from the Greek for land and pertaining to life; limnobiotic, or freshwater inhabiting, lakes or rivers, from the Greek for lake; halobiotic, or marine or saltwater inhabiting, the sea, from the Greek for sea. These 3 realms stand in marked contrast to one another, although, as we shall see, the inhabitants do intermingle to a certain extent at their lines of contact, which also give opportunity for permanent intermigrations. Geobiotic or terrestrial realm. The terrestrial realm extends from high tide mark along the shores of all continents and islands to the summit of the highest elevation. It ranges in altitude, therefore, from lowlands to the alpine subregion, and each division, lowland, upland, prairie, high plain, or mountain range, has its own distinctive fauna and flora, governed by many influences, but in part, at least, by altitude. This limits quite effectively the character of the flora, as, for example, the contrasting vegetation of the tropical Mexican coastal lowlands on the one hand, and of the temperate high plateau on the other. The so-called timberline, the limit of tree growth, is also governed by altitude, although varying in different regions due to latitude and climate. One additional terrestrial subrealm is the cryptozoic, or the subterranean caves, from the Greek for to hide and life, the only place in the geobiotic realm where light is absent. As we shall see in a later chapter, chapter 23, this forms a limited biologic environment which profoundly affects its denizens. Internal parasites and the wood-boring larvae of insects also dwell in a lightless environment and are consequently modified. Limnobiotic realm. The terrestrial waters contain a rather limited fauna, as comparatively few of the invertebrate phyla have ever attained a foothold therein. This possibly is due in part to the freshness of the water, but also to the flowing character of the terrestrial waters, a condition to which the great majority of invertebrates, with their mero-planktonic larvae, cannot adapt themselves. Certain lakes and relic seas are the only bodies of fresh water of sufficient depth to have the deep-sea characteristics of absence of light and increase of pressure. But we do not find such profound modifications in lacustrine forms as in those which people the abyss. This is probably due in large measure to the evanescent character of all lakes from the geologic point of view. They are individually so short-lived that there has not been time for any very marked adaptive characteristics to develop in their inhabitants. Thus, for instance, while phosphorescent or light-producing organs are so characteristic of deep-sea and nocturnal marine animals, none are found either in the deep lakes or in the equally evanescent caves, although in each instance they might be very useful in the struggle for existence. Halobiotic or marine realm. Biologically speaking, the most important bathymetric realm is the marine, for here we find all the contrasting characteristics abundantly developed, except, of course, the atmospheric medium, and, in addition, the ages during which the ocean has existed have afforded sufficient time for evolution to run its course. The marine realm is divided into 4 subrealms, whose characteristics are as follows: strand, light, substratum present; floxy or shallow sea, light, substratum present; pelagic, light, substratum absent; abyssal, dark, substratum present or absent. Strand. The strand or tidal zone is the transitional area between the marine and terrestrial realms, for here the inhabitants are left bare twice daily by the receding tide, and have to endure drying, either by means of closable shells or other devices, or burrow down into the moist sands, or must be able to breathe both the air and the water. The tidal zone is, of course, of very variable extent, owing to the differing height of tides and the declivity of the strand itself, and ranges from a width of a few feet to several, and in rare cases to many miles. In the Bay of Fundy, the tides, running into a constantly narrowing area, grow proportionately higher until they attain the greatest altitude recorded in the world, about 60 feet at the time of the highest tides. Thus, in Minas Basin, full-rigged, deep-water ships may be seen lying in the red mud with no water in sight, and yet a few hours later they will be borne on the bosom of the incoming tide. Floxy. The term floxy, which is derived from the German, or shallow sea, is applied to the waters overlying the continental shelf below low water mark. This continental shelf is formed by the action of storm waves, which are continually cutting back the shoreline and depositing the debris, together with other land waste, upon the area, especially at its outer edge. This margin, which marks the extreme limit of wave action, is in round numbers about 600 feet below the surface of the sea, or at the 100 fathom line. The continental shelf varies in extent, as does the strand, increasing in width at both the inner and outer margins, and is narrowest along the newer shores of continents and islands, and widest where the coastal area is old or possibly subsiding. The slope of the continental shelf is, in general, long and smooth, the bottom near the outer edge descending more or less rapidly to the more profound depths of the sea. The floxy is of the utmost importance biologically, for it has both light with its attendant vegetation and a substratum whereupon benthonic organisms may dwell. Furthermore, its relative shallowness makes the presence of comparatively low physical barriers effective for the isolation which is so essential in evolution. All of these factors, light, plant food, movements of the waters, warmth, and isolation, make the floxy a veritable hotbed of evolution. Its importance as such has been abundantly recognized, so that it has been called the cradle of evolution. Quote, "The shore fauna is certainly the most representative of all faunas. What pictures rise in the mind! Swiftly moving infusorians lashing their way through the water, foraminifera with beautiful shells of lime slowly gliding on the fronds of seaweed, calcareous sponges like little vases, and more irregular, flinty, and horny sponges, sometimes coating the rocks like the common crumb-of-bread sponge, sometimes growing in beds like the plants they were once supposed to be, hydroid zoophytes like miniature trees on rock or seaweed, sea anemones and corals, often like beds of flowers, living an easy-going life, waiting for food to drop into their mouths, or stinging small passers-by, unsegmented worms, such as the living films, which glide on the seaweeds or stones like mysteriously moving leaves, and the nemertines, or ribbon worms, also covered with cilia, but provided with a remarkable protrusible proboscis, sometimes ejected so violently as a weapon that it breaks off altogether and wriggles like a worm itself, the higher ringed worms, or annelids, in extraordinary numbers, like Nereus, Philodos, and Aphrodite itself, so beautiful in themselves and in their names that we can understand the enthusiasm of the expert who is said to have named his 7 daughters after 7 favorite polychaetes, the starfish creeping up the rocks with their strange hydraulic locomotor system, the brittle stars using their lithe arms like gymnasts, the sea urchins tumbling along the tips of their teeth, and the sluggish sea cucumbers plunging their tentacles into the mud and then into their mouths, the beautiful colonies of moss animals, or bryozoa, crusting stone and weed as if with lace, or forming leaf-like fronds like the sea mat, flustra, which was one of the first animals Charles Darwin worked at, or growing into calcareous tufts as if in mimicry of corals, myriads of crustaceans such as water fleas, acorn shells, beach fleas, sandhoppers, nobody crabs, sea slaters, shrimps, hermit crabs, and shore crabs proper, strange sea spiders, neither crustaceans nor spiders, like Pycnogonum litorale, clambering among the seaweeds and hydroids, bivalves innumerable, such as cockles and mussels, oysters and razorfish, herbivorous gastropods like periwinkles, and voracious carnivores like the dog-whelks and buckies, sedentary limpets with a slight range of movement and a slight memory for locality, since beyond a narrow radius they fail to find their way home, an occasional cuttlefish caught in a shore pool, and many more further out. A large representation of ascidians, or sea squirts, both simple and compound, which lie at the base of the vertebrate series. The lancelets, Amphioxus, buried all but their mouth in the fine sand, true shore fishes like sand eels and gunnels and shannies, an occasional reptile like the lizard Amblyrhynchus, which swims out among the rocks, or a poisonous sea snake, or a turtle coming ashore to lay her eggs, numerous shore birds like oyster-catcher and rock pipit, gull and cormorant, and an occasional mammal like otter and seal. On the whole, a more representative fauna than in any other life area." End quote. Keen struggle for existence. Quote, "It is evident that the shore area must be characterized by a keen struggle for existence. In the open sea there is practically no limit to the floating room and swimming room, but the shore is narrow and crowded. In a rock pool there is often no vacant niche. There is competition even for foothold. It is important, for instance, that the limpet, which makes little journeys in search of seaweed to nibble, should not go too far, else it will not find its way back and will have lost the spot which its shell has grown to fit. It is curious, too, to see the American slipper limpet, one growing on the top of another to the number of 4 or 5, suggestive of the root idea of a skyscraper." End quote. Thompson. Pelagic realm. The pelagic realm embraces all of the superficial waters of the ocean down to the depth to which effective sunlight penetrates. It is characterized physically by the presence of light and the absence of a substratum. In the upper portion there is variable temperature and frequent and violent wave action, while in its lower strata the movement of the waters and the temperature are greatly reduced. The distance to which sunlight penetrates varies, being manifestly greater in the tropics, where the sun's rays may be perpendicular to the surface of the sea, and less toward either pole, where the rays become more and more oblique. By exposing photographic plates at various depths, it has been ascertained that light penetrates in the tropics to a depth of 3,250 feet, though this is true only of the ultraviolet and blue rays. Red and green rays fail to penetrate to 1,625 feet, but at 325 feet, all of the rays of ordinary bright sunshine are present, though red light is the least strong. Assimilating plant life, which, as we have seen, forms the ultimate food supply of all animals, is dependent upon the presence of these red, orange, and yellow rays, which virtually restricts it to the upper 500 feet of oceanic waters. The importance of this is such that the vertical limit of the pelagic zone may be placed at about 600 feet or 100 fathoms. Hence it becomes a seaward extension of the floc-sea. Owing to the absence of a substratum, however, no benthonic forms can exist in the pelagic realm, but all must be either nectonic or planktonic. The pelagic realm constitutes therefore the high seas, and is not only the meeting place of the commerce of all nations, but the great means of dispersal for countless forms of marine life, including the mero-planktonic larvae of shallow and deep-water benthos. Abyssal realm. The abyssal realm is that portion beyond the limits of the continental shelf and beneath the pelagic, and includes all waters below a depth of 100 fathoms, more than 105 fathoms, according to Professor E. Forbes in the Century Dictionary. This realm may be divided into the abysso-pelagic zone, wherein there is no substratum, and all organisms, like those of the pelagic, must swim or float, and the abysso-benthonic zone, in which a substratum is present. The main characteristics of the abyssal realm are: 1. Absence of light. Light, of course, must exist in the upper transitional strata, but it lacks the essentials to assimilating plant life. Hence, none exists. The animals, therefore, are all either carnivorous or feed upon dead organic matter, some of which is of plant origin. Oozes. See Chapter 23. Below the transitional realm, the darkness, except for phosphorescence, is profound. 2. Quiescence. There is an utter absence of movement aside from the sluggish ocean currents of the greater depths, the progress of which is immeasurably slow. 3. Cold. Below a certain depth, the waters in all oceans the world over have become permanently chilled nearly to the freezing point of fresh water, and all diurnal and seasonal variations of temperature, and those due to the climatic zones, cease to exist. The mean temperature of the Atlantic at the surface is 68 degrees Fahrenheit, at 500 fathoms 37 degrees, at 1,000 fathoms 35.6 degrees. The Mediterranean, on the other hand, is warmer, owing to the barrier at the Strait of Gibraltar, which prevents the circulation of the deeper and colder waters. At equivalent depths, the Mediterranean temperatures are: surface 75 degrees Fahrenheit, 500 fathoms 55 degrees Fahrenheit, and 1,000 fathoms 55 degrees. 4. Pressure. The pressure of the abyssal waters is enormous, increasing directly with the depth, the ratio of increase being about 1 ton to the square inch of surface for every 1,000 fathoms of depth, as compared with the normal 15 pounds to the square inch at sea level. Thus, the abyssal realm constitutes a simple biologic environment of vast extent, but of comparatively uniform and changeless character, and hence one not conducive to rapid evolutionary change. None of the deep-sea creatures is old, geologically speaking, for while from 25 to 35 Paleozoic genera and a larger number of species are known in the present shallow seas, none of the animals which people the deep sea are older than the Mesozoic. They seem to be all migrants from shallow water which have become adapted to the deep sea conditions. But there is, in no instance, the evolution of a new race of animals exclusively restricted to the abyssal realm. End of Chapter 5A. Recording by Lucretia B. Chapter 5B of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Organic Evolution by Richard Swann LULL. Chapter 5B. Bathymetric Distribution. Intermigrations. Intermigrations between the various benthonic realms do occur where opportunity arises. They are, as in the case of geographic migrations, both permanent and temporary, the latter being divided in turn into seasonal migrations for breeding and occasional journeys for food or retreat. Permanent migrations shoreward have not been many. Of the plants, there have been only the numerous fuci, or seaweeds, which extend above the limits of the strand from just below high water mark to the limits of salt spray. Thus, while strictly terrestrial, they still feel the influence of their ancestral home. Beyond this point, the migration apparently cannot extend. Of the animals, certain mollusks are also shoreward migrants, but these are gastropods only, for they alone seem able to combine air living with locomotion. The bivalves, for instance, surviving exposure to the air by keeping the shell tightly closed, which makes any activity manifestly impossible. Examples of shoreward migrating snails are Littorina of Brazil, which climbs the mangrove trees, and Ampullaria, the connecting link between land and water snails. Of the Crustacea, there are several species of land crabs, of which one, Burgess, an ordinary crab-like form, is found far from the shore and even climbs mountains and trees, but returns to the seashore every year to breed, the marine habitat of the young indicating to us the ancestral home of the species. Another land crab, Cenobita diogenes, is one of the hermit crabs which utilize the cast-off shell of some gastropod for the protection of their otherwise defenseless body. A specimen from the dry Tortugas group of the Florida Keys actually has a fossil shell, Livona pica, for its habitation. It is possible that the terrestrial isopods, woodlice, and pill-bugs were also derived from a littoral stock. Probably, however, most of the transitions have taken place through accident in the relic seas or lakes. The transition from aquatic to terrestrial life on the part of the vertebrates, although doubtless occurring long ago, even previous to Devonian time, was another instance of permanent landward migration, but whether from the marine littoral, the landlocked seas, relic seas freshened into relic lakes, or from the originally fresh or terrestrial waters, is not quite clear. Evidence, however, seems to point to the latter supposition. The annual return of most amphibia to the limnobiotic rather than the halobiotic realm, for the purpose of bringing forth their young, points to the former as the ancestral habitat of the race. See Chapter 29. Temporary shoreward migrations are seen in several fishes, notably the common eel, which may travel from one pond to another through moist meadow grass. Periophthalmus, a curious fish found along the shores of tropical seas, inhabiting the mud flats at the mouths of the various tropical rivers of the Old World, is popularly known as the walking fish or mud skipper, as it emerges freely from the water for hours at a time, progressing by means of its curiously modified pectoral fins. The lungfishes, dipnoi, whose swim bladder is modified to serve as a lung, can also live a long time out of water. While there is evidence that the dipnoi are the survivors of a widespread group of fishes, they are all confined to the fresh waters of Australia, Africa, and South America today. The climbing perch, Anubis, which inhabits fresh waters and estuaries in Africa and the Oriental region, not only comes ashore, but actually climbs trees to the height of several feet by means of the strong spines on its pelvic fins and gill covers. Permanent seaward migrations. Of plants, there are 8 species of phanerogams, or sea grasses, which have become adapted to saltwater life. The mangrove trees make their homes along tropical shores within the reach of the tides, but while the roots and portions of the trunk may be entirely submerged, the crown of leaves is always in the air. The grasses, of which mention has just been made, may, however, be wholly below the surface of the water. Of arthropods, there are a number which have become entirely marine, although of terrestrial origin, notably the sargassum insects, which live among the floating fronds of the gulf weed, and a spider, Desis, found in rocky crevices along the shore. Of the vertebrates, the marine migrants belong only to the 3 higher classes, land-to-sea migrations on the part of fishes being a priori impossible, and on the part of amphibia rare, as salt water is distasteful, if not actually fatal, to them. Dr. Gadow says that common salt is poison to the amphibia, even a solution of 1% preventing the development of the larvae. Nevertheless, we have reports of little frogs of the genus Rana hopping about on the flats of a tidal creek opening into Manila Bay, and 2 holes made by a crab were seen to be full of wriggling tadpoles newly hatched. The tadpoles were developing in only slightly diluted seawater. However, even though occasional temporary migrations may occur, there is no instance at present, or in the geologic past, where amphibia have become permanently adapted to marine life. Of marine reptiles, however, the tale is a very different one, for not only are there several different sorts, marine turtles, crocodiles, and sea snakes, living today, but the geologic record is crowded with the remains of sea-going reptilia, plesiosaurs, the wonderfully adapted dolphin-like ichthyosaurs, the Cretaceous sea serpents or mosasaurs, and many others, all of which have become extinct. Of birds, many, like the gulls, terns, frigate bird, auks, and petrels, make their home on the bosom of the sea, but none perhaps is so thoroughly adapted as the great wandering albatross, which follows a ship for miles without resting, and has almost entirely forsaken the land as an abiding place. Among ancient forms, Hesperornis, from the marine Cretaceous strata of our great West, was an admirable instance of a sea-adapted bird. It had lost completely all powers of flight, while the retention of reptile-like grasping teeth in its jaws, and its inclusion in marine sediments in association with plesiosaurs, mosasaurs, and other marine reptiles and fishes, give indubitable evidence of its habitat. Of mammals, the seals, whales, and sirenia, or sea cows, are instances of permanent seaward migration, possibly by way of the terrestrial rivers or estuaries. The resultant modifications of these, as well as of certain of the marine reptiles, which will be discussed in Chapter 20, are so profound as to render their return to the ancestral habitat either a relatively rare temporary migration, as in the case of the sea turtles and seals, or an impossibility, as among the ichthyosaurs and whales. Temporary seaward migrants. Of temporary seaward migrants, the most noteworthy is the curious iguana-like lizard Amblyrhynchus cristatus, which is found in the Galapagos Islands. Darwin says of it, quote, "It is extremely common on all the islands throughout the group, and lives exclusively on the rocky sea beaches, being never found, at least I never saw one, even 10 yards inshore. Their tails are flattened sideways, and all 4 feet partially webbed. They are occasionally seen some 100 yards from the shore swimming about. When in the water, this lizard swims with perfect ease and quickness, by a serpentine movement of its body and flattened tail, the legs being motionless and closely collapsed on its sides. I opened the stomachs of several, and found them largely distended with minced seaweed, ulvae, which grows in thin foliaceous expansions of a bright green or a dull red color. I have reason to believe it grows at the bottom of the sea, at some little distance from the coast. If such be the case, the object of these animals occasionally going out to sea is explained. The nature of this lizard's food, as well as the structure of its tail and feet, and the fact of its having been seen voluntarily swimming out at sea, absolutely prove its aquatic habits. Yet there is in this respect one strange anomaly, namely, that when frightened it will not enter the water. Hence it is easy to drive these lizards down to any little point overhanging the sea, where they will sooner allow a person to catch hold of their tails than jump into the water. Perhaps this singular piece of apparent stupidity may be accounted for by the circumstance that this reptile has no enemy whatever on shore, whereas at sea it must often fall a prey to the numerous sharks. Hence, probably, urged by a fixed and hereditary instinct that the shore is its place of safety, whatever the emergency may be, it there takes refuge." End quote. Among mammals, temporary seaward migrants include the polar bear, but especially the sea otter, the latter being of particular interest in illustrating the course of evolution which the seals must have undergone in their adaptation to permanent marine life. This otter, Anhydrus, was still comparatively plentiful all along the northern Pacific coast in the middle of the last century, but because of its valuable fur has been almost entirely extirpated. It is well adapted for aquatic life, with hind feet suited only for swimming, back teeth with smooth rounded crowns for crunching shellfish, and in the care which the mother shows for the pup, dandling it and diving with it. Another very remarkable seaward migrant is the hippopotamus, which, while really a terrestrial or river-inhabiting form, occasionally takes to sea in its passage from one river mouth to another, along shores which would be otherwise difficult to traverse. Permanent migrations from sea to fluviatile realm. In all probability, the mollusks, freshwater clams, mussels and snails, the crustaceans and the crayfish represent permanent or landlocked migrants from salt to fresh waters, but the great host of marine invertebrates have never succeeded in gaining a permanent foothold in the fluviatile realm. There are some curious instances of creatures, vertebrates and invertebrates, however, which have made what might be called involuntary migrations into fresh water. Such animals are found in what are known as relic seas, formerly in direct open communication with the oceans, but now cut off from them. The best known examples of these severed bodies of marine waters, according to Reichert, are the Black Sea and the Caspian Sea, both of which were once widely connected with the Mediterranean. These seas are therefore marine relics of the past that have gradually been freshened through the inflow of rivers. The animals which inhabit these seas are also relic faunas, or relic species, which upon being cut off from their ocean-living brethren, have adapted themselves to the gradually freshening waters. In the Caspian Sea, for instance, while there are comparatively few different kinds of animals, the fishes are so abundant in individuals that the fisheries are equal to those of the northern Atlantic Ocean. The fauna includes sturgeon, salmon, herring, porpoises, and seals. American examples of relic seas and lakes are Lake Ontario and, more especially, Lake Champlain. The elevated beach deposits of Lake Champlain contain an abundance of marine shells and the bones of seals and whales. Temporary migrations from sea to fluviatile realm. There are a number of fishes, such as the shad, alewife, sturgeon, and salmon, which, while the major portion of their life is spent in the sea, ascend the rivers annually to spawn. Of these, the most notable are the salmon, which ascend the Sacramento River to its extreme source, a distance of about 400 miles. In the Columbia, they ascend as far as the Bitterroot and Sawtooth Mountains of Idaho, a distance of nearly 1,000 miles, but their extreme limit is not known. In the Yukon, a few ascend to Caribou Crossing and Lake Bennett, 2,250 miles. Quote, At these great distances, when the fish have reached the spawning grounds, besides the usual changes of the breeding season, their bodies are covered with bruises, on which patches of white fungus, saprolegnia, develop. The fins become mutilated, their eyes are often injured or destroyed, parasitic worms gather in their gills, they become extremely emaciated, and as soon as the spawning act is accomplished, and sometimes before, all of them die. The ascent of the Cascades and the Dalles of the Columbia causes the injury or death of a great many salmon." Jordan. This wonderful instinct again points to the salmon and other fishes having originally been freshwater forms which have made a permanent migration seaward in some bygone period. But the homing instinct still impels them to return to their ancestral waters to bring forth their young, even though the act be suicidal so far as the individual is concerned. Permanent migrations from fluviatile realm to sea. If, as certain authorities, Chamberlain, claim, the land waters are the ancestral home of all vertebrates, see Chapter 28, the marine fishes must have all come from one or more ancient seaward migrants from the fluviatile realm. It has also been argued that the cetacea, some of which, like the blind freshwater dolphins, Platanistidae, inhabit the rivers of India, made the limnobiotic realm their transitional habitat in their ancestral migration from land to sea. This, however, cannot be proved, although the supposition that they were at least estuary inhabiting forms before taking to the high seas is certainly plausible. Temporary migrations from fluviatile realm to sea. Of transitory migrants, perhaps the most notable is the ordinary freshwater eel. Thomson thus describes their life history. Quote, "The eels of the whole of northern Europe probably begin their life below the 500 fathom line, on the verge of the deep sea away to the west of the Hebrides and Ireland, and southwards to the Canaries. The early chapters of the life history remain obscure, but the young larva rises to the upper sunlit waters as a transparent, sideways flattened, knife blade-like creature about 3 inches in length, with no spot of color save in its eyes. It lives for many months in this state, known as a leptocephalus, expending energy in gentle swimming, but taking no food. It subsists on itself, and becomes shorter and lighter, and cylindrical instead of blade-like. It is transformed into a glass eel, about 2½ inches long, like a knitting needle in girth. It begins to move towards the distant shores and rivers. In some cases it may take more than a year to reach the feeding ground, those that ascend the rivers of the eastern Baltic having journeyed over 3,000 miles. Their ranks are thinned, but large numbers succeed in finding the estuaries, and the passage of millions of elvers up our rivers is one of the most remarkable sights of spring. There is a long period of feeding and growing in the slow-flowing reaches of the rivers and in the fish-stocked ponds, but there is never any breeding in fresh water, and after some years a restlessness seizes the adults as it seized the larvae, a restlessness due, however, to a reproductive, not to a nutritive motive or impulse. There is an excited return journey to the sea. They don wedding garments of silver as they go, and become large of eye. They appear to migrate hundreds of miles, often at least out into the Atlantic to the verge of the deep sea, where, as far as we know, the individual life ends in giving rise to new lives. In no case is there any return." End quote. This is a case of former saltwater fish which, having made a permanent migration into the fresh waters in some remote time, still seek not only their own birthplace, but that of the race for the purpose of bringing forth their own young. Migrations from sea to air and air to sea. The intermigrations between the sea and the air are relatively few. Under migrations from sea to air would come as temporary intermigrants the flying fishes, of which several genera, representing a number of separate evolutions, are known. Their aerial existence is very transitory, as the flights, if such they are, rarely exceed 100 yards and are generally far shorter. Of air to sea migrants, the penguins are perhaps the best instance, as they have lost entirely the power of aerial progression, but their wings, through the degeneracy of the feathers and a compensating broadening of the entire structure, have become admirable swimming devices for what may be called submarine flight. End of Chapter 5b. Recording by Lucretia B.
Chapter 6, Part A of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Don Evans. Organic Evolution by Richard Swann LULL. Chapter 6, Part A. Geological distribution. The distribution of animals and plants in time is fully as important to our understanding of evolution as their distribution in space. For while the biologist who bases his research upon recent forms alone need concern himself with the latter distribution only, the student of the documentary evidences of evolution, which are, after all, the final court of appeal, is concerned very deeply with the former. The reader is referred to an historical geology such as Schuchert's for a complete understanding of the basis for the divisions of geologic time, but the following statements will suffice for our purpose. The science of geologic chronology is the result of a century and a half of growth, and while the major divisions of Earth's history and their limitations are now pretty well understood and agreed upon, there are yet many details to be adjusted. Geology, says Schuchert, we quote, was at first a science of minerals and rocks, and it was not until the significance of fossils as determinants of age was first worked out in England by Smith, and still more clearly by Cuvier and Brongniart in France, that stratigraphy and geologic chronology had their beginning." Unquote. Then arose the doctrine of catastrophism, advocated by Cuvier and D'Orbigny, a doctrine by which geologists, with the exception of Lyell, were largely swayed until the appearance of The Origin of Species, when they gradually came to a belief in the continual evolution of life. "The idea of catastrophism has now given way to the theory of local and general changes in the environment, changes that bring about small and great alterations in the plants and animals and in their local associations. We learn, therefore, that the primary basis for discerning the sequence of geologic events is the fossils entombed in the rocks at the time of the formation of the latter. However, many rocks have no fossils, and in the earlier and longer portion of the earth's history The life then existent was so rarely preserved that other methods have had to be devised to unravel their sequence and genetic relation to one another. Eras. Geologists, as a result of study of the rocks with their contained evidences of changing environmental conditions, have divided the Earth's past history into a number of major divisions called eras, the names of which indicate the degree of evolutionary advancement of life. Thus, beginning with the most ancient, Archaeozoic (primal life), Proterozoic (primitive life), Paleozoic (ancient life), Mesozoic (medieval life), Cenozoic (modern life), and Psychozoic (mental life). Periods. The eras in their turn are divided into periods, the names of which are in large measure geographic, that is, they were taken from the locality where the rocks pertaining to the period were first described, or they may be of historic significance in the development of the science. Thus the names Cambrian, Ordovician, Silurian, and Devonian take their origin from the ancient inhabitants of England or Wales, or from the districts where the rocks are best developed. Triassic refers to the tripartite division of the rocks of that period in Germany. Jurassic to the Jura Mountains in Switzerland, in which the strata are admirably displayed, while Cretaceous, a relic of the old days of mineral geology, is from the extensive chalk deposits pertaining to the formation in western Europe. Epochs. Subdivisions of periods have been called epochs. The epoch terms of the Cenozoic and Psychozoic eras are Eocene, dawn of the recent; Oligocene, little recent; Miocene, less recent; Pliocene, more recent; and Pleistocene, most recent. Popular names such as Age of Man for the Psychozoic era or Age of Mammals for the Cenozoic are also in general use. Reduced to its last analysis, the limits of all these eras, periods, and so on, are due to certain more or less profound changes, climatic and otherwise, which have as a basic cause the warping of the earth's crust due in turn to shrinkage of the earth's mass, giving rise not only to land elevation and often extensive mountain making, but to the alteration of the strand line or line of demarcation between land and sea. This implies, of course, inroads of the sea upon the land, with the severance of old migratory routes and the restriction of terrestrial habitats, or the withdrawal of the waters and the formation of new land bridges, or the resurrection of those which formerly existed but which have been temporarily destroyed. It will be readily seen how profound an influence upon the evolution of life such movements may have, and there were many of them, especially when we bear in mind the attendant climatic changes, some of which were of a very marked character. For changes of climate react directly upon plant life, and hence both directly and indirectly upon that of animals, while restrictions or amplification of habitat and the severance or formation of land bridges provide the essential isolation, or by the introduction of new forms increase competition, both of which stimulate evolutionary progress. Hence it is that evolution is not a uniform process, but where profound geologic changes are recorded, the tide of life flows more swiftly, and, on the other hand, during the long periods of comparative quiet, evolution is slowed down to an almost imperceptible rate of change. The times of rapid progress Cope called expression points in evolution, and the rhythm is more or less synchronous with the physical changes which time has wrought in the earth itself. Geologic time scale. A convenient time scale has been worked out, knowledge of which is fully as important to a student of evolution as is a general idea of the geographic or bathymetric divisions of the earth's surface. It follows in general the geologic timetables of Schuchert and Barrow. Age of the earth. An estimate of the earth's age in terms of years has been for a long time a subject for discussion, but the results vary astonishingly, as the following brief statement from Schuchert will show. There are two principal groups of data whereupon an estimate may be based. The first is the geologic one of the rate of sedimentation and erosion and the known thickness of the sedimentary rocks. The other group is that furnished by the physicists, and is based either upon the emanation of heat from the earth or upon the calculated age of radioactive substances. To quote Schuchert, in 1862 the physicist Lord Kelvin held that as our planet was continuously losing energy in the form of heat, the globe was a molten mass somewhere between 20 million and 400 million years ago, with a probability of this state occurring about 98 million years ago. Finally, in 1897, he concurred in Clarence King's conclusion that the globe was a molten mass about 24 million years ago. Both of these conclusions, however, were wrought out under the Laplacian hypothesis, and now many geologists hold that the earth never was molten. While geologists have not been able to fit their evidence into so short a time, they have ever since been trying to keep their estimates within the bounds of Lord Kelvin's older calculations. Walcott, in 1893, on the basis of the stratigraphic record and the known discharge of sediment by rivers, concluded that 70 million years had elapsed since sedimentation began in the Archaeozoic. Sir Archibald Geikie places the time at 100 million years, and most geologists have tried, although with difficulty, to fit the record within these estimates. Quote, "Since the discovery of radium, all of the calculations previously made have been set aside by the new school of physicists, and now geologists are told they can have 1 billion or more years as the time since the earth attained its present diameter. Even if finally it shall turn out that the physicists have to reduce their estimates as to the age of certain minerals and rocks, geologists nevertheless appear to be on safer ground in accepting their estimates than those based either on sedimentation, chemical denudation, or loss of heat by the earth." Unquote. It may truly be said of evolution that it has been an extremely slow process, requiring an immensity of time far beyond anything which our minds can comprehend. Even in these days, when money and munitions and wasted lives are reckoned by the millions. Records of life. The records of past life are the fossils entombed in the rocks. These are the actual relics of animals and plants which lived in past geologic ages, and their nature and the methods of their preservation and their interpretation will be discussed in full in Chapter 25. They are found only in sedimentary as opposed to igneous or volcanic rocks, that is, in limestone and sandstone or shales. Of these, the majority were formerly waterborne aqueous sediments, such as sands or muds, while those composed of fine sand or dust carried by the winds, that's aeolian, are comparatively rare. Of the aqueous rocks, the marine, especially those formed in relatively shallow waters bordering upon the continents, are the most extensive. Hence the record of marine life is far more complete than that of any other realm. Freshwater deposits make up for their rarity by their importance, for they contain practically all of the relics of terrestrial life. This last record is very much broken, due either to a lack of deposition or to subsequent erosion. Climatic variations. At the present day, the earth presents a variety of climatic conditions, ranging from the equatorial belt or torrid zone, where heat predominates, through the temperate zone, where the climate is milder, but where extremes both of heat and cold sometimes prevail, to the polar regions, where intense cold is the rule. Not long ago, however, geologically speaking, the temperature throughout the world was much colder than now, though there were long intervals during the glacial period of almost uniformly mild conditions. The warm climates persisted during long geological ages, and even though there were zonal belts and fluctuations in the temperature, the polar areas contained warm climate animals and plants. The temperature fluctuations were greatest toward the beginning and end of periods, and there is also evidence of increasing aridity at such times. I quote, "The long warm times were separated by short periods of cool to cold climates. Geologists now know of 7 periods of decided temperature changes: earliest and late Proterozoic, Silurian, Permian, Triassic, Cretaceous Eocene, and Pleistocene, and of these at least 4 were glacial climates, both Proterozoic times, Permian, and Pleistocene. The greatest intensity of these reduced temperatures varied between the hemispheres, for in earliest late Proterozoic and Pleistocene time it lay in the northern, while in latest Proterozoic and Permian time it was more equatorial than boreal. Cooled climates occur when the lands are largest and most emergent, during the closing stages of periods and eras, and cold climates nearly always exist during or immediately following revolutions, when the earth is undergoing marked mountain making." This quotation from Schuchert. End of Chapter 6, Part A. Recording by Don Evans. www.lazuli.com. Chapter 6, Part B of Organic Evolution. This is a LibriVox recording, and all LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Don Evans. Organic Evolution by Richard Swann LULL. Chapter 6, Part B. Summary of Geologic History. As human history is divided into ancient, medieval, and modern periods, so geologic history is comparably divisible into eras: the Paleozoic, Mesozoic, and Cenozoic. Human existence, however, far antedates written history, there having been what historians are wont to call the legendary period, but which is now pretty generally known as the prehistoric. In a like manner, there stretches back from the beginning of the fossil records of the Paleozoic a time inconceivably vast, during which life must have existed upon Earth. But the evidence for its existence is either argumentative, reasoned from the perfection which it had attained when legible fossil remains first appear, which implies a long antecedent evolution, or based upon the large deposits of limestones, graphites, and iron ores, which, so far as our knowledge goes, are mainly of organic origin. Precambrian, Archeozoic, and Proterozoic. The great legendary eras are the Archeozoic and Proterozoic, the former of which is called the Age of Unicellular Life, for undoubted fossils of this time are as yet utterly unknown, and it has been inferred that the dominant forms of plant and animal life were all unicellular forms, Protophyta and Protozoa, of very lowly organization. In the Proterozoic, while known marine fossils are extremely rare and imperfect and almost indecipherable, they nevertheless indicate a very material evolutionary advance. The evidence is positive for the existence of marine algae among plants, some radiolarians, and tubes and burrows made by annelid worms. But because of their position in the scale of animal life, the tubes and burrows imply annelida, and these, in turn, the more lowly organized sponges, coelenterates, and other worms. This Proterozoic era, especially its latter half, may therefore be called the age of primitive marine invertebrates. Paleozoic, Cambrian. By Lower Cambrian time, all the main invertebrate phyla had been evolved, and possibly the vertebrates, as the fishes were well established by the Middle Ordovician. The degree of perfection of the invertebrates at the beginning of Paleozoic time shows that more fundamental evolution had taken place up to this time than subsequently. That's per Schuchert. The main evolutionary structure of all invertebrate types have been established. Their future changes are mainly those of detail. Ordovician. The Ordovicians saw the rise of the progressive cephalopods and the first recorded fishes, with whose development the trilobites, the highest and most aggressive form of Cambrian life, began to wane, ultimately to pass out of existence with the close of the Paleozoic. The active and carnivorous cephalopods became more and more important during the Ordovician and Silurian, to be gradually displaced by the fishes. The cephalopods persisted, however, in considerable numbers until the close of the Mesozoic, when they were reduced to the comparatively unimportant place which they now hold. By far the vast majority of Paleozoic invertebrates were sedentary, benthonic forms, feeding upon microorganisms or organic debris, though some were vagrant, living upon the benthonic seaweeds, and others, like the starfishes, were carnivorous. The Ordovician rocks give us the first meager evidence of land plants, for while none are known prior to that period, the woody kinds appear before its close. To the Ordovician period, therefore, we owe the origin of two most important groups of organisms, the woody plants and the fishes among the vertebrates. Silurian and Devonian. The Silurian and Devonian periods collectively constitute the Middle Paleozoic, in contrast to the Early Paleozoic of which we have been speaking. They also usher in two events of prime importance to the animate world: the development of air-breathing forms on the part of both invertebrates, that's Silurian, and the vertebrates, Devonian. In rocks of Silurian age we have recorded the first scorpion, as well as fishes whose organization is in many respects similar to that of the double-breathing lungfishes of today. Out of this ancient lineage, although we have not yet recognized their undoubted ancestors, were to come the amphibia, which in turn gave rise to all the later terrestrial vertebrates. The Devonian rocks also give us the first record of amphibian life in the form of a single footprint. During the Devonian, the fishes developed wonderfully into various armored and shark-like forms, so that the name Age of Fishes has often been applied to this period. Terrestrially, the late Silurian and early Devonian were characterized by increasing aridity of climate, which seems to have been the impelling cause in the evolution of air-breathing vertebrates through the drying up of the streams and lakes wherein their forebears among the fishes made their homes. The Devonian was also the time of the establishment of the first land flora. Mississippian, Pennsylvanian, Permian. The Carboniferous, which is now divided into the Mississippian and Pennsylvanian periods, together with the Permian, constitutes the late Paleozoic, a time characterized in its earlier part by a mild, moist climate which, however, grew more and more severe toward the close and culminated in the early Permian Ice Age. The Carboniferous was therefore the great age of coal plants, the vegetation reaching its maximum development in variety and in the size of the individual plants during the Pennsylvanian period. Our knowledge of the plants at that time, however, is restricted to those of the low-lying swamps, and we know nothing whatever of the upland flora. The coal plants were principally spore-bearing, of rapid growth and soft, spongy woods. Seed-bearing trees and shrubs of many kinds were also present, but their flowers were small and inconspicuous. Owing to their great carrying power, the spores were very widely disseminated, giving the forests a very uniform character the world over. During the Mississippian, sharks were the dominant fishes in the seas and oceans. They were of many kinds, but consisted principally of the more ancient shell-feeding types, which were subsequently almost wholly blotted out. The Pennsylvanian, with its widespread coal swamps, formed an admirable habitat for the development of land animals, spiders, scorpions, centipedes, ancient insects, and snails among the invertebrates, and amphibians among the vertebrates. Probably before the close of this period, true reptiles, such as had abandoned the ancestral gill breathing even in the adolescent condition, appeared. Of this there is direct evidence, and in addition the deployment of reptiles in the Permian implies their existence during the preceding period. In Permian time the flora underwent a change. Harsher conditions following the warm, moist climate of the Pennsylvanian either destroyed the old cosmopolitan plant life or impelled its evolution into hardier sorts of vegetation. A new flora then arose, especially in the southern hemisphere, where the change began, because the Ice Age was here most dominant in early Permian time and spread thence throughout the world. This flora, consisting mainly of modern ferns and conifers, ginkgos, and cycads, became the dominant vegetation throughout the Mesozoic until supplanted by the modern flora in Cretaceous time. Due to the stress of climate, the insects developed those wonderful larval adaptations, seen in the metamorphosis of living insects, that enable them to live through the winter in the resting or pupal condition. The passing of the Paleozoic, which was marked by the culmination of the Appalachian Revolution, also saw the extinction of many forms of ancient life, especially among plants and invertebrates. Of the latter, those which survived have altered little in the ages which have since elapsed, while the vertebrates, especially the reptiles, birds, and mammals, have undergone practically their entire evolution. Mesozoic, Triassic, and Jurassic. The Mesozoic era, or Age of Reptiles, is justly so called, for although all 5 classes of vertebrates, that's fishes, amphibians, reptiles, birds, and mammals, were probably present throughout its entire length, the reptiles were the dominant forms of life. During the Triassic there were many kinds, some partially or wholly aquatic, others terrestrial. The Jurassic saw great numbers of reptiles inhabiting the land and the air and the sea, and toward its close an immensity of size on the part of some of them which has never been equaled before or since on the part of either terrestrial or semi-aquatic forms. The Jurassic also records the first flying reptiles and reptile-like birds, although the degree of their development again implies their existence during the Triassic. Cretaceous. The Comanchian, or Lower Cretaceous, witnessed the rise of flowering plants and the extinction of the reptiles of huge bulk, such mighty forms being as a race usually short-lived, geologically speaking. The Cretaceous proper, or Upper Cretaceous, saw the modernizing of the flora so that the forest plants would now wear a familiar aspect, although in unfamiliar combinations. The land reptiles soon reached the height of their specialization, and while not as huge as those which had gone before, exceeded them in grotesqueness and bizarre appearance. Toward the close of the Cretaceous more conservative forms again prevailed. Mammals were numerous, though still small and unspecialized, while the birds were essentially modern, except that in all known examples they still retained the teeth, characteristic of their reptilian ancestors. With the close of the Mesozoic, which was marked again by great crustal changes, the so-called Laramide Revolution, came the extinction of the dominant reptilian types on land and sea, thus preparing the way for the evolution of the warm-blooded mammals, which were to be the ruling dynasty of the Cenozoic, as the reptiles had been the overlords of creation during Mesozoic times. Cenozoic. During the Cenozoic era, or the Age of Mammals, the vegetation was of modern cast and life conditions in the main were similar to those of today, although there is much evidence of a gradual elevation of nearly all lands, with a consequent increase in aridity and diminution of moisture-loving vegetation. This meant the great spread of grasses and a necessary adaptation to grazing habits on the part of such mammals as could do so, and the weeding out or extinction of such as could not. The widespread meadows also gave insect and bird life a more diversified habitat and therefore an evolutionary impetus. Eocene. The Eocene period immediately followed the extinction of the great reptiles. Then nature began afresh to people the world with terrestrial animals, this time of the warm-blooded, furry mammalian stock which had so long been held in check. For though they had existed during the age of reptiles, their evolutionary progress was virtually at a standstill. The first deployment of mammals gave rise to creatures which served fairly well but were limited in their potential mentality, among other defects, and from Eocene times an increasing value has been placed upon mental prowess in the struggle for existence. These archaic mammals, as they have been called, underwent a brief career and were gradually replaced by the modernized forms whose brain power was capable of vastly greater development. By the close of the Eocene, the replacement was practically complete, and but a few survivors of the ancient mammals are extant. Oligocene, Miocene, Pliocene. During the Oligocene came the increasing aridity of climate which culminated in the Miocene, and with it the gradual elimination of browsing and the development of grazing types. The Miocene was the time of mammalian culmination of both numbers and kinds. The Pliocene, with its increasingly hard conditions prophetic of the glacial age, the formation of new land bridges and the severance of others, was a period of great unrest. Many migrations occurred the world over, new competitions arose, and the weaker stocks began to show the effects of the strenuous life. One momentous event seems to have occurred in the Pliocene, and that was the transformation of the precursor of humanity into man, the culmination of the highest line of evolution. Pleistocene. The Pleistocene was the final period of the Cenozoic, when, owing to continued elevation of the great continents, the age of ice was ushered in, with its long periods of devastating cold, separated by warmer interglacial times when conditions were less severe and the great ice sheets retreated into their northern fastnesses. The Pleistocene was a time of wholesale extinctions, when many races of animals were blotted out, but mankind, because of his superior mental attributes, was able to survive and rapidly took his place as the dominant form of life. Psychozoic. With the final retreat of the ice, the Psychozoic era, or Age of Man, began, with a greater perfection of man's mentality and the assertion of his "dominion over the fish of the sea, and over the fowl of the air, and over the cattle, and over all the earth, and over every creeping thing that creepeth upon the earth," and the rise of world civilizations until their present purging in the holocaust of the world's greatest war. End of Chapter 6, Part B. Recording by Don Evans. www.lazuli.com.
Part 2. The Mechanism of Evolution, Chapter 7a of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Joy Suzanne Grazer. On the web at burningjoy.com. Organic Evolution by Richard Swann LULL. Part 2. The Mechanism of Evolution, Chapter 7a, Natural Selection. All scientists and most other thinking men and women are now convinced of the truth of evolution, both inorganic and organic, that out of simple beginnings, when in the course of ages the earth was fit for organic habitation, life began. And by a continual unfolding process, there has come not only all of the marvelously adapted forms of animal and plant life which we see today, but those which paleontology reveals to us, and such as we know existed, but of which no discoverable relic remains. For our purpose, then, the fact of evolution is taken ab initio, without argument, together with the assumption that all organisms which do exist or have existed are blood-related, though the degree of relationship varies from the nearest to one inconceivably remote. But while the fact of evolution may be accepted as true, the ways and means whereby it has been brought about are not so evident, and have given rise to endless argument and discussion. These are the factors of evolution, what they are, by whom advocated, the arguments offered for their acceptance, and their plausibility are the chief subjects of our present study. Summary of factors. To summarize the various factors which have been proposed, the list is briefly presented here. The arguments will be given in later chapters. Variation is the first and most fundamental evolutionary factor. In fact, the causes of variation are among the prime causes of evolution itself. Variation, the fact that no two organisms or parts of organisms are precisely alike, no matter how closely related, is a commonly observed phenomenon, and admits of no argument whatsoever, as it is an established truth which any one, within the limits of his opportunities, may demonstrate for himself. It is the progressive factor in evolution, for without variation no change could occur, and evolution would be impossible. Although the fact is not open to argument, the means whereby variation has been brought about, the character of the variations, whether regular or irregular, determinate or fortuitous, and the amount and the part of the organism affected are subjects for debate. Heredity. The second fundamental factor is heredity, the conservative factor in evolution, that which, when variation has given rise to a new character, causes it to persist. Evolution is the change produced in a race of organisms. The mere variation of the individual, no matter how profound or how beneficial it may be, is not evolutional until it can be handed on to the offspring. And this is the function of heredity. Heredity, therefore, is an essential, a basic factor as variation itself, and is just as fully established a fact, but, like variation, there are points concerning it, especially as to the means whereby a variation becomes heritable, which are still among the unsolved problems of our science. Segregation. Another essential basic factor is isolation or segregation, the physical or biologic barrier which prohibits promiscuous interbreeding. Forms with similar variational tendencies should interbreed to perpetuate them, and dissimilar forms should not. Otherwise, the new variations would be swamped, and unless they were of dominant character, would straightway disappear. Isolation, while not of such fundamental importance as variation or heredity, nevertheless stands forth as an extremely necessary adjunct to the evolutionary process. The first means whereby segregation is accomplished is physical, as in the instance discussed under the geographic distribution, the Galapagos tortoises, page 56, or the land snails of Tahiti and Hawaii. A second form of isolation is biological, either physiological, where, due to actual structural differences, mating is either a physical impossibility, or the germinal elements fail to combine, or if they do, the resultant offspring either does not develop or is in and of itself sterile and cannot procreate. Or the impediment may be a psychological one, though to what extent this may occur outside of humanity we have no means of knowing. It is doubtful whether it is of importance in nature. Among mankind, however, it may be largely responsible for the purity of such races as the Hebrews, although even under the best conditions it is not universally effective. These fundamental factors are admitted by all, but there are other causal factors advocated originally by Charles Darwin which may or may not be true, as all students of evolution do not accept them. They are as follows. Natural selection is the great Darwinian factor, and is today held by certain writers, notably those of the so-called Neo-Darwinian school, of which the German savant August Weismann was the leader, to be almost the only factor to be considered. Natural selection determines what variational lines shall persist, and what shall be eliminated, and, according to the Neo-Darwinian school, acts upon small uncontrolled variations occurring in any conceivable direction of change. Nature either weeds out those forms in a race whose variations are out of harmony with environmental needs, allowing others to survive and hand down their adaptive changes to offspring, or it selects the fitter to survive, or it may use a combination of the two. Not all authorities, however, accept natural selection as an important factor. For the school of mutationists, headed by the celebrated Dutch botanist Hugo de Vries, believe that the new species arise by a sudden, marked changes appearing in the offspring of a normal parent. These large changes or variations are called mutations. Mutare, to change, de Vries, or salutations, saltare, to leap. Mutationists believe that natural selection therefore has nothing to do with species forming, but only in a general way with descent control, that is, keeping the successive generations of a species true to type when once it has been formed. Still a third, the compromise school, believes that natural selection is important to both in species forming and in descent control, but not as the Allmacht, which the Neo-Darwinians would have us believe. They recognize the existence of various other factors working simultaneously with selection to effect the evolutionary change. Sexual selection. Still another Darwinian factor is sexual selection, the means whereby Darwin sought to explain the existence of what are known as the secondary sexual characteristics among animals. As we shall see, this is the most doubtful factor of all of those advocated by Darwin, and is only held because nothing else better has been offered in its place. See page 127. Artificial selection. Artificial selection, as the name implies, does not occur in nature, but is the means whereby man has been able to produce the various races of domestic animals and plants out of their original wild progenitors. It has aided nature in the production of certain local strains of animals, mainly through a very efficient isolation, but is principally interesting to us in giving experimental evidence of the way wherein nature may have worked. In fact, it is the most fruitful source of inquiry which Darwin had at his command. With these introductory statements, we may pass to a detailed consideration of the first great Darwinian factor, natural selection. But it must be borne in mind that however much Darwinism may be assailed, the word refers only to a certain of these causal factors, leaving the citadel of evolutionary doctrine as impregnable as ever. Natural selection. This still seems to be the most important factor in evolution, and has been defined as the survival of the most fit, with the inheritance of those species-forming adaptations wherein fitness lies. Jordan and Kellogg. Crampton says of it, natural selection proves to be a continuous process of trial and error on a gigantic scale, for all living matter is involved. Its elements are clear and real. Indeed, they are so obvious when our attention is called to them that we wonder why their effects were not understood ages ago. These elements are 1. The universal occurrence of variation. 2. An excessive natural rate of multiplication. 3. The struggle for existence entailed by the foregoing. 4. The consequent elimination of the unfit, and the survival of only those that are satisfactorily adapted. And 5. The inheritance of the congenital variations that make for success in the struggle for existence. It is true that these elements are by no means the ultimate cause of evolution, but their complexity does not lessen their validity and efficiency as the immediate factors of the process. Prodigality of production. Perhaps one of the most impressive things in nature is the teeming abundance of living creatures. The swarms of gnats dancing in the sunlight, the great number of birds on certain oceanic islands, the immense collection of individuals in a great school of fishes, are all examples of what Thomson has called the insurgence of life, And when one realizes that he sees but the smallest fraction of the total numbers which occur, he is the more impressed. Speaking of the splendor of oceanic phosphorescence which is often met with at sea, Thomson says, "There is a cascade of sparks at the prow, a stream of sparks all along the water level, a welter of sparks in the wake, and even where the waves break there is fire. So it goes on for miles and hours, a luminescence due to the rapid and vital combustion of pinhead-like creatures, Noctiluca and others, so numerous that a bucketful contains more of them than there are people in London." On the night before the new or full moon, in the middle or latter half of December, there occurs the remarkable swarming of the Japanese Paolo worm. It invariably takes place about midnight, just after flood tide. At 1 a.m., Akira Izuka relates, the worms covered the whole water as with a sheet, and were thick down to the depth of a fathom. By 2:15 a.m., there was not a single worm to be seen. The reproductive orgasm was over. The phenomenon appears to us to be a dramatic instance of the abundance of life, of the crisis nature of reproduction, and of the precise way in which internal rhythms may be related to external periodicities. But the productivity of all living organisms is far beyond the ultimate numbers which can possibly survive. And the reason is this: organisms at their least rate of increase reproduce in geometric ratio, whereas the space they may occupy in the available food supply remain constant. Hence, without some very efficient check, the slowest breeders would soon exhaust the possibilities of food and space. For example, the elephant is the slowest breeder among mammals, but Darwin calculated that a single pair beginning to breed at 30 years and continuing to do so until a century old would produce on the average 6 young, and would have in 750 years, barring accident, 19 million descendants. A rabbit, on the other hand, may have 6 young in a litter and 4 litters in a year, and the young may begin to breed at 6 months, a vastly more rapid rate of increase than that of an elephant. Among the lower vertebrates, where no paternal care is given to the young, the potential productivity is necessarily enormous. In 4 herring, the number of eggs varied from 20,000 to 47,000. In a cod, there were 6 million, a turbo 9 million, and a ling 28 million. And yet, despite the enormous number of offspring which might possibly be produced from a single pair in one generation, the ultimate number of herring or cod or ling remains on the average about the same. The chance of survival, therefore, of a ling's egg is 1 in 14 million. The vertebrates, however, are relatively slow breeders, for there are as a rule but 1 or at most half a dozen generations in a year. With invertebrates, on the other hand, the actual number of generations may greatly exceed this. And this is what Linnaeus meant when he said, "Tres muscae consumunt cadaver equi, acquiescito ac leo." Huxley estimated that the descendants of a single green fly, if all survived and multiplied, would at the end of one summer weigh down the population of China. Common houseflies in the same time, 6 generations of 3 weeks each, occupy a space of about 250,000 cubic feet, allowing 200,000 to a cubic foot. An oyster may have 60 million eggs, and the average American yield is 16 million. If all the progeny of one oyster survived and multiplied and so on until there were great-great-grandchildren, this number, 66 decillion, and the heap of shells would be 8 times the size of the earth. Professor Woodruff, in his experimental study of Paramecium, has maintained 5-year pedigreed race, the descendants of one wild individual. In the 5 years, there were 3,029 generations, the mean rate of reproduction being 3 divisions in 48 hours. They were as healthy at the end as at the beginning of the culture, and had given evidence of the potentiality of producing a volume of protoplasm approximately equal to 10,000 times the volume of the Earth. It has been estimated that at the end of the 9,000th generation, the mass would exceed the confines of the known universe and the rate of growth would be extending its circumference into the space with the velocity of light. With such extraordinary productivity on the part of all living matter, the efficiency of the check upon every species of plant or animal is at once apparent. This check, that which Darwin and Wallace both recognized and called the struggle for existence. Struggle for existence. This struggle for existence is the competition between all organisms and between each individual and the physical environment. The struggle is threefold. Although in the long run it is all against what may be called the environmental complex, which includes all surrounding nature, whether due to physical conditions, to plant or animal life. The intraspecific struggle is the struggle against the organism's own kind, the internecine strife. In some cases, this is the most severe check of all, for each one's needs are precisely similar to the competition. Instead of touching at 1 or 2 points, is absolute. In human warfare, the hatred is more bitter the nearer the contestants are related, as shown by Germany's Gott strafe England. So it is with the organic world. Examples of this intraspecific struggle are the young trees in a forest. As the seedlings, they may spring up over a devastated area in great abundance. Some soon die from the lack of sufficient soil or moisture due to other causes, but they are still numerous until they become so tall that their branches begin to mingle and a leafy canopy is formed, which shuts out light and air from the trees of less vigorous growth. Then the weeding out of the less fit begins, and the number of trees in an area rapidly diminishes until ultimately the relatively few great trees in a mature forest are the result. In artificial lobster culture, experiments have shown that it is better to turn the newly hatched young at once into the sea rather than retain them within the limits of the aquarium for any length of time, for they are their own worst enemies, and the results of what may be called cannibalistic selection are more destructive to the race than competition with the natural environment. Interspecific struggle is the familiar struggle between members of different species, often in the nature of competition, but perhaps more frequently because one may afford food for the other. Mankind is just as much concerned in this interspecific struggle as any other form of life, but in general it is the lower organism, be it plant or animal, which is worsted in the struggle and must make good its losses or perish. That the reverse, however, is sometimes true is attested by the following note, for which the youth's companion is authority. The toll of the jungle. India still pays its annual tribute of human life to the jungle. In fact, the number of deaths from snake bites or the attacks of wild animals has steadily increased during the last 3 years, a fact which the London Times attributes to the great floods. The rising waters have driven the serpents out of the lowlands, up into the villages, and have diminished, through drowning, the natural food supply of the larger wild beasts. In 1910, 55 persons were killed by elephants, 25 by hyenas, 109 by bears, 319 by wolves, 853 by tigers, and 688 by other animals, including wild pigs. No less than 22,478 died from the bite of poisonous snakes. The grand total of mortality is 24,878. During the same year, 93,000 cattle were also killed by wild beasts or snakes. The losses on the part of the inhabitants of the jungle were nearly, but not as quite as great as those of their human enemies and the domesticated animals combined. 91,104 snakes and over 19,000 wild beasts of various kinds were killed. Instances could be multiplied ad libitum, as the struggle is universal and no creature is immune, although in more favored communities, with rare exceptions, only parasites and disease germs make their direct attack upon man. But every animate form depends on some other organism, be it animal or plant, for its food, so none is exempt from direct or indirect participation in the internecine strife. Environmental struggle is that against the physical environment, against excessive moisture or of drought, against extreme heat or cold, against lightning and tempest, earthquake and volcanic eruption. The eruption of Mont Pelee in May 1902 slew practically every inhabitant of the city of St. Pierre, there being but one lone survivor out of a population of perhaps 28,000 souls. While in August 1883, the volcano of Krakatoa, as the culmination of a series of increasingly violent explosions, threw back the inpouring sea and drove a wave of water high upon the neighboring coasts of Java and Sumatra, engulfing more than 36,000 people with their villages and lands. Iddings. The Sicilian earthquake of December 28, 1908, caused the death of possibly 200,000 people in Messina and the adjacent city of Reggio. Again, as a result of neither earthquake nor volcano, the great tropical storm of September 1900 piled up the waters of the Gulf of Mexico, almost overwhelming the city of Galveston, with the loss of about 5,000 lives. The destruction wrought by our western cyclones and tornadoes is well known, though rarely is there so appalling a loss of life as in the instances that have been given. Lightning is said to be the greatest single cause in the destruction of ranch cattle in Nebraska, due, however, in large part to the conductive power of the wire fences against which the animals drift before the storm. Thus, the lightning bolt, which would in a state of nature be local in its effect, has its danger zone very largely increased through human interference. River floods, such as those in China, take their annual toll of thousands of human lives, and doubtless of many animals as well. The tertiary sediments on our western plains, formerly supposed to be those of extensive lakes, are now interpreted very largely as river flood plain deposits. The fossil animals which they contain, and which must number many thousands, are largely the accumulations of flood victims of ancient days. Drought is another potent cause of destruction, not only of plants but of animals as well, for the drying up of a waterhole is frequently the forerunner of tragedy. Excessive cold, for which the animals are not prepared, is still another cause, as in the case of the numerous skeletons of the guanacos, a wild species, allied to the domestic llama of South America, which have been observed in Patagonia. Of these, Hatcher says, during the winter storms, these animals would be driven from the surrounding plains to seek shelter in the river valleys, and there, beneath embankments or in clumps of bushes, would be found the remains of such, as through old age or disease were unable to survive the rigors of the storm they had sought to escape. All three aspects of the struggle are, strictly speaking, with the conditions of life, and as we shall see, the interrelations of various organisms with these conditions are generally very intricate, and over against the record of a vast host of all living beings nature writes a sentence comparable to the handwriting on the wall. Thou art weighed in the balances, and thou art found wanting. But the destruction is not without distinction, for although the boldest and best of a race are sometimes the first to be destroyed, and often the slaughter is utterly indiscriminate, like that in the trenches of Flanders, or when a great Greenland whale rushes through an immense school of the delicate sea butterflies, as the pteropods are called, which form the bulk of its food, during which thousands are engulfed and swallowed. No perfection of detail, nor harmonizing color, nor activity, nor any other usually advantageous variation availing one any more than the other. Nevertheless, taking nature as a whole, the fittest survive in the long run, and the least fit are the first to perish. End of Part 2, The Mechanism of Evolution, Chapter 7a, Natural Selection. Recording by Joy Suzanne Grazer on the web at burningjoy.com. Part 2, The Mechanism of Evolution, Chapter 7b of Organic Evolution, Natural Selection. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Joy Suzanne Grazer on the web at burningjoy.com. Survival of the fittest. The survival of the fittest is therefore the result of natural selection. While the same conditions persist, specific change is very gradual, but with changing conditions placing a premium on new or different characters, species also undergo a change. Natural selection therefore enforces adaptation, and of two forms in competition, the adaptable will crowd out the inadaptable. This is forcibly illustrated by the Tasmanian wolf, or thylacine, Thylacinus cynocephalus, which is confined today entirely to the island of Tasmania, but whose remains are found in the superficial deposits of the Australian mainland, showing it to be but recently extinct. The thylacine is one of the native pouched animals, or marsupials, on page 287, which form the indigenous mammalian populations of Australasia, and is characterized, among other things, by being dull of wit, as compared with a true placental dog. Australia has such a dog, the dingo, Canis dingo, the origin of which is doubtful, but is supposed to be of Asiatic extraction and introduced into Australia by human agency. We have here the adaptable placental placed in competition with the inadaptable marsupial, with the inevitable result: the marsupial holding its own when it had only the ancient enemies of its race to contend against, but powerless in competition with the representative of a more vigorous stock. Nature's balance. Competition is inseparable from life, and is really the source of all progress, but this very competition leads to a nicety of adjustment between rival organisms, and a linking together of other beings into a marvelous web of interrelationships. This nicety of adjustment is known as nature's balance, and, although often unobserved, man has inadvertently sometimes upset this adjustment, causing dire results which he knows to his cost. Not all organisms are enemies, as we have seen in discussing the binomic relationships of animals in Chapter 3, but in many instances, although generally among unrelated forms, there is a marked interdependence, all of which adds to the complexity of the web of life, and at first sight the extremes of a series of interrelated organisms, when the links in certain chain are unknown or disregarded, make them seem very far-fetched as illustrations of the case in point. Such, for example, is the linkage suggested by Darwin between domestic cats and red clover, but when all of the links are known, the connection is at once evident. Darwin found by experiments that humble bees are almost indispensable to the fertilization of heart's ease, Viola tricolor, for other bees do not visit this flower. He also found that the visits of bees are necessary for the fertilization of some kinds of clover. For instance, 20 heads of Dutch clover, Trifolium repens, yielded 2,290 seeds, but 20 other heads protected them from bees produced not one. Humble bees alone visited red clover, as other bees cannot reach the nectar. Hence, we may infer as highly probable that if the whole genus of humble bees became extinct, or very rare in England, the heartsease and red clover would become very rare, or wholly disappear. The number of humble bees in any district depends in a great measure on the number of field mice, which destroy their combs and nests, and Colonel Newman, who has long attended to the habits of humble bees, believes that more than 2/3 of them are thus destroyed all over England. Now, the number of mice is largely dependent, as everyone knows, on the number of cats, and Colonel Newman says, near villages and small towns I have found the nests of humblebees more numerous than elsewhere, which I attribute to the number of cats that destroy the mice. Hence it is quite credible that the presence of a feline animal in large numbers in a district might determine, through the intervention first of mice and then of bees, the frequency of flowers in that district. Huxley has added a link to each end of this chain of a relationship by the supposition that the cats are very largely harbored by the unmarried spinsters on one hand, whereas clover affords sustenance for the cattle, which in turn produce the roast beef of old England, which nourishes their valiant sons, which are the source of England's might, thus making the number of maiden ladies in a community productive in this very roundabout way the prowess of the mistress of the seas. It will be readily inferred from the foregoing how wonderfully delicate this balance of nature is in its adjustment, and how easily it may be deranged by human interference. A few notable examples of such derangement of balance may be given. The English sparrow was introduced into New Haven, Connecticut for the purpose of eradicating the measuring worms which were defoliating the elm trees at the time, so characteristic of the town. It might be said, to its credit, that the sparrow did largely abate the nuisance for which it was imported, but owing to its fecundity, greediness, and quarrelsome disposition, it has become a widespread pest, driving out the native song and insectivorous birds, and offering in exchange only its own unattractive personality. Another instance is the Colorado potato beetle, Doryphora ditium lineata, a native of the Central West, where it fed upon the nightshade and was kept in check by its natural enemies. The introduction of the potato plant, a close ally of the nightshade, offered the beetle a new and abundant food supply, to which it took with great avidity, multiplying rapidly, for the lessening of the competition for food rendered the other natural checks of relatively little avail. The creatures then began an eastward migration in an ever-widening pathway, going from one potato plantation to the next, until they finally reached and extended along the Atlantic seaboard, and now extract an annual toll equivalent to thousands of dollars from the raisers of the esculent tuber. In this case, it was not, as usual, the introduction of an animal into new environmental conditions that upset the balance, but the reduction of one of the most severe checks to survival, the struggle for food. Another very remarkable instance, the entire history of which is known, is that of the gypsy moth, Ocneria dispar, which was accidentally liberated in Medford, Massachusetts in 1869. Professor Leopold Trouvelot, a French naturalist, was experimenting with silk-spinning caterpillars, especially the American species, to see if any could be made of economic importance. He also imported specimens of the insect under discussion from Europe. Evidence seems to show that some of the egg clusters or young caterpillars escaped from his house, and as he was aware of the dangerous nature of the insect in its native home, he destroyed all of the caterpillars he could find. But soon seeing that he could not fight them single-handedly, he reported the matter to the authorities. Little notice was taken of the insects, however, although after a few years they did become exceedingly troublesome to the people of the neighborhood by defoliating their shade and fruit trees. During the summer of 1889, however, their depredations and numbers increased to such an extent as to become a public menace, depreciating the value of property and causing an exodus of the infested districts, as they swarmed everywhere, and many trees and orchards died as a result of the repeated defoliation. The legislature of the Commonwealth then took up the problem of extermination and appropriated the sum of $25,000 for their elimination. Additional appropriations were requested and granted until 1900, when the work of the State Commission ceased. In the meantime, another similar pest, the brown-tailed moth, Eoproctus chrysorrhei, had also been introduced from Europe. Together with the gypsy moth, which spread alarmingly with the cessation of the work of extermination by the state, has become a problem of national importance. Hence, the United States government, in cooperation with that of Massachusetts, has taken up the fight. Actual extermination seems now out of the question, as every available method, mechanical, by poison, or by fire, has been tried. And what the authorities are striving to do is to restore nature's balance by introducing the parasites and other natural enemies of the two insects from their native home, with the hope that thereby they might be controlled and not become a burden greater than New England can bear. Yet another noted instance is the introduction of the carnivorous mammal, the mongoose, or Pestis grisos, into Jamaica. Rats brought by ships became a plague in Jamaica. To cope with them, the mongoose was imported, and it made short work of both the old world rats and the Jamaican cane rats. But when these were gone, the appetite of the mongoose remained, and the poultry and various ground birds began to suffer. Useful insect-eating lizards were also eaten, and another cloud rose on the sky. There was a multiplication of injurious insects and ticks, so that plants and animals began to be affected through an ever-widening circle. Thompson. One instance where nature's balance has been restored after being upset by human interference is in the case of a scale insect accidentally introduced into California from Australia on some young lemon trees. This multiplied until it became a most pernicious pest, which various mechanical remedies failed to control. Search was made in Australia, and a natural enemy, a ladybug, was brought over to California, with the result that not only was the scale reduced, but almost completely eliminated. It was then found that the ladybug depended upon the scale for food to such an extent that it died in turn, and now protected colonies of scale and ladybugs are kept in readiness to control future outbreaks of the pest. Survival of the existing. We have spoken of the survival of the fittest, which controls the existence not only of a race, or the individuals which make up the race, but also of the characteristics which compose the individual. There are, however, certain characteristics which seem to be non-important, and, so far as we can judge, have nothing to do with the organism's chance for survival. These non-essential characters are, as we may say, not of selection value, and persist through heredity. They are minor traits, such as peculiar color patterns, relative proportions of parts, or vestigial structures, like the red color seen in the fins of certain deep-sea fishes. These forms live in a habitat where, as no light exists, the color cannot be seen and is hence of no possible utility to the animal. The spots on the coat of a lion cub are also instances in point. Usually these indifferent traits may be interpreted in the light of historic vestiges and point to former conditions in racial history, where they were of importance in determining the chances for survival. To this category belong a great number of vestigial organs, of which Wiedersheim has enumerated 180 in the human body alone. See Chapter 37. Summary. The effect of natural selection as an evolutionary factor has thus been summarized. A. Under new conditions, harmful characters will be eliminated by selection. B. Beneficial characters are intensified and modified. C. The great body of characters, neither hurtful nor beneficial, will not be modified, but will persist through heredity. The resultant of these existing conditions of environment is, according to Darwin and his followers, an inevitable natural selection of individuals and of species. Thousands must die where 1 or 10 may live to maturity, for example, to the time of producing young. Which 10 of the 1,000 shall live depends on the slight but sufficient advantage possessed by 10 individuals in the complex struggle for existence due to the fortuitous possession of fortunate congenital differences, variations. The 990 with unfortunate congenital variations are extinguished in the struggle, and with them the opportunity for the perpetuation, by transmission to the offspring, of their particular variations. There are thus left 10 to reproduce their advantageous variations. The offspring of 10, of course, will vary in their turn, but will vary around the new and already proved advantageous parental condition. Among the 1,000, say, offspring of the original saved 10, the same limitations of space and food will again work to the killing off before maturity of 990, leaving the 10 best equipped to reproduce. This repeated and intensive selection leads to a slow but steady and certain modification through the successive generations of the form and function of the species. A modification always towards adaptation, towards fitness, towards a molding of the body and its behavior to safe conformity with external conditions. The exquisite adaptation of the parts and of functions of the animals and plant as we see it every day, to our infinite admiration and wonder, has all come to exist through the purely mechanical, inevitable weeding out and selecting by nature, by the environment determining of what may and may not live, through uncounted generations in unreckonable time. This is Darwin's causo-mechanical theory to explain the transformation of species and the infinite variety of adaptive modification. A rigorous, automatic, natural selection is the essential idea in Darwinism, at least in Darwinism as it is held by present-day followers of Darwin. Kellogg. Several objections to natural selection as a universal factor have been offered. Among them are the following. 1. To give rise to such specializations as elaborate mimicry, or the electric organ of the torpedo, etc., which are of apparent advantage only in the perfected state, natural selection, acting only upon minute gradations toward perfection, seems inadequate. The same is true of so complex and coadaptive a specialization as the eye and its function in invertebrates, or in insects and crustaceans. Kellogg. 2. Overspecialization, of which there seem to be repeated instances, such as the huge antlers of the extinct Irish deer, which in some instances outweigh the entire skeleton, or the immense spiral tusks of the Columbian mammoth, or the minute fidelity of certain mimicking insects such as the calamar, page 243. All these point to the impossibility of natural selection as an agent, for it's inconceivable that natural selection would exert an influence beyond the point of greatest usefulness to cause the organ to become a hindrance and not help, nor would it extend to fineness of detail and mimicry far beyond the most aesthetic perception of the enemy to appreciate. The objection to this objection is the absence of absolute proof that these are rightly interpreted as overspecializations. 3. Natural selection cannot account for degeneracy. To say an organ is no longer useful and hence disappears is to state the effect and not the cause. If under changed conditions a character built up by natural selection becomes a menace, the reversal of selection can accomplish its removal, but this will not suffice where the characteristic is an indifferent one. Thus it will be seen that whereas natural selection may be conceded to be a factor of importance, it is apparently not the only factor, nor indeed the only important factor in the evolution of organic life. End of Part 2, The Mechanism of Evolution, Chapter 7b of Organic Evolution, Natural Selection. Recording by Suzanne Grazer, on the web at burningjoy.com. Part 2, The Mechanism of Evolution, Chapter 8a of Organic Evolution, Sexual and Artificial Selection. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Suzanne Grazer, on the web at burningjoy.com. Organic Evolution by Richard Swann LULL, Part 2, The Mechanism of Evolution, Chapter 8a, Sexual and Artificial Selection. Sexual selection. Sexual selection is the second Darwinian factor, the one whereby Darwin sought to account for the secondary sexual characters of animals, many of which seemingly cannot be the result of natural selection, as the structure is not in every instance useful in the struggle for existence. Primary sex distinctions. The primary sex distinctions are the functional ones which naturally differ in the two sexes. They are the reproductive organs, ovaries and testes, with their essential glands and ducts, and the organs in the female whereby the young are nourished and developed before and after birth, the placenta and mammary glands. Secondary sex characters. The secondary sex characters, on the other hand, are such as are often not directly concerned with procreation, but may nevertheless be one of considerable importance to the organism. They often enable us readily to distinguish the sexes, as in the case of the peafowl, Pavo cristatus, whereas in other instances, sex may be the only recognizable by a microscopic examination of the reproductive glands, as in the American oyster, Ostrea virginica. Special organs for mating. The secondary sex characters may be grouped under several headings for the purpose of the discussion. First among them are special organs for mating, structures sometimes found in the male in addition to the normal devices for coition, which are primary sex organs. Such, for example, are the holding organs in the frogs, curious pad-like structures on the palm of the hand by which the female is firmly clasped on either side of the hip girdle. Its purpose is to keep the two sexes together, as there is generally no internal impregnation, but the eggs are fertilized in the water, which must be done immediately after extrusion before the gelatinous envelope has time to swell, since after that impregnation is impossible. The shark-like fishes, with one living exception, have a portion of each pelvic fin in the male modified to what is known as the clasper for use as an intermittent sex organ in mating, while in the related chimaeroids or silver sharks there is, in addition to the pelvic claspers, a curious device on top of the head, which looks not unlike a door knocker and is provided with hooks derived from the skin. The actual use of this knocker-like organ has never been observed, but it is also supposed to be a clasping mechanism. The cephalopods show a remarkable seasonal alteration of one of the tentacle-like arms in the male, which is used in mating, a modification known as ectocotyledonation. The arm is filled with the spermatophores prior to coition and is detached from the male during the latter process, a new one being developed to take its place. Brooding organs. Another kind of secondary sex characters are the brooding organs found especially in the female but sometimes in the male. Under this head comes the marsupium, or pouch of the female marsupial, either one transverse or two longitudinal folds of the skin, which cover the teats and serve to protect the very immature and helpless young until they are able to sift for themselves. A comparable device is seen in the seahorse, Hippocampus, a small but highly specialized fish in which the ventral fins have become modified into a brood pouch to carry eggs, until time has come for them to hatch. In this case, curiously enough, it is the male which, as Thomson says, carries the eggs about in his breast pocket. The same is true of some pipefishes, Signatus. The frogs and toads also show marvelous brooding devices, especially the famous Suriname toad, Pippa americana, in which the skin of the back of the female forms growths for the reception of the eggs, and in these the young undergo their whole metamorphosis. Each receptacle consists of a cavity with a lid. The origin of the latter is not understood, but it is probably produced by the remnant of the eggshell itself, which, after the larva has hatched, remains on the top of the cup, Gadow. Gadow says further of this group, "The greatest charm of the Anura, frogs and toads, lies in their marvelous adaptation to prevailing circumstances, and the nursing habits of some kinds read almost like fairy tales." Special sense and sound-producing organs. A third instance of secondary sex characters is represented by a special sense and sound-producing organs. Here it is the insects which form the best means of illustration, for being as a rule active locomotor types, their special senses are proportionately developed. Male moths, especially the so-called giant silkworm moths, the Cecropia, Polyphemus, Luna, and others, have the feathery antennae enormously developed compared with those of the female. They are the seat of a marvelous sense for which, for want of a better understanding, has been compared with the human sense of smell. It is used by the male in searching out the female for the purpose of mating, and is wonderfully effective, the male moths assembling around a newly emerged female from a radius of several miles. Among the scale insects, both sexes are degenerate secondary types during their young condition, and often obscurely colored so as to be discerned with difficulty. The female remains scale-like throughout life, but the male upon metamorphosis changes into a delicate two-winged fly, in sharp contrast to his lowly mate. Abortion of the mouth parts in adult insects is not infrequent, as in the Chinese silkworm Bombicus mori, mayflies, etc. But in the male coccid they are replaced by an extra pair of eyes in the underside of the head, as a necessary aid in finding the obscure female. Vocal organs are almost exclusively confined to the vertebrates, with the exception of the insects, but here it is the males only which are provided with sound-producing organs. With the crickets and katydids, they are a modification of the forewings, which have sonorous structures that are thrown into vibration by being rubbed past each other, the sound being amplified by tightly stretched membranes analogous to a banjo head, or by the resonant chambers formed by the wings, and is comparable to the body of a violin. The grasshoppers stridulate by rubbing the hind leg across the edge of the wing, and the cicadas have a remarkable pair of kettle drums at the base of the abdomen, which are made to resound by the alternate stretching and relaxing of the membrane which covers them. They lie beneath a pair of backwardly projecting flaps, comparable to the skirts of an 18th century waistcoat. Special locomotor organs, such as occur in the male scale insects and certain moths, are perhaps not so much a development in the male as degeneracy in the female. For absence of locomotor powers on her part renders increased activity upon that of the male imperative for the sake of future generations. In the famous gypsy moth, the female, although still possessing wings, has lost the power of flight because of the great weight of her body, whereas in the cankerworm moths the female wings have utterly disappeared. Organs of special use usually take the form of weapons, such as the antlers of the male deer, the tusks of the boar, and the male musk deers and chevrotins. And among insects, the huge mandibles of the stag beetles and the spines on the head and thorax of the rhinoceros beetles. Among bees and wasps, on the other hand, the sting is confined to the females, or the so-called neuters, or workers which are in reality underdeveloped females. The sting is a modification of the ovipositor, or the egg-laying organ characteristic, for instance, of the parasitic Hymenoptera, which are near relatives of their stinging allies. Special characters for exciting or attracting the opposite sex are such as appeal to the senses of sight, hearing, and smelling, taking the nature of cries and antics, of color and plumage, and of special odors. They may be either seasonal or persistent, and are in many ways the most inexplicable of all of the secondary characters of sex. They are, of course, confined almost entirely to the male. Instances may be multiplied indefinitely, as they have been observed by all. The gorgeous tail of the peacock, the pompous dignity of his carriage, and even his strident voice are all supposed to make an irresistible appeal to the female. The strutting of the common turkey, and especially the drumming of the ruffled grouse, are further instances. The beard of a man and the mane of a lion may also be included under this head. Reciprocal organs are found in a reduced state in the female, as horns in the goats, antelope, caribou, and reindeer. Stridulating organs, though underdeveloped, are present in female crickets and katydids, while in the male mammals the mammae are present in a rudimentary state. In the male, the mammary apparatus normally becomes absorbed, though frequently at birth and at puberty milk is produced in the human subject. Male goats and castrated sheep have also been known to give milk, Weitersheim. A functionless rudimentary brood pouch is present in the male Tasmanian wolf, Thylacynus. Indifferent characters. Under the head of indifferent characters are included such as are of no vital importance to their owner and yet are sex distinctive. They are mainly the negative reciprocals of certain structures already mentioned as characteristics of the opposite sex, as, for instance, the reduced wings of certain female insects, the vestigial gut in the male rotifers or wheel animalcules, the slight indifferences in size or color in many birds and insects, or the differences in the proportions or the pattern and arrangement of the veins of their wings, and in the number of tarsal or antennal segments. Atavistic characters are those distinctive of ancestral conditions, like the hairy breast and greater bodily strength which often occurs in men but rarely in women. These are the secondary sex characters to explain which the theory of sexual selection was proposed, but it will be seen that with the exception of those under the caption of indifferent characters, and perhaps the last three, they may all be regarded as a result of natural selection, as they are useful in the struggle for existence. The characteristics included in the indifferent characters group, on the other hand, are such as to make their owner more conspicuous and doubtless expose him to dangers from which the more obscure animal would be immune. Hence their development is opposed to the principle of natural selection, as the results are a handicap and not an aid in the struggle for existence. Theory of sexual selection. The theory of sexual selection is based upon the competition or struggle for mating, and while natural selection presupposes a passive female, sexual selection implies presumptive choice on her part of the most desirable male to be the father of her progeny, with the consequent inheritance by the offspring of his estimable characteristics. Darwin also included in his theory the competition or struggle for mating where rival males fight for the possession of a female, as in the case of the deer or sea lion, the female being in each instance the passive reward of the victor. But this fighting on the part of the males is merely a phase of the intraspecific struggle, although it is not a fight for food and space but for a chance to mate. This chance, however, often depends upon a life and death struggle, and no theory of sexual selection is necessary to account for the development of the weapons or greater prowess which enables one animal to become the victor over another. Postulated basis of the theory. As Darwin originally proposed it, the theory was based upon the following assumptions, the truth of which has apparently attested by a varying number of facts. First, mainly secondary sexual characters are not explicable by natural selection. They are not useful in the struggle for life. Second, the males seek the females for the sake of pairing. Third, the males are more abundant than the females. Fourth, in many cases there is a struggle among the males for the possession of the females. Fifth, in many other cases the females choose, in general, those males specifically distinguished by more brilliant colors, more conspicuous ornaments, or other attractive characters. Sixth, many males sing or dance or otherwise draw to themselves the attention of the females. Seventh, the secondary sexual characteristics are especially variable. Darwin believed that he had observed certain other conditions to exist which help make the sexual selection theory probable, but the conditions noted are sufficient if they truly exist. Kellogg. Difficulties. Some of the difficulties which stand in the way of our acceptance of Darwin's tenets are thus enumerated by Kellogg. The theory can only apply where the males are more numerous or polygamous. Otherwise, even if rejected by the first female, each male, however undesirable, would sooner or later find his mate, and thus the unornamented males would leave as many progeny as the ornamented, which would prevent any culmination of ornamental variations by selection. Among the higher vertebrates, where a great number of ornamented males occur, the proportion of the sexes is about equal, and where the polygamy exists, there is always a struggle for mastery, not an active female choice. In most species, the mating female is observed to be wholly passive, and propinquity is seen to be greatest factor in determining which two shall pair. Ornamental colors are as often characteristic of males of species in which there is no real pairing as among those which pair. Sexual choice certainly cannot account for the remarkable ornamental colors of the males of many fishes in the breeding season, for in many cases the female may not even see the male which fertilizes her already laid eggs. Eigenmann, on the other hand, notes the utter absence of such ornamentation among cave fishes which live in the dark, and argues that where they do appear, therefore, they must be due to visual selection. This may, however, be explained in a different way, as we shall see. A high degree of the aesthetic sense on the part of the females of animals would be necessary for choice on the basis of ornament and attractiveness. For this we have no other proof, and we cannot imagine its existence on the part of invertebrate animals in which ornament is not often so highly conspicuous. Even among the higher forms wherein the aesthetic sense may be developed to a certain extent, we have no assurance of any one standard of beauty, for individual taste varies greatly with men and probably also with animals. Even if we may attribute a certain aesthetic sense to mammals and birds, the question naturally arises whether it can be so keenly developed as to lead the female to make a choice among slightly differences of color or song. Yet this assumption is necessary if the theory of sexual selection is to be accepted. Would not the evolution of this aesthetic sense upon the part of the female be just as difficult to account for? Very few cases of actual choice by the female have ever been observed, for even so earnest as an observer as Darwin himself, who had every reason to record the greatest possible number, failed to note more than 8 cases among birds, and but half a dozen more, all doubtful, are mentioned in the literature from his day until 1907. Many of the so-called attractive characters of males have been found to be during life of such a nature that the females could not note them, as for instance the brilliant colors and curious horns of the male dung beetle, which are so obscured by filth that they cannot be used for display, while in the case of melodious or luminous insects like the crickets or fireflies, nearness will make a relatively feeble song or light seem much finer than that of a distant but much more musical or brilliant insect. That dances and serenades do occur during the breeding season is well known, but they may be for the purpose of excitation of the usually passive female, and may not imply the necessity of any discriminating choice upon her part among the number of males. That rivalry would be developed among the dancers or singers is only natural, and may or may not lead to further perfection of the art. End of Part 2, The Mechanism of Evolution, Chapter 8A of Organic Evolution, Sexual and Artificial Selection. Recording by Joy Suzanne Grazer. On the web at burningjoy.com.
Part 2. The Mechanism of Evolution. Chapter 8b of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jack Blake. Organic Evolution by Richard Swann LULL. Sexual and Artificial Selection. Experimental evidence. There is as yet comparatively little evidence based upon actual experiment, but such as we have is strongly opposed to the sexual selection theory. In this connection, the experiments of Meyer are of remarkable interest. He worked with the giant silkworm moth Calysamia promethea, in which there is decided sexual distinction in colour and pattern. The females have a reddish-brown ground colour, while the males are blackish, and the ornamentation in the two sexes is distinctly different. If there is any moth species in which the colours and general pattern of the male ought to be readily obvious to the female, and in which sexual selection might be presumed to have been the influence in producing a pronounced male type of preferred pattern, it is this species. Meyer's experiments were as follows. He took 449 pupae in cocoons which had been collected in Massachusetts and New Jersey south to Loggerhead Key in the dry Tortugas Islands off Florida. This island is separated by many miles of ocean from other land and is hundreds of miles south of the range of the species. Evidently, no interference with Meyer's experiments could come from outside individuals of this species. The moths issued during May and June in the proportion of about 2 males for each female. The males of this species seek out the female for pairing and can do this for a considerable distance. As many as several dozen males will find a single female and hover, fluttering about her. Meyer's first experiments were directed to the end of determining if the males found the females by sight or by smell. By enclosing females in numerous jars, variously arranged and covered or uncovered, it was readily determinable that the males never pay attention to females enclosed in transparent jars, so closed as to prevent the escape of any odours from the female, while to the females enclosed in boxes or wrapped in cotton, so as to be invisible but yet capable of giving odour off into the air, males came promptly and hovered about. To locate organs of scent in the female, Meyer cut off abdomens from various females, and then placed abdomens and abdomenless females at some little distance apart. Males came to the abdomens and not to the thorax plus wings, legs, and head parts. Females were proved to increase in attractive power with age, and virgins are a little, but only a little, more attractive than already fertilized females. It was readily proved by experiments with males whose antennae were covered with shellac, photographic paste, glue, paraffin, etc., that the sense of smell is seated in the antennae. Males with antennae covered with photographic paste did not find females, while the males with the paste dissolved off did. Meyer now tried to test the selective action of the female. The male promethea has blackish wings, while the females are reddish-brown. In accordance with the theory of sexual selection, the peculiar coloration of the male should be due to the selection of darker colored males, so that under this influence the males would become, in successive generations, darker and darker, until the present coloration has been attained. Meyer's own account of his experiments and conclusions to test the preferences and selective action of the females is as follows. In order to test this hypothesis, I cut off the wings of a number of females, leaving only short stumps, from which all the scales were carefully brushed. Male wings were then neatly glued to the stumps, and thus the female presented the appearance of a male. Under these circumstances, the males mated with the females quite as readily as they would have done under normal conditions. I then tried the experiment of gluing female wings upon the male. Here again the mating seemed to occur with normal frequency, and I was unable to detect that the females displayed any unusual aversion towards their effeminate-looking consorts. It is also interesting to note that normal males pay no attention to males with female wings. In another series of experiments, the wings were cut entirely off of the males and females, and the scales brushed off their bodies. And yet these shabby males were readily accepted by normal females, nor could I see that normal males displayed any aversion to mating with wingless females. We are therefore forced to conclude that the melanic coloration of the male has been brought about through the agency of sexual selection on the part of the female. Later, Mayall and Soule repeated the experiment on a much larger scale, with some variations in character. 1,500 cocoons of Promethea were collected in the winter of 1901 to 1902 and hung in trees, so that the issuing moths might fly about unconfined. About 600 males emerged from the cocoons, and the wings of about one half of them were painted with scarlet or green ink, while the others were allowed to remain normal in colour. It was evident that the males whose wings were scarlet and green succeeded fully as well in their attempts to mate as did the normal males. Experiments were also tried with the gypsy moth Osneria dispar with similar results, except that males with their wings cut off were more apt to meet with resistance from the females than perfect males were. From these experiments Mayer and Soule conclude that the mating instinct on the part of these two insects is a phenomenon of chemotaxis. Sexual selection on the ground of colour alone does not affect it, and there is no associative memory connected with it. Kellogg. Alternative explanations. It will be seen from the foregoing that the Darwinian factor of sexual selection rests upon very meagre evidence, the great majority of secondary sex characters being explicable by natural selection, and, on the other hand, even where natural selection cannot be invoked, sexual selection does not stand the test of experiment. Some alternative explanation becoming necessary, the following have been offered. First, that the secondary sexual characters are produced as a result of the immediate stimulus, naturally different, of the sexually differing primary reproductive organs, this stimulus being usually considered to result from an internal secretion of the genital organs acting on certain tissues of the organism, and second, that the males in most species possess an excess of energy which manifests itself in extra growths, extra development of pigment, plumage, etc., and that displays by the males of special movements, sound makings, etc., are direct effects or manifestations of sexual excitation. Kellogg. In explanation of the first of these alternative theories, it should be remembered that there are within the body numerous glands, some of which, like the salivary glands, liver, or pancreas, have ducts connected with them, and these ducts bear away a definitive secretion which, like saliva, pancreatic juice, and bile, has a particular and well-known function. In addition, there is a group of so-called ductless glands, such as the spleen, the thymus, and thyroid bodies, and suprarenal capsules. These are of considerable size and very constant in a large number of vertebrated animals. Hence their importance is manifest, but is not in every instance clearly understood. They seem, however, to have a very vital regulating function of one sort or another, and their serious derangement is always followed by or concomitant with a disease. The reproductive glands, especially those of the male, are often large, seemingly unnecessarily so if procreation is their only function. Hence it is probable that in addition to their normal external secretion, which is passed out through the seminal ducts, there may be additional internal secretion, which is poured into the blood or lymph stream and in some way controls the growth of horns or mane or beard, just as another ductless gland. The pituitary body seems to be concerned with bodily growth. The secondary sex characters do not develop until the sex organs mature, and on the other hand, emasculation of the glands themselves prevents the appearance of these characters, which is positive evidence of the interrelation of these structures. The excess of vigor in the male is due to the vastly greater task which the female has of providing nourishment for the offspring, either in the form of yolk in the bird or reptile, or of interuterine nourishment and milk in the mammal. With approximately equal vitality to begin with, the drain upon the female would lead to relative excess of energy on the part of the male, which could manifest itself in the development of the male characteristics. As we shall see in the later chapter, chapter 23, cave animals are characterized by depauperation, lessening of the stature due to starvation. Excess of energy is inconceivable on the part of a cave salamander or fish, and therefore could not give rise to the exuberant growth. This may answer Eigenmann's argument, at least in part. In order that the duty of procreation may not be shirked, it is necessary for the male to have increased activity and sexual instinct in proportion as the female is passive, which would account for a greater sexual excitation on his part. A final explanation for secondary sex distinction is that of Emery, who believes that many cases of secondary sexual differences are explained by the sudden appearance, mutation, of another form of male or female, the persistence for a while of the two forms side by side, as now exists in numerous dimorphic species, especially among insects, and then the gradual dying out, killing out by natural selection, of one of the two old original forms, the one like the other sex, thus leaving the other or aberrant form, Kellogg. This explanation is also offered to account for the development of mimicry among butterflies, and will be further discussed under that head. Kellogg seems to think that as an explanation for development of sex characteristics it is rather far-fetched, but in the Promethea moth, which we have discussed, the larger and more brilliantly coloured individual is the female, which makes it difficult to apply the excess of male vigour theory, to say the least. The effect of emasculation upon the male, if the experiment could be tried, would be of great interest. By way of summation, Kellogg says the plain truth is that the satisfactory, all-explaining explanation of secondary sexual characters and sexual dimorphism as a whole is yet to be formulated. Artificial selection. Artificial selection is the process whereby the various breeds or races of domestic animals and plants have been formed. As the name implies, it does not occur in nature, and its place is in a discussion of evolution is largely illustrative in that it shows, at least in part, the way nature in her turn has wrought out the wonderful changes which the organic world has undergone. It is of the character of experimental biology upon which modern investigators rely so largely for their facts, but it has been found that laboratory experiments sometimes succeed where nature fails, so that it is quite possible that the theory of natural selection, for instance, rests too largely upon the assumed analogy with the artificial. Artificial selection is, in its simplest aspect, an extremely old process, judged by human standards, extending as it does over 8,000 years, and some of the changes wrought animals and plants are truly marvelous. Certain types, on the other hand, like the peacock or guinea pig hen, lack plasticity, and all the centuries of their domestication have failed to produce any very marked departure from the original stock. The forms produced by artificial selection are often very far from a natural ideal, and are not such as would be produced or even survive in the wild state. In nature, characteristics which make for success in the struggle for existence are the product of evolution. In domestic races, the qualities or traits which are useful to man or conform with his fancy or with style are selected, many which would prove an insuperable handicap in open competition. Another characteristic of artificial breeds is their instability, their proneness to revert to the original type in a few generations if the vigilance of the breeder in prohibiting promiscuous mating is relaxed. Examples of artificial selection. Pigeons. Among the most plastic of all domesticated animals are the pigeons, of which considerably more than 150 named varieties, all descended from a single known source and which breed true, were known at the time of Darwin, 1868. Moreover, the range of variation is so great that some domestic races of the rock pigeon differ fully as much from each other in external characters as do the most distinct natural genera. Darwin. The rock pigeon Columbia livia, which include 2 or 3 closely allied subspecies or geographical races, is to be regarded as the common parent form. From this conservative bird there have been derived some remarkable types, such for instance as the pouter, in which the body and legs are elongate and the feet are fully feathered. But the most peculiar feature which gives the name to the race is the enormous size of the esophagus, which is often inflated, giving the bird a remarkable military air. A second race consists of the carrier pigeons, with elongated beak, neck, and body, but with the eyes surrounded by much naked, generally wattled skin. These are the pigeons capable of the most sustained flight, and are used abundantly as homing pigeons. In the race of the fantails, the tail is expanded directly upward and formed of many feathers, with no oil gland, and there is a rather short body and beak. The carriage of this bird is remarkable. The head touches the tail feathers, and habitually trembles very much, and the neck has an extraordinary backward and forward movement. Good birds walk in a singular manner, as if their feet were stiff, and owing to their large tails they fly badly on a windy day. The turbits have the feathers reversed along the front of the neck and breast, while in the Jacobins they are reversed even more along the back of the neck, forming a hood which, meeting in front of the neck, almost encloses the head. Tumblers have a curious habit of tumbling backwards during flight, some, particularly the Dutch rollers, tumbling to an extraordinary degree. Every few seconds over they go, 1, 2, or 3 somersaults at a time. Here and there a bird gives a very quick and rapid spin, revolving like a wheel, though they sometimes lose their balance and make a rather ungraceful fall, in which they occasionally hurt themselves by striking some object. Brent in Darwin. In the Indian frillback, as in the Jacobin, the feathers are reversed, but in the frillback they curl backward over the whole body. The trumpeters have a tuft of feathers at the base of the beak curling forward, and a very peculiar voice. These instances, the descriptions of which have been taken from Darwin, will suffice to show not only the extremes of variation, but the impossibility of natural survival on the part of some of them, notably the tumblers and fantails, with their poor locomotive powers, and the frillbacks, whose feathers, instead of being an admirable protection against inclement weather, actually invite the destruction of the bird. The young of all the highly improved fancy birds are extremely liable to disease and death, owing to the detrimental effect produced on the constitution of an animal by too close inbreeding. Some of these breeds are very old, pouters, Jacobins, and tumblers having existed prior to 1600. Nevertheless, they are not yet stable, and it is said that only 2 generations of promiscuous breeding will suffice to produce a mongrel in many ways a practical reversion to the ancestral rock-dove type. Factors of artificial selection. The means employed by the stock breeder in the production of new varieties have been enumerated by Jordan and Kellogg as follows. First, unconscious selection with more or less complete isolation. What this really means is a weeding out of the unfit, the less desirable animals from every point of view. These are eliminated and the remaining animals permitted to breed. This improves the stock without giving the race distinctive qualities. Nevertheless, where isolation is effective and environmental conditions differ, it leads to time to marked radical divergence. Among the sheep of England, several markedly distinct races have been thus produced as follows. Hornless varieties. Southdown sheep of Sussex, tawny face and legs. Hampshire sheep, black face, ears and legs, black spot and a tail. Devonshire sheep, similar to preceding but without black spot and a tail. Cheviot sheep, face and ears white, head free from wool, ears erect. Shropshire sheep, dun face, face more or less covered by wool. Horned varieties. Dorset sheep, white face and ears, small white curved horns. Irish sheep, black horns. Second, conscious selection of the more desirable individuals, emphasizing such points as larger size, plumpness, earlier maternity, greater docility and fertility, while unconscious selection tends to produce racial divergence. Here the reverse is true, for these good qualities appearing in all individuals tend to obscure natural or racial traits and make all sheep look alike. Third, conscious selection directed towards definite or special ends, that is, emphasizing certain individual characteristics rather than working toward a good all-round animal. Variation is continually bringing new points to the breeder's notice. Those which strike his fancy or increase the value of the animal will be cumulatively emphasized in successive generations by breeding only those individuals which show the characteristic best. In this way, increased milk flow or yield of meat or wool or disappearance of horns is obtained. Often the character which strikes the breeder's fancy is non-beneficial and hence opposed to the result which would be produced by natural selection. Fourth, crossing or hybridizing. The crossing of 2 individuals is often of great benefit because it 1. Increases the range of variation, 2. Adds or combines certain desirable characters, 3. Eliminates the undesirable. In general, at least after the first generation, the progeny will diverge widely from one another. Some will show good qualities, some poor, some will be a mosaic of both parents, some will diverge widely from either, often showing traits either remotely ancestral or wholly new. Jordan and Kellogg. When this crossbreeding is accompanied by careful selection directed towards definite or special ends, remarkable results are accomplished, and it is mainly upon this series of processes that breeding as a fine art depends. In this way, Luther Burbank has produced a marvelous assemblage of plant varieties, flowers and fruits, attaining by his patience and skill results which are almost like those of wizardry. Limits of artificial selection. These are not met with as soon among plants as among animals, and the first impediment is lack of fertility in making wide crosses. Among animals, crosses of varieties only are practicable, and, as a rule, related species, such as the horse, Equus caballus, and the ass, Equus asinus, can only be bred for 1 generation, as the offspring is sterile. Among plants, on the other hand, not only are wider crosses practicable, but many plants can be propagated from cuttings, while higher animals, including all domestic animals, cannot, and the only way of getting another individual, such as a mule, is to make the original cross again. Mules can be improved, therefore, only by improving the parents, or by crossing different breeds of horse and ass respectively. Crossbreeding contrasts. Contrasting results are sometimes obtained in crossbreeding by reversing the sexes of the two varieties mated. Thus the common mule is the offspring of the male ass and the female horse. From the father he inherits certain superficial traits, such as the small hoofs, somewhat scantier mane and tail, voice, and some peculiar mental characteristics, while from the mother come the deep-lying size and strength and symmetry. Some authorities claim that his intelligence is greater than that of either parent, although he lacks the dignity and poise of a good horse. Reverse the cross and the result is a hinny, more horse-like in contour and appearance, but with the smaller stature of the ass. The voice is that of the horse, and the animal is more apt to be fertile than the mule. The superficial characteristics and voice are in each instance those of the father, the stature, strength, and symmetry those of the mother. Among plants, the reverse hybridizing of the walnuts gives another instance of contrasts. The California walnut, Juglans californicea, male, and the black walnut, J. nigra, female, when propagated, give trees which increase in size twice as fast as the combined growth of both parents, with clean-cut, glossy, bright green leaves from 2 to 3 feet long, and odor like apples, but no nuts. From the male black walnut and the female California tree, however, there is produced a tree with larger nuts of a quality superior to that of either parent. Mechanical limits. The second limit to artificial selection is a mechanical one, for just as architecture, and especially bridge construction, have their limitations fixed by the strength of the building materials at the disposal of the builder, so a limit may be reached in nature. Speed among animals requires, among other characteristics, long and slender lower segments to the limbs, which reach their highest perfection in animals of the size of the average African antelope. With a larger creature, such as a horse, the impacts and strains to which the limbs are subjected are increased, not only because of greater force required to move a larger animal, but very rapidly with each added increment of speed. The modern race horse, with a speed of over 30 miles an hour, has just about reached the limit of strength on the part of bone and muscle, and a marked increase on the part of future animals is not to be looked for without proportionate risk of frequent injury to the horse. There are known cases in which a positive limit has been reached in attempting to modify organs through selection alone. End of Chapter 8b. Sexual and Artificial Selection. Recording by Jack Blake.
Chapter 9 of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lee Smalley. Organic Evolution by Richard Swann LULL. Chapter 9. Variation and Mutation. The fundamental basic prerequisite to evolution is undoubtedly variation, which together with heredity may be regarded as an undeniable fact. Therefore, as has been said, the cause of variation must be a contributory cause of evolution itself. But not all variations are alike, and only certain ones, apparently, are heritable. Hence, it is necessary to understand quite clearly what sorts of variations exist, since those that cannot be inherited can have no part in the evolution of a species, as they concern only the individual and not the race. Sorts of variations. Variations may be grouped into 3 sets of contrasting kinds, 6 in all, and any character may fall within one or more of the groups. They are: 1. Congenital or blastogenic variations, which are determined at conception. The term congenital in its etymology means existing at or doling from birth, but as applied to a variation it refers to the very beginning of an organism's existence. Blastogenic, on the other hand, means occurring in the germ plasm. Of course, the variation may not, often cannot, appear until later in life, as, for example, variations in adult size and proportions. Nevertheless, they are fluctuations which have been, as it were, foreordained, and will in the fullness of time come to pass, but may occur at any period from the beginning of embryonic life to the death of the organism. Congenital variations are intrinsic and not due to any external influence whatever, in contrast to the 2. Acquired variations, which are imposed upon the organism during its lifetime and are due to extrinsic influence. Under which of these 2 heads a variation should fall is often almost impossible to decide, except by experimental work, and sometimes not then. But the difference is of fundamental importance if, as we are told, congenital variations can only be inherited by the offspring. See, however, page 145. Examples of congenital variation are the occasional occurrence of supernumerary digits in man, the domestic cat, the horse, and other forms, for they cannot be due to accident or to any external influence, and are occasionally inherited through several generations. On the other hand, the loss of a digit in man through too close proximity to a circular saw would certainly be an acquired characteristic, and long series of experiments have proved conclusively that such variations are without the pale of heredity. Another example which occurs normally in nature would be the hive bees, in which the sex distinction between the workers and queens is an acquired variation, while that between drone and queen or worker is blastogenic. The queen is impregnated but once, the male elements being stored in the seminal receptacle, and used one at a time for the subsequent fertilization of the eggs. The workers build 2 sizes of eggs in the brood combs, in the larger of which the queen lays an unimpregnated egg, while that laid in the smaller cell is fertilized at the time of extrusion. From the unfertilized egg there arises invariably a drone or male bee, while the fertilized egg produces a potential female. Hence the difference between male and female bee, depending as it does upon impregnation or not, is congenital. The ultimate fate of the impregnated egg is subject to the whim of the workers, for while the vast majority of the eggs remain within the small worker cells and, being fed upon a meager and comparatively innutritious diet, develop into workers, the so-called neuters, which are in reality undeveloped females. A select few have their cells enlarged at the expense of the surrounding ones, and are fed upon highly nutritious royal pabulum, and ultimately develop into mature females or queens. It is said that even after 3 days of larval life, the humble worker, like the beggar maid of King Cophetua, may become a queen. Thus this variation, being imposed upon the animal during life, is an acquired one. Indeterminate and determinate. Variations may be further classified as 3. Indeterminate. Those fortuitous variations which are not subject to any law, but occur in any conceivable direction of change, or 4. Determinate, controlled by some unknown influence and confined to certain definite lines or directions of change, usually in an adaptive direction. Of the first of these 2 contrasting types there is no doubt, and they are the variations upon which the Darwinian factor of natural selection is supposed to operate. Illustrations are legion, as the comparison of any group of related organisms will show a variation of size, which embraces every dimension of space and combination thereof. Of determinate variations we are not so sure. Some claim that they have no real existence, that there is no such tendency to vary always in a given direction in successive generations, while others, notably Osborn and Eimer, consider these variations, which they call orthogenic, the important ones in evolution. What is apparently an example of determinate variations is that given by Kellogg, who described in 1006 the gradual but obvious change from one dominant type of color pattern to another in the leaf-eating beetle Diabrolica soror on the campus of Stanford University, California, during the last 10 years, as is shown by statistical variation studies. It is apparently proved that such change is not explicable on a basis of intra-species selection, nor can it be interpreted as a direct ontogenetic pertaining to the individual reaction in each succeeding generation to changing climatic conditions. The case is believed to be an example of definitive orthogenetic variation. Many paleontologists think they see repeated instances of orthogenetic variation, as they are, as a rule, so profoundly impressed by the adaptive nature of the evolutionary process and by the definitiveness of its direction, that they cannot regard the restraining or selective action of the environment as enough to keep the breed true. For example, the sure way in which the cusps of the teeth in ungulate animals appear in the course of time, so that one can predict the ultimate tooth pattern at the end of an evolutionary series with fair assurance. The rhinoceroses, on the other hand, and the totally unrelated Coney hyrax on the other, have teeth so similar that Roosevelt calls attention to the fact in his African Game Trails. This is an instance of convergence, which is often the result of what is apparently orthogenetic variation. The overgrown antlers of the Irish deer or the tusks of the Columbian mammoth (see chapters 12 and 34), which in each instance seem to be so far beyond the point to which natural selection would carry them, are considered as further instances of this form of variation. Continuous and discontinuous. Variations may also be classed as 5. Continuous, that is, small, abundant, and occurring in graded series. These, if also fortuitous, are the so-called Darwinian variations or fluctuations, to be acted upon by natural selection. They are generally quantitative rather than numerical variations, and the increment of change between successive generations is extremely slight. In contrast to the continuous are the 6. Discontinuous variations, which are mostly large or rare. They are also known as sports or saltations, and have been called mutations by De Vries, although the last word in its original usage by Wagen represented a different conception, in that De Vries's mutations may be contemporary in the offspring of a single generation, while Wagen used the term to include stages of transition between Linnaean species occurring in direct lines of racial ascent and never contemporaneous. The great mass of variations come under the head of continuous, the discontinuous ones being relatively rare, although many such have been recorded, as for example the numerous instances of variation from the standard number of digits in vertebrates. In mankind, 6, 7, or even 8 fingers to the hand have been observed, while the doubling of the foot has brought the number of toes as high as 9 on a side. Cattle and horses sometimes show multiple digits, and, on the other hand, pigs with the 2 median toes united into one perfectly formed digit, the so-called solid-hoofed pigs, occasionally occur. Sheep sometimes show 4 horns instead of 2, but the peculiarity is that instead of having one pair behind the other, as in the normal 4-horned antelope, Tetracerus quadricornis, the horns always stand in a single transverse series across the skull. One family of goats on an isolated farm near Bozen has 4 horns, which have been inherited for many generations. Bateson. All of these are instances of meristic or number variations, and are apt to occur wherever any structure is repeated in numerical series, in the number of segments of worms and arthropods, or in the vertebral column, ribs, and muscles, and in the number of appendages. Radially symmetrical forms such as sea anemones and starfish also exhibit it, and it frequently occurs among plants, especially in the flowers or leaves, as in the 4-leaf clover. Other instances of discontinuous variations are not of this numerical sort, but are mutations of color, form, and size. Such, for example, are the famous new saltations of Lamarck's evening primrose, which breed true and gave rise to De Vries's theory of the origin of new species by saltations or mutations. Some of these vary from the original in size. One is a smooth-leafed form with a more beautiful foliage, and so on. Another example is that of the short-legged ram, which suddenly appeared in Massachusetts in the year 1791. This ram proved to be a potent sire, capable of handing on his peculiarity to his progeny, and thus was the founder of a breed of so-called Ancon sheep, whose principal virtue was their inability to jump fences due to the brevity of their limbs. With the introduction of the more desirable merinos, the Ancon sheep disappeared. Causes of variations. The causes of acquired variations are apparent, for every modification which the organism undergoes in its lifetime in response to an external condition whatsoever comes under this head. The influence of abundance or scarcity of food in giving the animal a greater stature or one less great than that of its brethren, the influence of heat, cold, omnipresent enemies, or even the absence of exacting conditions. All these make themselves felt upon the individual in greater or less degree. But, as has been emphasized, this individual adaptation, however interesting it may be, is not evolution. Therefore, in our inquiry into the subordinate factors of evolution, it is not the cause of acquired but of congenital variations with which we are concerned. These have been summarized by Kellogg as follows. Origin of congenital variations. Three principal explanations, none experimentally proved or even fairly tested, are offered for the origin of congenital variations. 1. That there exists in the germ plasm an inherent tendency or capacity to vary so that there is inevitable variation in all individuals produced from germ plasm. This variation may be either fortuitous or fluctuating or follow certain fixed or determinate lines. 2. That amphimixis, i.e., biparental parentage, is the principal cause of variation, it seeming logical to presume that individuals produced from germ cells derived from the fusion of germ plasm coming from two individuals more or less unlike would differ slightly from either of the parental individuals. 3. That congenital variation is due to the influence of the ever-varying environment of the germ cell producing individuals. Objections. Inherent, however, does not clear up in any degree a phenomenon for which we are demanding a causo-mechanical explanation. It will readily be seen that this explanation merely begs the question and offers no real explication of this inherent tendency. For if such really exists, then it is not the cause of variation, but the cause of the tendency to vary, that is a primal factor of evolution, and until that is found we are as far from a true understanding as ever. The second explanation seems at first sight to be a very plausible one, for the mating of two plants or animals, especially if they vary from each other, will give offspring which possess certain characteristics of one parent and certain of the other, especially when from the nature of these characters they are mutually exclusive. It will also give rise to variations which combine those of the parents, and thus the offspring will differ from either. But the animals and plants are not produced in this way, for hosts of them have but one parent, either due to the simplicity of their organization, such as the asexual protozoa, or to the suppression of sex, i.e., parthenogenesis. Among protozoa it would be difficult to prove that any variations which could be observed were congenital. The parthenogenetic forms, on the other hand, are all relatively high in the scale of life, such for instance as the drone bees and aphids, both of which have been subjected to careful observation by Kellogg. The production of the drone bees from an unfertilized egg has already been emphasized, yet, as Kellogg shows, the variation, especially in the size, proportions, and venation of the wings, which cannot be acquired characters, is greater than among the bees, workers, and queens, produced from fertilized eggs and hence of biparental parentage. The plant lice or aphids are tiny creatures among which rapidity of multiplication during the season of abundance is highly important, and this is obtained by generation after generation, sometimes more than a dozen, being produced without male intervention, all of the individuals of each generation being parthenogenetic females which bring forth their young alive. Yet Kellogg says, in a series of 200 winged females of the mustard plant Lucei, produced viviparously by agamic, that's without, and marriage, stem mothers, the variation in wing size, in dimension of vein parts, in modification of the venation, in fore and hind wings, and the number of grasping hooks on the hind wings was studied. In all these characters a notable variation is apparent. No comparison was made with the variation of the aphids of the early spring generation that comes from eggs of bisexual parentage. But it was apparent that in the variations which were observed there was sufficient range in extent and character to serve natural selection as a species-building basis, if the familiar fluctuating, continuous, or Darwinian variation ever is sufficient for this purpose. Amphimixis is not only not necessary in order to ensure Darwinian variation, but there is no evidence, that I am aware of, to show that it increases this variation. There is, on the other hand, a little evidence, some of it presented herewith, to show that such variation occurs, whether the offspring be of uniparental or biparental ancestry, and to show that this variation is no greater in amphimixis than among parthenogenetically produced individuals. Yet the neo-Darwinians, headed by Weismann, explain variation as a product of sex, and sex as a product of the necessity for variation. The third cause of congenital variation, that of the influence of the ever-varying environment, will be discussed more in detail in a later chapter, Chapter 11. It suffices to say here that we know no means whereby the character of the surrounding medium can make itself felt upon the germ cell itself, which has been shown to be the physical basis of heredity. So thoroughly is the latter apparently insulated from all outside influences. In the protozoa such influence is understandable, but not in the higher and more complex forms. Then, too, variations arising in this way would approach perilously near being acquired and not congenital ones at all, unless they manifested themselves only in succeeding generations. Theory of germinal selection. A theory of germinal selection was proposed by Weismann in 1895, and more definitively in 1896. He called it a spring of definitely determined variation, and it was invoked to explain, first, how not only degeneration, physiological, but rudimentation, morphological, occurs in panmixia, i.e., cessation of natural selection. Second, why exactly those variations needed for the development of a certain adaptation appear at the right time. Third, how correlation of adaptation comes to exist. And fourth, how variations are able to develop orthogenetically along a definite line, without depending on the necessity of a personal selection raising them step by step. In 1002, Weismann further applied the theory to the explanation of monsters, of sports, of suddenly appearing sex characters, of specific talents, and still other hitherto unsatisfactorily explained phenomena. Weismann conceives the protoplasm of the cell nucleus to be composed of units called biophores. These biophores can also migrate out into the cytoplasm surrounding the nucleus, which are the bearers of the individual characters of the cell. The total character of any cell, its form, makeup, and special properties, is determined by the totality of its biophores. These biophores are not, however, such simple structures as the atoms of the chemist. Indeed, they are to be looked on as supermolecules, as complex groups of chemical molecules, of determined character and arrangement. Moreover, as these biophores are life units, they possess the essential characteristics of life, that is, the capacity to assimilate food, to grow, and to reproduce themselves by division. The number of different biophores is almost inconceivably enormous, for it must equal the possibilities of variety in character exhibited by, or capable of being exhibited by, all the cells of the body. But as each biophore is made of many complex molecules which may vary among themselves, and also vary in their structural relation to each other inside the biophore, it is not difficult, perhaps, to imagine the possible variety of biophores to be equal to the possible variety of cell characters. These biophores are conceived to be united into fixed, indissoluble groups called determinants, each determinant containing all the biophores necessary to determine the whole character of any one kind of cell. Like the biophores, the determinants can assimilate food, grow and multiply by division. While in each specialized body cell there needs to be but a single determinant, namely one of the special kind conforming to the special kind of cell, in the germ cells there must be conceived to be every kind of determinant, which may be found in all the body cells taken together. But, fortunately, by virtue of the determinant's capacity for multiplication, it is not necessary to assume that there exists in the germ a determinant for every cell that is to develop in the body, but only one for every different kind of cell. All cells exactly alike can be supplied with similar determinants by the multiplication of the proper kind. Now Weismann's theory of germinal selection rests upon the assumption of a competition or struggle of the determinants in the germ plasm for food and hence for opportunity to grow, to be vigorous and to multiply. The germ cells derive their food, as do the other cells and tissues of the body, from the general food streams circulating around and through the cells. Weismann, recognizing the absolute principle of slight variation everywhere in nature, it is practically impossible to conceive of identity, believes that the initially slightly stronger or more capable determinants will be able to take up larger supplies of food, even to the extent of lessening the supply for neighboring determinants, perhaps to the degree of starvation. Indeed, he suggests a reason for the initial slight variations in vigor of the determinants in the probability that the food will reach the various determinants in slightly, purely fortuitously variable quantity, so that the first inequality in vigor of the determinants will depend on the fortuitous variability of food supply, while thereafter the variability in the determinants thus produced will enable the stronger ones to draw to themselves or take up more food, and thus accumulate determinately the initial fortuitous inequality. Kellogg. End of Chapter 9. Recording by Lee Smalley.
Part 2, Chapter 10a of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. Organic Evolution by Richard Swann LULL. Chapter 10a. Heredity. With heredity, again as with variation, we are dealing with a fact. The laws of heredity and whether or not certain characters are heritable, however, are subjects for debate. Heredity is thus defined by the Century Dictionary: the principle or fact of inheritance, or the transmission of physical and mental characteristics from parent to offspring, regarded as the conservative factor in evolution, opposing the tendency to variation under conditions of environment. Heredity has also been defined as the rule of persistence among organisms, each organism being likely to resemble its parents. By some writers, heredity is considered the force which compels the resemblance; by others, the process whereby the offspring comes to resemble its immediate ancestry. Of course, while partaking of the nature of each parent to a certain extent, the organism through them partakes also of the nature of its grandparents, and so on back in ever diminishing degree. The problem of inheritance, especially the means by which it is brought about, is one of the most interesting in biology. Formerly the fact of inheritance was considered self-sufficient. Now inquiry into the mechanism of heredity has thrown much light upon the problem of evolution itself. Physical basis of heredity. How the inheritance is handed down has been investigated by a number of workers, some of whose results follow. Darwin's pangenesis theory. Darwin realized that his doctrine of natural selection lacked completion if he merely accepted the fact of heredity at its face value without trying to learn in what way mental or physical traits or new variations got into the egg or sperm and thus were borne on to the next generation. He therefore devised the theory of pangenesis, according to which every cell of every tissue and organ of the entire body produces minute particles called gemmules, in which each instance partake of the nature of the cells producing them. These gemmules may circulate throughout the entire organism, but finally congregate in the reproductive products or in buds, so that each germ cell or each bud (asexual) capable of giving rise to a new individual would be in a sense a miniature replica of the parent's body, and would thus be capable of developing into the same kind of a body even in minute detail. Darwin thought that sometimes certain of the gemmules might lie dormant for several generations and then develop, bringing out in an individual its ancestral atavistic traits. If this theory of gemmules were true, it would lead to the acceptance of the teaching of Lamarck or even of Buffon, because under such circumstances the inheritance of acquired characters gained by the parent during its lifetime would be entirely feasible, for such characteristics could be impressed upon the germ cell as readily as could the variations which we call congenital. Later research, however, proved that such a theory has no basis in fact, and biologists soon began to search for a substance which could be a physical basis for heredity, just as the protoplasm which makes up the bulk of all organisms is the physical basis of life. And while Nageli and Weisner were convinced that there was such a substance, it remained for August Weismann, for nearly 50 years professor at the University of Freiburg, to identify and demonstrate its existence. Weismann's germplasm theory. Weismann's germplasm theory was published in 1892 in a volume called Das Keimplasma, wherein he brought together the accumulated observations of the numerous contemporary students of cell biology and utilized them for the development of his somewhat speculative theories. This volume Crampton calls an immortal foundation for all later work on inheritance. The essential principles of the germplasm theory are given by Crampton as follows. The chromatin of the nucleus contains the determinants of hereditary qualities. In reproduction, the male sex cell, which is scarcely more than a minute mass of chromatin provided with a thin coat of protoplasm and a motile organ, fuses with the egg, and the nuclei of the two cells unite to form a double body, which contains equal contributions of chromatin from the two parental organisms. This gives the physical basis for paternal inheritance as well as for maternal inheritance, and it shows why they may be of the same or equivalent degree. When now the egg divides, at the first and later cleavages, the chromatin masses or chromosomes contained in the double nucleus are split lengthwise, and the twin portions separate to go into the nuclei of the daughter cells. As the same process seems to hold for all the later division of the cleavage cells whose products are destined to be the various tissue elements of the adult body, it follows that all tissue cells would contain chromatin determinants derived equally from the male and female parents. As, of course, only the germ cells of an adult organism pass on to form later generations, and as their content of chromatin is derived not from the sister organs of the body, but from the original fertilized egg, there is a direct stream of the germ plasm which flows continuously from the germ cell to germ cell through succeeding generations. It would seem, therefore, that the various organic systems are, so to speak, sister products in embryonic origin. The reproductive organs are not produced by the other parts of the body, but their cells are the direct descendants of the common starting point, namely, the egg. As the cells of the reproductive organs are the only ones that pass over and into the next and later generations, it will be evident in the first place that the germ plasm of their nuclei is the only essential substance that connects parent and offspring. This stream of germ plasm passes on in direct continuity through successive generations, from egg to the complete adult, including its own germ cells, through these to the next adult, with its germ cells, and so on as long as the species exists. It does not flow circuitously from egg to adult and then to new germ cells, but it is direct and continuous, and apparently it cannot pick up any of the body changes of an acquired nature. Now we see why individual acquisitions are not transmitted. The hereditary stream of germ plasm is already constituted before an animal uses its parts in adult life. We cannot see how alterations in the structure of mature body parts through use and adjustment to the environment can be introduced into it to become new qualities of the species. Weismann has produced so very logical a theory that no one seriously questions the truth of it today, and yet there are certain things in connection with it which we do not clearly understand. Weismann divided all of the bodily protoplasm into the germ plasm of which we have been speaking and the somatoplasm, the latter constituting all of the other protoplasm of the body. While the germ plasm may be handed on, both its substance and life, to future generations, and is also the source of all the somatoplasm of a body, the latter is normally confined to the individual and at his death ceases to exist. The somatoplasm is therefore the mortal portion of an organism, the germ plasm potentially immortal. However, in lower forms, such as the protozoa, not only is the chromatin of the nucleus, germ plasm, handed down, but the entire body of the organism may be divided between the offspring. Still other protozoa which reproduce by budding give up only a portion of their nucleus and cytoplasm to their children, and the same thing is true of all invertebrates which reproduce asexually, or in plants which may be propagated by cuttings. In so high a plant as the hothouse begonia the normal method of reproduction is by the production of seeds, hence by the transmission of germ plasm to offspring, as Weismann has said, but a small piece of begonia leaf, which consists apparently only of somatoplasm, can be made to produce an entire plant, stem, leaves, flowers, seeds, germ plasm and all, and if the seeds be planted they will continue the inheritance which was also true of the piece of leaf. In this case, and the same would be true of the willow, potato, or any of the other countless plants which can be propagated by cuttings, not only is the germ plasm the vehicle of inheritance, but apparently certain portions of the somatoplasm as well, and furthermore the latter may produce not only all of the organs and tissues of the entire plant, but new germ plasm also. This indicates therefore one of two things, either that each body cell has retained its potential quota of hereditary characters, or that portions of the germ plasm are widely distributed through the tissues of the organism. Osborn. In the higher animals, on the other hand, this is a relatively rare occurrence. Sponges have been propagated by cutting the entire body into small pieces, each one of which will produce a new sponge, but here there is little difficulty, as the sponges exhibit a very lowly physiological differentiation among the cells, and probably every piece which is successfully grown into a complete sponge had some of that portion, the mesoderm, which normally gives rise to the reproductive bodies. Starfishes can also reproduce lost parts to the extent of forming an entire animal, if one arm and a portion of the disc be present. From the latter, however, the reproductive bodies normally arise, so here again, in contrast to the begonia, an actual portion of the ancestral germ plasm may be handed on. Weismann's theory seems therefore to be true of all higher animals, but not necessarily so of plants. In the latter, while the germ plasm, when it is passed on, carries the inheritance, there must be some other vehicle of heredity when it is not. It has been argued that all plants propagated by cuttings are in reality one individual and do not represent successive generations. This may be true, but does not contradict the fact that new germ plasm can be derived from a piece of leaf or of tuber or stem, as the case may be, and thus apparently does not represent a continuous flow from germ plasm to germ plasm without a break. Latent and potent qualities. The sum of the inheritance of any organism contains many qualities, not all of which are externally manifest in the individual. This is especially true of two contrasting qualities which are mutually exclusive. For instance, a child, one of whose parents is tall and the other short, may have an ultimate stature which is in a sense a compromise between the two, or on the other hand, he may be tall and yet nevertheless have the power of transmitting to his offspring the short stature which he inherited along with his tallness, but which was latent within him. The qualities which are manifest are therefore potent or dominant, while the invisible ones are latent or recessive. The latter may be none the less real in heredity. A more remarkable instance is found in the drone bee once more, which, as we have seen, comes from an unfertilized egg, and therefore has no father, but a mother only. Nevertheless, all his qualities of maleness, his reproductive organs, size, and any other characteristics whatsoever which distinguish him from the female, including his inborn aversion to labor, are inherited from his mother, the queen bee. She therefore had these qualities present in every one of the germ cells which she inherited from her father, but those which are fertilized, in other words, those which have the male qualities latent and the female dominant, receive the stimulus which brings this about from the male. Therefore, if the bee has no father, it exhibits fatherly qualities; if it has a father, it does not. Another remarkable instance of latent inheritance is the famous racehorse Arion, a trotting stallion which made a record of a mile in 2 minutes 10 3/4 seconds to a high-wheeled sulky as a 2-year-old, later reducing it to 2 minutes 7 3/4 seconds when the pneumatic tire sulky was invented. He was sold for $125,000, at that time the highest price ever paid for a trotting horse, and his new owner expected to make a fortune with him as a sire, and to establish a line worthy of his name. Strange to say, his progeny never developed any speed, but his daughters, almost without exception, have produced some wonderful trotting colts, the speed lying dormant for one generation, and to reappear in the second. It is said that in appearance and otherwise Arion possessed many feminine characteristics. Atavism. This leads us to the problem of atavism, or reversion to ancestral type. Under atavism have been included what Delage calls 3 very different things. They are 1. Family atavism, where in one family individual characters are transmitted in latent condition for several generations and then suddenly reappear. The case of Arion is an instance in point, but would be better were there were several intervening generations rather than but one. 2. Race atavism, the more or less regular reappearance in a race of characters of another race from which the first may have been derived. Such, for example, are the instances of the profuse development of hair on the face and body which occasionally occurs in man, as in the Russian dog-man Adrian Jeftijew. 3. Atavism of teratology, the appearance in a race of abnormal characters which, however, are normal in other supposedly ancestral races. Instances of this are the external ears sometimes found in porpoises, in which such structures are normally lacking. The ancestral terrestrial atavus of the whales, to which group the porpoise belongs, undoubtedly had these structures, which were gradually lost among other adaptations to aquatic life. See Chapter 20. Fistulae, or permanent abnormal openings of the neck, which sometimes occur in the human subject, have been considered as relics of the ancient gill slits of our piscine ancestry. See Chapter 37. In summation, it may be said that less marked cases set down to atavism may be instances merely of normal regression. Many cases of more abnormal structure, which are really due to abnormal embryonic or post-embryonic development, are set down to atavism, as for instance the cervical fistulae mentioned above. It is also used to imply the reversion that takes place when domestic varieties are set free, to interbreed indiscriminately, and when species or varieties are crossed. Atavism is, in fact, a misleading name covering a number of very different phenomena. Encyclopaedia Britannica. Telegony. There is a very widespread feeling among breeders of domestic animals, especially of the finer strains, that the first male bred to a female will influence not only his own offspring, but subsequent offspring by another sire. Up to the end of the last century, Lord Morton's experiments with a male quagga and a young chestnut 7/8 Arabian mare were regarded as affording strong evidence of this theory. These experiments were repeated as accurately as possible in 1899 by J.C. Ewart. The initial one was the impregnation of a mare, Mulatto, by a Burchell's zebra. The offspring, Romulus, resembled the richly striped Somali zebra more than his sire. Later, Mulatto was bred to a pure Arab stallion, but while the foals showed traces of stripes, they were decidedly less suggestive of zebras than were purebred foals of a near relative of Mulatto, which had never seen a zebra. Ewart considers the evidence inconclusive, and believes that the apparent instances are due to other factors. Telegony has been theoretically explained in 2 ways. 1. Spermatozoa, or portions of spermatozoa from the first sire, may occasionally survive within the mother for an abnormally long period. 2. The body or the reproductive cells of the mother may be influenced by the growth of the embryo within her, so that she acquires something of the character of the sire. The first supposition has no direct evidence to support it, and is made highly improbable from the fact that a second impregnation is always necessary, except in forms like certain insects, in which one pairing, during which the sperms are stored up in a special receptacle, serves for a lifetime of egg production. Against the second supposition Pearson brings the cogent empirical evidence that the younger children of the same sire show no increased tendency to resemble him. Nevertheless, if telegony is true, all we can deduce from it is that in some manner the normal characteristic ova are modified by the foreign male germ cells without either contact or fertilization. Osborn. Jordan and Kellogg think it probable that the phenomenon called telegony have no real existence. Prenatal influence. There is a widely held belief that in mammals a special additional formative influence is exerted by the mother in the period between conception and birth. Maternal impression does not refer to the results of good or poor nutrition, which are discussed below, but to the development in the unborn young of definite anomalies such as birthmarks and the like. While instances are numerous, they have never been given accurate scientific research and are still open to question. Nevertheless, many high authorities and most physicians believe in prenatal influences, and the belief is very old, as the first recorded instance is in Genesis chapter 30, verses 32 to 42, dating back to the time of the patriarch Jacob, about 1730 BC. Jacob was to receive as his share of Laban's flocks and herds all the speckled and spotted cattle, and the brown cattle among the sheep, and the spotted and speckled among the goats, while Laban was to retain such as were not so marked. So Jacob took him rods of green poplar, and of the hazel and chestnut tree, and pilled white streaks in them, and made the white appear which was in the rods. And he set the rods which he had pilled before the flocks in the gutters and watering troughs when the flocks came to drink, that they should conceive when they came to drink. And the flocks conceived before the rods, and brought forth cattle ring-streaked, speckled, and spotted. But Jacob was shrewd enough to put the rods before the eyes of the stronger cattle, but when the cattle were feeble, he put them not in, so the feebler were Laban's and the stronger Jacob's. Transmission of parental conditions. One thing which must be distinguished very clearly from heredity is the transmission of characteristics which are not those normal to the race, but those peculiar to the parent, such for instance as the malnutrition of the embryo due to the weak or impoverished condition of the mother. Heredity hands down qualities of the parents as they should be, transmissions as they are. The one is concerned with the nature, the other with the nurture of the individual. In breeding, the potentially best is often better than the actually best, as an old racehorse sire will produce speedier colts than a young and vigorous cart horse. Nevertheless, the feebleness of either parent through disease or debauchery may produce offspring with so heavy a handicap that they are never able to overcome it and cope with others of potentially inferior stock. Insufficient nutrition both before and after birth may neutralize the most vigorous inheritance. End of section 2, chapter 10a. Part 2, chapter 10b of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. Organic Evolution by Richard Swann LULL, Chapter 10b. Sex Control. The problem of sex control is another vexatious one, which, although many theories have been advanced, has never been satisfactorily solved. But the fundamental differences in sex are not so great as might be imagined, as the organs of the one are often represented as rudiments in the other, the differentiation coming about mainly through division of labor between male and female in the production and nutrition of offspring. How each sex is determined is also not clear. The germ cell may be either sexless or bisexual, but each animal soon becomes male or female. Occasionally there occurs what is known as hermaphroditism, that is, a combining of the sexes in one individual. Among animals this is rare and is almost invariably found in sedentary or semi-sedentary types. For example, the European oyster is hermaphroditic, while its American ally is not. Barnacles, sedentary crustacea, are often bisexual, and sometimes there may be seen within the body of the hermaphroditic female a small, so-called complemental male, evidently in process of elimination from the race. The snail and earthworm, which, though not sedentary, have very limited powers of movement, also have the sexes combined, while in plants separate sexes are the anomaly, hermaphroditism being the rule. Among invertebrates, the proportion of the sexes varies enormously. Among vertebrates, on the other hand, they are generally nicely balanced. A very slight influence may determine the sex of the developing animal, but what it is rarely known. Among hive bees, as we have seen, unfertilized eggs invariably produce males, whereas among aphids parthenogenesis gives rise to females only until autumn, and then to both sexes, while the fertilization of the winter egg, as in the case of bees, produces females only. Here the appearance of males, and the same is true of wasps and many other insects, is a harbinger of cold and inclement weather, and may sometimes be postponed by artificially continued uniform conditions. For example, the scale insects (Coccidae) found in a state of nature normally produce the males toward the end of the growing season, and this is also true of some types resident upon hothouse plants (Pulvinaria). On the other hand, certain hothouse species far from their native habitat have been observed for years without the discovery of a single male. Among certain animals, possibly in the forms just discussed, variation in nutrition is a sex determinant, but sometimes abundance will produce females and scarcity males, and again the reverse may be true. Whether or not this is a factor among mankind is not proved, although it is a popular belief that in times of war or famine the production of male children is preponderant. However, this is not borne out by the study of the vital statistics of France or the United States. Homologies and analogies. The distinction between homologous organs which have the same structure and origin, in other words, such as our morphological equivalents, and analogous organs which have a similar use or function but which may not be historically identical, is often of the utmost importance. Homologous organs imply blood relationship on the part of their possessors and are therefore the basis for classification. Analogous organs, on the other hand, while they necessarily have the same function, may have their origin in very unlike structures and may be very misleading to the systematist. Such, for example, are the various types of wing whereby at least 4 different groups of animals, 3 vertebrate and 1 invertebrate, have attained true flight. In the vertebrates, the birds, bats, and the extinct pterodactyls have each independently developed a wing, but in every case it is the modified forelimb equivalent to the arm and hand of man. Hence the wings of bat and bird and reptile are both analogous and homologous, as they are historically the same organ and also have the same function. The wings of the insect, however, are not the same structure at all, but are modified outpushings of the body wall which have become expanded into thin membranous plates, stiffened with veins and ribs, movably articulated to the body, and endowed with muscles to sustain their owner in the air. Hence the wing of the insect is analogous to those of the bird and the bat, but not their homologue at all. This matter of homologies may be carried further, for not only do the forelimbs of forms so remote in habits and habitat as a salamander, ichthyosaur, bird, and whale agree in being the homologues of one another as a whole, but the individual bones and even the principal muscles of one limb are homologous with those of another. Classification, which, as has been said, should show true phyletic relationship, is based upon the resemblances and dissimilarities of homologous structures. Vestigial organs. Vestigial organs are such as are not fully developed and are to be contrasted with rudimentary structures which are in process of evolutionary growth and are thus progressive, whereas the vestigial organs are retrogressive and are tending toward diminution and ultimate loss. Rudimentary horns are often observed on the head of fossil ungulates such as the titanotheres and rhinoceroses, whereas the splints on either side of the cannon bone of a horse's foot are vestiges of formerly useful lateral toes. The vestigial organs are therefore of historical importance and would not exist, especially where their old-time function has entirely ceased, were it not for heredity. Of such are the vestigial hind limbs seen in the python and other related snakes. Externally, they are mere spurs on either side of the vent. Internally, they are seen to contain several of the bones normal to a fully formed limb: ilium, femur, tibia, and claw. Embryo whales often exhibit the full coat of hair of their ages vanished forebears, and also, as Kukenthal has shown, the relics of hind limbs as well developed buds. At birth, however, the hair has been shed except for a few bristles about the lips, and all external trace of hind legs has gone, there being only a few bones, as in the python, buried deep within the mass of the creature's flesh. Mankind, according to Wiedersheim, has no fewer than 180 such relics, which will be discussed somewhat at length in Chapter 37. Atrophy of parts. Atrophy of parts, which results in these vestiges, has been variously accounted for, the 3 or 4 principal theories being as follows. 1. Panmixia, or cessation of selection, the organ being no longer held up to a high degree of efficiency. Organs once useful, from change of environment or of habits, are no longer of value, so that natural selection ceases to act upon them, and animals born with the organs somewhat defective or in a condition below the average would not necessarily be killed off in the intraspecific strife, and would therefore be as likely to mate and keep on producing offspring as those with the organ of average or better than average development. This indiscriminate breeding or panmixia would obviously lead to a loss of high condition on the part of the organ, but how far the latter would degenerate, and whether cessation of selection would ever cause it to disappear entirely, as the limbs of most serpents have, is open to serious question. This leads us to the second possibility. 2. Reversal of selection. Of this factor there can be little doubt, and it may well work in connection with panmixia, when a useless organ becomes a burden, to complete what the latter has begun. This theory postulates a change of condition or habit under which an organ previously beneficial may become actually detrimental to the animal. It differs from cessation of selection, which implies that the structure is no longer of selection value, hence its presence or absence is entirely immaterial. Here the absence of the organ is to be desired, therefore it is of negative selection importance, and not merely an indifferent thing. A very graphic instance wherein reversal of selection has been operative is that of the wingless beetles found on certain oceanic islands. The interference is that while in a wide environment wings are so distinctly advantageous that natural selection would tend to strengthen them toward greater and greater perfection, in a small islet they would become a distinct menace, often causing their unlikely possessors to be swept overboard and drowned, and though the laws of chance would operate as usual, nevertheless in the long run the individuals with the strongest powers of flight would be placed in the greatest jeopardy. Hence natural selection, in opposition to its usual results, would weed out what in most conditions would be the fitter, leaving the less fit to survive and reproduce their kind. It is not therefore a reversal of the process of natural selection, but a reversal of its results, due to diametrically opposed conditions. 3. Inheritance of the results of functional disuse. This was apparently the simplest and most logical way to account for the atrophy of parts in evolution until Weismann's epoch-making work cast doubt upon it, for it is a well-known fact that with the individual, use strengthens an organ, while disuse causes it to weaken and partially atrophy. Witness the Hindu fakirs, who hope to acquire a state of singular holiness through the mortifying of the flesh. Some of them keep the arms raised permanently above the head, with a consequent shrinkage of the muscle and stiffening of joint until the limb could not be used if they would. But as Weismann has shown, such modifications are those of the mortal somatoplasm, and cannot apparently impress themselves upon the race. How, then, can this explanation account for the evolutionary atrophy of parts, unless, as Osborn has said, there is still some factor of heredity which we know not of? 4. Orthogenetic variations, if such exist, may account for the atrophy of organs as readily as for their increase, and for those who believe in determinate variation, the continued tendency to diminution, generation after generation, would suffice. If orthogenetic evolution has caused the continual strengthening and lengthening of the median toe of the ancestral horses, it can also account for the reciprocal shortening and weakening of the lateral ones until they ultimately disappear. Summary. Thus, cessation of selection might readily account for the initial reduction of an organ, but probably only to the condition of fluctuating around a mean, and would never cause its total atrophy. Reversal of selection under conditions where the organ is not only no longer useful but an actual menace would be a potent cause for its elimination. Inherited effects of disuse cannot be proved, nor are determinate variations generation after generation of unquestionable occurrence. Consider the way the splint bones of the modern horse vary in every conceivable direction of change, with no very marked tendency toward reduction since the Pleistocene. Characters which are not heritable. Acquired characteristics. Long observation has shown that certain variations among animals are not heritable. These are 1. Acquired characteristics due to disease, mutilation, use, or disuse of parts, and changes due to the direct action of the environment upon the organism, such as the loss of color on the part of forms living in the dark. This question will be discussed in detail in Chapter 11. 2. Characters peculiar to sex, which are inherited not by all but by the appropriate sex. That is, the traits which are manifest, for in the case of the fatherless drone bee it will be remembered that as he inherited all of his traits, masculine and otherwise, from his mother, she must have borne all of the male characteristics within her but in latent condition. This is also shown by the fact that emasculated males are apt to show feminine traits, as with the domestic horse, wherein a gelding and a mare may make a very well-matched pair, but not as a rule either a gelding and a stallion, or the latter and a mare. It may well be, however, that it is not so much the feminine characters which the gelding shows as the lack of masculine, which nevertheless are within the sum of its inheritance. 3. Certain parental characters, apparently not inherited, really have been received but lie in latent condition, to reappear in some future generation, as in the case of Aryan's speed. End of chapter 10b. Part 2, Chapter 10c of Organic Evolution. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. Organic Evolution by Richard Swann LULL. Chapter 10b, Heredity. Laws of Heredity. Students of heredity have worked out a few definite laws of inheritance with which, under certain conditions, organisms seem to conform. The principal ones are Galton's law and that of Mendel. Galton's law. Galton's law of ancestral inheritance was based upon two main sources: the study of the carefully kept pedigree book of the kennels of the Basset Hounds Club, whose records extended over a period of 22 years, and a study of inheritance in the British peerage, of which very complete genealogical records have been kept. Galton's statement is that any organism of bisexual parentage derives 1/2 of its inherited qualities from its parents, 1/4 from each parent, 1/4 from its grandparents, 1/8 from its great-grandparents, and so on. These successive fractions, whose numerators are 1 and whose denominators are the successive powers of 2, added together, equal 1, or the total inheritance of the organism, thus: 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, and so on, equals 1. Jordan and Kellogg. This has been shown to be only a close approximation of the actual inheritance relations, but while receiving very general acceptance among biologists until the rediscovery of Mendel's law (see below), it is now thought to be too simple, and it is not known whether it is in agreement with Mendel's formula or not. Another consideration is due to the fact that, as Brooks has shown, each person has 2 parents and 4 grandparents, but beyond that the geometric progression may not hold, since even in a country like ours, which draws its population from the 4 corners of the earth, each of the 8 great-grandparents is not always a distinct person, for when parents are cousins, this number may be reduced to 6, 5, or even 4 instead of 8. In older, more settled communities where the people stay at home generation after generation and marry neighbors, a person whose ancestors have transgressed none of our social laws may have a minimum ancestry of only 4 in each generation. The maximum and minimum fixed by our customs would be as follows for 10 generations: 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256 plus 512 plus 1024 equals 2046. 2 plus 4 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 equals 38. Few persons who can trace their ancestry for 10 generations with completeness are descended from 1024 distinct persons in the 10th generation, and in old and settled communities of simple folk the number is much smaller. In the long run, the number of ancestors in each generation is determined by the average sexual environment, and it must be a small and pretty constant number, a fact which apparently has not been fully recognized by most students of heredity. Brooks. Mendel's law. That which we have come to call Mendelism was first discovered by an obscure Austrian monk, Gregor Johann Mendel of Brunn, who was born in 1822 and died in 1884. Mendel wrote but little, but wrote that little with admirable clarity of thought. Nevertheless, it was apparently beyond the understanding of the wise men of his day, among others the great German botanist Carl Nageli, whom Mendel strove particularly to impress with his ideas. The reason was that Mendel was in advance of his time, and the discovery of several biological principles, then unknown but now clearly understood, was necessary before a full understanding of his theories could be reached. Long after Mendel's death in 1900, his law was independently rediscovered simultaneously by three men, De Vries, Correns, and Schermach, and it speaks highly for their chivalry that, honoring the all but forgotten monk, they called their newfound law Mendel's rather than their own. Castle. Bateson discovered the application of the law to animals as well as plants. Mendel's law was based upon a series of experiments carried on in the seclusion of the monastery garden upon pedigree cultures of peas (Pisum sativum) and other plants, and his results were published in 1865 in the Abhandlungen of the Natural History Society of Brunn. He found in the course of his experiments that the pea showed a number of pairs of contrasting characters, of which 7 are recorded, one of each pair being dominant, the other recessive. These characters were: 1. Shape of ripe seed, whether round or angular and wrinkled. 2. Color of endosperm cotyledons, whether some shade of yellow or a more or less intense green. 3. Color of seed skin, whether various shades of gray and gray-brown, or white. 4. Shape of seed pod, whether simply inflated or deeply constricted between the seeds. 5. Color of unripe pod, whether a shade of green or a bright yellow. 6. Nature of inflorescence, whether the flowers are arranged along the axis of the plant or are terminal and form a kind of umbel. 7. Length of stem, whether about 6 or 7 feet long or about 3/4 to 1½ feet. Jordan and Kellogg. The results of a large number of crosses showed but only one of each of these characters in the offspring in the first generation, proving that in each pair one character was dominant and the other recessive. By letting the crossbred peas fertilize themselves, Mendel raised another generation in which the proportion of dominant to recessive characters was with very considerable regularity in the ratio of 3:1. In other words, the proportion in the offspring of crossbreeds was 75% dominant and 25% recessive. These were again self-fertilized in the offspring of each separately sown, with the result that, whereas from recessives he obtained only recessives in any number of succeeding generation, the offspring of the dominants were not at all alike, in that they gave first pure dominants, which, like the recessive, produced pure dominants indefinitely, and second, crossbreds, which, while appearing dominant, nevertheless contain recessive characters, and when self-fertilized produce once more dominants and recessives in the ratio of 3:1. But of the apparent dominants, one only was pure to every 2, which, although mixed, showed only the dominant trait. Therefore, by self-fertilization the original crossbreds produced out of every 100, 25 dominant to 50 dominant recessive to 25 recessive. Like the pure recessives, the pure dominants are thenceforth pure. The 50 dominant recessives again have mixed offspring, 1 dominant to 2 dominant recessives to 1 recessive, apparently 3 dominant to 1 recessive. It was found that by working with combinations of 2 characters the results were the same, although naturally more complicated. Mendel's interpretation of his law is based upon the theory of the purity of the germ cells and is as follows. In the young of the first generation, after a cross mating, but one of the contrasting characters will show in the body makeup, but when they form the germ cells, the 2 parental characters will be present, but only one in any one germ cell. Therefore each pollen grain in each ovule cell will carry but one of the contrasting characters. If this be true, and if on the average the pollen in ovule cells were about equally divided as to the 2 characters, then by miscellaneous and random mating according to the laws of probabilities, we should get 25% pollen dominance plus 25% ovule dominance, 25% pollen recessives plus 25% ovule recessives, 50% of each kind with each other. Therefore, out of every 4 crosses we should get 1 pollen dominant mates with 1 ovule dominant, produces dominant. 1 pollen recessive mates with 1 ovule recessive, produces recessive. 1 pollen dominant mates with 1 ovule recessive, produces dominant. 1 pollen recessive mates with 1 ovule dominant, produces dominant. Produces 3 dominant to 1 recessive. Thus, the so-called Mendelian laws of heredity refer to 2 laws of inheritance. 1. How inherited characters are actually distributed. 2. The fundamental cause lying in the germ plasm for this particular kind of distribution. Since 1902, a great deal of experimentation has been carried on independently by many botanists and zoologists, and the results are everywhere practically the same. Work has been done on rabbits, guinea pigs, fowls, beetles, and silkworms by Castle, Davenport, Bateson, Kellogg, and others, and while certain inconsistencies have been found which will limit the application of Mendel's law, they do not lessen its apparent importance. Castle has experimented with guinea pigs with some interesting results, the contrasting characters being white or black color, short or long hair, smooth or rough coat. In mating those of contrasting colors, he finds that in the first generation all of the offspring appear black, which is the dominant color. When 2 of these are mated, their offspring, if 4 in number, will contain 3 black and 1 white individuals. The latter, mated with a white individual, will produce white forever. Of the black, but 1 is pure, the others having combined characters, of which, however, only the dominant one is visible. The pure black mated with another pure black would have black offspring forever, while if the crossbreds were mated, their offspring would be in the ratio of 3:1, and so on. Castle's explanation follows. When the egg of a black guinea pig is fertilized with the sperm of a white one, or vice versa, protoplasmic constituents unite which in one case are able to produce a black coat, in the other a white one. These constituents, whatever they are, evidently separate from each other and pass into different cell products when the germ cells of the crossbred individual ripen. Half the sperms, accordingly, of the crossbred black individual bear black, half white, none both, and the same is true of the eggs. Experiment proves conclusively that this is so. Blackness and whiteness behave in crosses like indivisible units. They may be brought together repeatedly in crosses, but always separate again at the maturation of the gametes (conjugating bodies). We call them unit characters. Black is a positive unit, presence of black pigment; white its corresponding negative, absence of black pigment. With reference to the character of the coat, rough is a unit character dominant over smooth, while short hair is dominant over long, the length of the hair being independent of its color or roughness; hence a short-haired color animal mated with a long-haired white one produces only short-haired colored offspring, which, bred inter se, produce in the next generation young of 4 sorts: 1 long white, 2 short dark, 3 long dark, and 4 short white. Recombinations in such ways can be accounted for if we suppose each different unit character to have its basis in a different material body within the cell, perhaps in a different chromosome or part chromosome. A further interesting experiment was the transplanting of the ovaries of a young black female into a white one. The latter was then bred to a white individual, and whereas a normal white individual cannot have any black unit characters in its germ cells, and therefore should produce only white indefinitely when mated with another white one, the offspring of this union were black, showing conclusively that the inheritance lies in the germ cells, and that this somatic characteristic of the foster mother in no way influenced the offspring, although all of its nourishment, both in utero and later, was derived from her body. Occasionally the dominant contrasting characteristic of the parents is not exhibited in all of the cross-mated young in the same degree, but a blending of dominant and recessive traits may occur. Thus among silkworms, a cross of the Shanghai variety which has a white cocoon, and the yellow var with a rose yellow one, produces a form whose cocoons are straw yellow. Again, the blend may be a chemical one, as in grapevines, of which the aramon coloring matter has the chemical formula C46H36O20. The teinturier has the formula C44H40O20, and the Petit Boucher hybrid has the formula C45H38O20. With peas, Mendel bred one 1 foot high with another 6 feet high, producing an hybrid with a height varying from 6 to 7.5 feet, while the crossing of the flower Mirabilis jalapa, female, red, with the male white, produced offspring with red, white, and red-white streaked flowers, the last being an instance of mosaic inheritance. In many instances exhibiting at the first blended inheritance, the regular 3:1 splitting of dominant and recessive characters may occur in subsequent generations. Experiments carried on by Miss McCracken on little beetles have shown that the dominant unit characters tend gradually to extinguish the recessive ones, so that while for 3 or 4 generations the normal 3:1 ratio prevails, in the 7th generation the proportion may run as high as 28:1. Another phenomenon is the decomposition of varietal characters, which may be interpreted to mean either that 1. The dominant and recessive features are not simple unit characters, but are in reality complex, the resultant of several combined characteristics, or that 2. There exists a real instability in the parent type, and that the stimulus or influence of the cross mating is all that is needed to break down this weak apparent stability of the type and allow its component characters, the elementary units of De Vries, to recombine into various new and differing types. This may be the cause of the extraordinary variation brought out by hybridizing. Jordan and Kellogg. Luther Burbank, whose breeding experiments with plants have produced such marvelous results, depends very largely upon this as a basis for his intensive selection. Mendel's law, therefore, while apparently a generalization of the greatest importance, does not apply universally to all cases of inheritance. End of chapter 10C.